Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the R-PYQ series for control systems. So this will be the part 1 where we will be discussing about basics of control system, and the next chapter would be SFG and block diagram reduction technique, and the third chapter would be time response analysis, which is the very important chapter. So we will cover everything in detail. There will be almost minimum formulas, like minimum, as low as possible. Once you will study, trust me, you will realize like to what level I have taught you, and without mugging up the concept, we have solved using basics. So there is a huge problem in non-unity feedback for steady state error. Okay, so we have solved for that case as well. We have discussed that in detail, but literally in a lucid manner, very simple manner. So everything has been covered. So this will be, I think, around 7 hours, 8 hours, I don't know how long, a marathon. So just one request, please hit the like button, right? Please comment down below if you enjoyed the RPYQ series. Please hype the video. So all these things really help us and keep us motivated so that I can make the next part as well. Okay, so after this there will be part 2 and part 3, part 4. So I will have divided control systems into 4 parts, so they will come as I record them. Okay, yeah. So yeah, that's it. So let's start with basics of control system. So before this, there are few prerequisites that I want you to go through. So this one is the first one. I hope you have already gone through. This is already included in the playlist wave curve method. Also, uh, basics. Although I will tell you few Laplace transform, but it will be better if you already know basics of Laplace transform. So this anyways you study in your college, right? Basic formulas also is more than enough. What is Laplace transform, how to use the formula, that is more than enough. So first of all, let's discuss why do we study control system. There are many reasons to check the stability of a system. So I hope you have already heard about this kind of block diagram, or you have seen this kind of block diagram. I have a uh, block diagram like this, right? Feedback HG, and then I have a negative feedback. Here I provide my input r of t, let's say. Here I get the output c of t, and by knowing this transfer function I can directly comment if my input is some input, right? For a specific input, will the output also will be bounded, basically stable. Bounded meaning the output will be between minus infinity to plus infinity. It will not, like, it will be some finite value, not infinite. So what is a real life example? Real life example would be something like this. Let's say I have this MOSFET here, and like I'm just drawing the like small signal model. Okay, I'm not drawing exactly the large signal model. Sorry, not the MOSFET. I have op amp here, correct? And this op amp is connected to a MOSFET, and it is connected via feedback. And here I have some resistance, and there are some voltage sources. I don't care. Okay, there are some voltage sources, resistance, I don't care. So it is like a feedback. To understand the stability of this feedback, whether this system will be stable or not, all these things will be taught by control system. Whether my system will be observable or not, whether it will be controllable or not. What do I mean by observability, controllability? These things you will learn in state space. That will be the last to last chapter, like before the last chapter. So this will take us a while. Before that, we'll cover a lot of things. Okay, so state space in which you will understand, and stable or not, in today's lecture only you will understand what do I mean by stable system. So basics of Laplace transform. So this is the Laplace transform. Basically, we convert our time domain signal into frequency domain. So Laplace transform basically means it is a mathematical tool used to get information in the frequency domain. So I have a signal x of t. This has information in the time domain. Now I want the same information in the frequency domain. So let's say my x of t is a sinusoid, sine omega t. So I know the time domain information. This is the time domain information. Maybe I want to know the frequency domain information. How will you know? So you might want to know the frequency, right? That will give you the frequency domain information. So all those things are uh, done using this transformation. We transform our time domain signal into frequency domain. So we have a variable x of s that is equals to sigma plus j omega, where omega is the imaginary part of the frequency and sigma is the real part of frequency. S is complex frequency. That's all you need to know. You don't need to do extra PhD on this. That is all. Just S is complex frequency, sigma is the real part of complex frequency, omega is the imaginary part. Okay, or also known as the signal frequency. Okay, don't need to worry about anything else. So there are a few basic things like unit step signal. Unit step signal, it is equals to 1 for t greater than 0. It is equals to 0 for t less than 0. It is similar to a switch, right? It is similar to a switch closing at t equal to 0. Okay, very similar to the switch closing at t equal to 0. Okay, so yeah, now exactly at t equal to 0, what is the state? We don't know. Exactly at t equal to 0, what is the state of u of t? I don't know. Okay, if someone says you what is the state at t equal to 0, I don't know. There will be a sudden jump at t equal to 0, right? So I can shift this signal as well. This you will learn in signals and system, like the shifting property of a signal. It's very simple. If instead of u of t, I write u of t minus 3. So at t equal to 0, it was u of 0, and at that particular point of time, I was getting a switching, right? And here if I put t equal to 3, this will be again u of 0, right? So at t equal to 3, there is a jump. So basically my signal will be something like this. This will be my signal at t equal to 3. Okay, that is how my signal will look like. I hope you have understood this point. So here again our chapter, right, we will be mainly concerned with linear control system. Basically all the systems will be linear. Like I hope you remember, basically we can define our system with linear differential equation. Linear differential equation. Now I will not explain what is a linear differential equation, because that has been taught to you, right, in differential equations in mathematics. So all my systems or transfer functions can be defined with linear differential equations. Or another way to understand linear is it must follow these two principles: homogeneity and superposition. So let's say if I give some input x of t, x1 of t, for that I get y1 of t. Now if I give some input k into x1 of t, k into x1 of t, right, for that I will get k into y1 of t. This is the property of being linear. Now sorry, property of being homogeneity. Homogeneity has two things, right? One is this, it must be linear. Another one is okay, this is my homogeneity. Basically this is my homogeneity. And superposition meaning that basically, let's say for x1 of t I was getting output y1 of t, for x2 of t I was getting output y2 of t. Now if I give input as x1 plus x2 of t, then the output also should be sum, basically y1 plus y2 of t. I'm just writing in rough, but I hope you get the point. And this you have already learned in network as well, correct? So this is the property of a linear system. The property of a linear system, trust me, they will ask you a question from this. I'm telling you, they will ask this basic question: when is my system linear? And they will give some four. So basically, right here I have this block diagram. Okay, this is my let's say this is my transfer function for now, t of s or h of s for now. Okay, and in time domain, this is in Laplace domain. In time domain, it will be h of t. So here I will give some input x of t, and I will get some output y of t. Okay, so yeah, x of t I will give it some input x of t, and I will get some output y of t. Okay, so that is the thing basically. Now that is like then this system has to follow this property. So if I give some input x1 of t, I will get y1 of t. If I give some input k into x1 of t, I should be able to receive k into y1 of t. So we will understand this more, like you will get an idea more about this in signals. So I'm not going too much in depth here, but mostly we will discuss about linear systems. Okay, So there are a few basic Laplace transforms. So Laplace transform of a step will be 1 by s. So there is a derivation. I'm also telling you, you must go through Laplace transform before this. So I will not derive. Okay. So similarly, Laplace transform of a into ut, like let's say 3 into ut will be 3 by s. Right. So simply a constant will be multiplied, because in the formula also something like that happens. Constant can come out of the integration. So there is no problems. Similarly, if I do Laplace of transform of, let's say, u of t minus 3, then again if you use the formula, what will happen? Laplace transform of u of t is 1 by s, and u of t minus 3, for that I have to just simply multiply another e raised to power minus 3s. That's it. That's it. Okay. That is the extra term that I need to multiply. That has been derived in the formula as well. You can go through and see the formula, like the derivation. You will understand how it comes. Okay, so these things are basic, so that's how you remember. If you ever forget this, again you can derive it through the basics. I am not deriving it because we don't have enough time. So Laplace transform of any signal, let's say I know Laplace transform of xt in time domain is x of s, then Laplace transform of xt minus 3 would be x of s as well, multiplied by the extra exponential e raised to power minus 3s. Very simple. Any signal, this will always be valid. For any signal, this will always be valid. So yeah, shift in time domain is simply multiplication in exponential domain. That is what is written over here. Similarly, unit ramp signal is similar to unit step, but the difference is, of course, it will be a ramp. So t less than 0, it will be 0, but t greater than 0, it will be equals to t, and the Laplace transform of it will be 1 by s square, and Laplace transform of a into t ut would be a by s square. So remember, you have to write ut represents that t less than 0, the signal is 0, and t greater than 0, the signal is 1. You must write t into ut. If you just write t, then what is the graph of this? The graph of this would be something like this, and that is fine, but that is not the signal that we are describing. So whatever Laplace transform we are doing, all these are for causal signals. So don't be scared. You learn about this in signals. Causal, anti-causal, non-causal. You learn about this in signals. Okay. Causal meaning the signal exists only for t greater than 0. Signal does not exist for t less than 0. That is what simply causal means. So we are actually defining this particular signal. To define this, you must write t with u of t. You cannot just simply write t. That is a problem. You cannot simply just write t. Okay, yeah, that is the thing over here. So yeah, Laplace transform of t minus a into ut e raised to power minus as by s square. That's all. So yeah, if I do t minus a into ut, it will be e raised to power minus a by square. This is actually wrong, because what did I tell you? I have told you the Laplace transform of x of t minus a would be x of s into e raised to power minus as. But you are just changing this t. You are not changing this t. This t is also important. You must change all the t's. You must change all the t's here. Okay. So Laplace transform of r of t minus a, that is t minus a into u of t minus a, would be this. Absolutely valid. But what is the Laplace transform of this? So again, we can simply use bit of tricks here. So what I will do, I will break this down. I will multiply t into u of t, and I will multiply minus a into u of t. So I know the Laplace transform of this. The Laplace transform of this is 1 by s square. What is the Laplace transform of this? Laplace transform of this is minus a by s. Okay, because this is what? U of t Laplace transform is 1 by s, and I have multiplied minus a. So simply minus a is multiplied. So that is the Laplace transform of this particular signal. Okay, it is not this. This is for this one, this signal. So please be mindful when doing this kind of properties, using these properties. Be very, very mindful. Next, we have unit impulse signal. Impulse basically means when at t equal to 0, I am providing a very high value, very sudden jump. So let's say I have a small wire, okay, and I provide it a voltage source, and for a very small second I connect and then disconnect. At t equal to 0, I connect and then again disconnect it. That basically means what is the current through the wire? I. Current through the wire would be V upon 0, that is infinity. Okay, so I is infinity, and we define this infinity with impulse. We say it is just like an impulse, very high value. So at t equal to 0, I will see very high value, so we represent the impulse like this. There will be arrow, and after t equal to 0, before t equal to 0, it is nothing, like there is no current, so it is 0. So that is what basically impulse means. At t equal to 0, I'll get infinity value, and at t equal to not equal to 0, I'll get 0 value. Now impulse can also be defined like this. So this is the property of impulse. I have not shown you. Basically what we do is, if I say my signal is a square, okay, square like this, and let's say this value is some alpha, minus alpha, this is alpha. Alpha is a very small positive number, or let's say this is 0 minus and this is 0 plus, right, just before 0 and just after 0, and let's say this value is a. Okay, so we say sorry, this value, let's say, yeah, this value is a, and what we say is we try to make, okay, let me not keep it a, yeah, let me keep this value to be minus 1 by 2a, and this to be minus plus 1 by 2a, and this amplitude to be a. Okay, so what is the area here? Area here, I hope you understand, it is 1. Area here is simply unity. Okay, so area is 1, right? So if area is 1, then yeah, if you, what you do, you keep on, because what is my impulse? My impulse is at t equal to 0, it should be infinity. So I will increase my a further, very towards infinity, right? If I keep on increasing my impulse, what will happen? This width will die down, will reduce, but the height will increase, and this will keep on happening, right? Height will keep on increasing, but my area is constant. My area is 1. That's why the name unit. Unit represents the area of the impulse. Area of the impulse is unity, although the value is infinity at t equal to 0. If I keep on increasing the a, but area is constant. So that is the property of impulse, of a unit impulse. The area from 0, because if I keep on increasing my a, right, it will be just before 0, and this value will be just after 0. So area of the impulse is actually constant, that is 1. This is the property of impulse. Similarly, if there is a delta of t, that basically represents that this a represents the area of my impulse. A represents the area of the impulse. Okay, I hope it is clear. So yeah, a into delta of t minus a. So if I do a into delta of t minus a, so this will be simply a, that is the impulse. So what is the Laplace transform of delta of t? You can see by the formula, Laplace transform of impulse of t would be 1. Laplace transform of impulse of delta of t would be simply 1. That is the only thing that you have to keep in mind. You can ignore the convolution for a second. You will understand more about convolution in signal and system. Here I am just ignoring, because this is a rank improvement batch, so I am ignoring this convolution for now. But this, for the students who have studied convolution, they will understand. So basically, if I have a transfer function, okay, this block h of t, and I have this input r of t, and I have this output c of t. So basically my output c of t will be, it is not simple multiplication, it will be convolution of h of t into r of t. So this star symbol is represented using convolution. Okay, star symbol is represented using convolution. That's all. So yeah, okay, so yeah, that's pretty much it actually. So but for the students who don't understand this, don't worry, because in control system this thing will not be asked to you, but like few basic things will be asked. I will discuss about those things, but in signals you'll study more about this, okay. So okay, that is one thing. So the Laplace transform of impulse is 1. So Laplace transform of a into delta of t minus a would be simply a e raised to power minus as. What is delta of t minus a? Delta of t minus a basically means impulse but shifted by a period of a, right? So basically previously the impulse was occurring at t equal to 0, now it will occur at t equal to a. Pretty simple to understand. Now let's discuss about few more things. So there is bit of analogy. So if you see, the Laplace transform of my step was 1 by s. Laplace transform of impulse is 1. So if I multiply in frequency domain by s, I get back to this particular thing, right? And Laplace transform of ramp signal is 1 by s square. So I have to multiply by 1 by s now. I don't have to multiply by s, I have to multiply by 1 by s. So that is the thing basically. Now what happens? There is bit of relation. So multiplication by 1 by s in frequency domain represents taking the integration of that particular signal in time domain. So let's say I have u of t and Laplace transform of u of t is s. So if I multiply this with 1 by s, what is the inverse Laplace? It is 1 by s square. And what is the inverse Laplace of 1 by s square? It is r of t. So what is the relation between u of t and r of t? R of t is nothing but running integration of u of t. R of t is integration, right? Integration of u of t, correct? Into dt, 0 to infinity. Simply if you integrate this, what will you get? U of t is equals to 1 for t greater than 0, otherwise it is 0, so it is 1 dt, so it is nothing but t basically, right? Basically the 0 to t running integration, that's why you will not put the value of t, you will say it is running integration because t is always running, t is constantly increasing. So this is t into u of t, because you have to multiply u of t because t less than 0, this signal is always 0, integration is 0, right? That's why you must multiply u of t, you must multiply u of t. So basically what do you see? You see it is my ramp signal. So simply if I multiply by 1 by s, I am integrating in the time domain. If I multiply by 1 by s, I am integrating in the time domain. If I multiply by s, I am differentiating in the time domain. How? So if I multiply by s, my u of t, u of s, it is simply 1. And what is the inverse Laplace of 1? It is delta of t. So basically what is the relation between u of t and delta of t? So u of t is nothing but the derivative of, delta of t is nothing but the derivative of u of t. How? So you see, if I differentiate this function, so what is the slope? Slope here is always 0. Slope here also t less than 0, it is always 0. Only here there is a sudden change. So what is the slope of this particular point at this particular point? So I can say slope will be u of 0 plus. So let me write this. Slope formula is simply x of 0 plus minus x of 0 minus just before the value, before t, and it is t plus 0 plus minus 0 minus 0 plus, let's say this is some delta of t, right? That is my slope basically, du of t upon t, right? This is my delta of t. And yeah, this value is 1, this value is 0, so it will be 1 by delta of t. Now delta of t is very small basically, like very small difference, right? Very small, very small, like there is literally no time given, the value changing. So this is turning to infinity basically. So this is nothing but the impulse signal, because impulse signal also represents the same thing. T greater than 0, it is 0, t less than 0, it is 0, just at t equal to 0 it is infinity, that's it. Okay, that's all basically. So I hope you have understood this point. Okay, so yeah, that's the one property, that's a very important property that I want to say. So basically you remember this thing as well, your step response. So if I want to go from impulse response to step response, what do I have to do? I have to multiply by 1 by s. So that means I have to integrate my impulse. So you remember it like this. Okay, just remember this. You must remember, and how to remember also, like I have told you the analogy. So your step response will be integration of impulse response. Okay, what do I mean by impulse response? So basically, I have a block diagram, transfer function h of t. For that, I give some input x of t and I get some output y of t. Okay, and my output y of t is basically convolution of h of t into x of t. So there is one property. Now I am not getting into the property right now. So if I convert this equation into Laplace domain, it will be y of s will be equals to h of s into x of s. I am not discussing how this comes. For now, you just understand this. Convolution in time domain will be multiplication in frequency domain. We'll be taught more about this in signals and systems. Now, this is my property. So now if let's say my input is delta of t impulse, then what is the Laplace transform of impulse? It is 1. So simply my y of s will be h of s. So what will be my y of t? Y of t would be simply h of t. So whenever my input is delta of t, output is simply the transfer function only, h of t. That's why it is called as the impulse response. This h of t is also called, it is actually not called as a transfer function, because transfer function it is called whenever we are discussing in Laplace domain, because transfer function is the ratio of the input by output in Laplace domain with no initial conditions, because our system will be linear only, no initial conditions. That is the basic definition of transfer function. Now here, if I tell you what is impulse response? So impulse response is simply the response when my input is delta of t. So here I'm providing input delta of t, so my output is nothing but h of t. So that's why h of t is called as the impulse response. That's why h of t is called as the impulse response. Okay. Now there are few properties. What if my input, instead of being impulse, it was step, right? U of t. So if it is u of t, then here in x of s, instead of 1, my y of s will be h of s by s, right? H of s by s. And what do I do? So h into h of s into 1 by s. So what is this? It is nothing but integration in the time domain. So basically in the time domain, what is happening? My output y of t is integration of h of t dt 0 to t, running integration, or sometimes it is called minus infinity to t, because I am taking the for t less than 0 as well, I am taking the values. So that is what is written over here. Okay. So basically my step response meaning whenever I am providing my input to be step, whenever my input is step, the response for it will simply be the integration of my impulse response. Step response meaning output only. Output when the input is step. Okay, it will be simple integration, running integration. And similarly, impulse response will be just the difference, right? Opposite, sorry, not the difference, will be opposite. Basically, it will be the derivative of step response. Okay, so my impulse response will be the derivative of step response. That's all. Okay, I hope you understood this basic point. Yeah, that's all. Yeah, so yeah, that's all. Now there is another signal, very important, exponential signal. So the Laplace transform of exponential signal e raised to power minus at, because this is a stable signal. How it is stable? Basically, if I plot this signal, right, at t infinity, it is dying down or it is bounded. So that's why we call it as a stable signal. Let's say I plot this, right, e raised to power 80 where a is greater than 0, a is not less than 0. So what will be the graph of this? This will be the graph. Okay, into u of t is there, so for t less than 0 it is 0 simply. So you are saying at t equals to infinity the value is not settling. So here, right, you might have a doubt, how is this impulse a stable signal? It is because at t equals to infinity the value is bound at 0 for only a certain point, for a certain second it is going to infinity, but for other periods it is never going to infinity, it is bounded. But here if I see, for large period of time the value will be very large, it will be tending towards infinity. So that's a problem. Okay, that's a problem basically for us. So yeah, I hope you have understood this basic thing. So yeah, that's the thing. So this signal is not stable, but of course Laplace transform for both of them exist. Laplace transform of this will be simply 1 by s plus a. So sign will change basically, and Laplace transform of this e raised to power plus at will be 1 by s minus a. So basically, if I have exponential, the sign will just revert here. That's all. If I have exponential, the sign will revert. Okay. Similarly, another property is there, that let's say uh, that I have any signal x of t whose Laplace transform is x of s. If I multiply any exponential e raised to power minus 18 into x of t, the Laplace transform will be simply x of s minus a, sorry, s plus a. So multiplication with exponential in the time domain will be shifting in the frequency domain. That is also a very good property that will be useful to us. Also, the Laplace transform of sinusoid and cosinusoid, this you have to remember. This you have to remember. So how do you remember? There is a very easy way to remember for the students who understand initial value theorem. For the students who understand initial value theorem, they will be able to relate with this thing. So what does my initial value theorem tells me? So initial value theorem here would be that, like for the students who know initial value theorem, great. For those who don't know, I will come to it later, but yeah, let's discuss about that for now. So initial value theorem is basically, it gives me the value of signal at t equal to 0. How do I get the value of the signal at t equal to 0? So you multiply s, limit as s, just give me 1 second. S into hex of s, limit as s tending to infinity. This is my initial value theorem. For the students who don't understand, don't worry, I will come to it just in the next few slides. So if I do that same property here, use the same property, if I multiply s into omega naught upon s square plus omega naught square. So if I put s equal to infinity, what will happen? If I put s equal to infinity, obviously denominator, the power is higher, so it will go to 0. And it is correct, because what is it? At x equal to 0, I'm expecting it to be 0, and it is 0. But if I multiply s here, this will be s square by omega naught square. If I put s equal to infinity, obviously the powers of the numerator and the denominator are same. So only I will take the higher order powers. So it will be s square by s square. I will ignore omega naught square because it is a constant. As s is very high, this is a constant, I can ignore it. This has been taught to you in mathematics, limits. So s square will be cancelled. That will be 1. Limit, basically here I am not writing limit as s tending to infinity. I am not writing that value. Okay. So it is going to 1, and that is what we expect, right? Because at t equal to 0, cosine is 1. So that's how you remember which is which formula, because I also many times get confused, like should I use this formula for sine or this formula, because there will be only two things. Like you will remember both these formulas, but you will not be able to figure out which one is mapping to which formula. So that's how you map out. So you can use the help of initial value theorem, because you will not be able to apply the final value theorem, because for these two signals final value does not exist, because the signals are oscillatory in nature. So these are also stable signals, but they are oscillatory. Why? Because there is no like constant value that it is settling to. It is always changing between -1 to +1. Although both -1 and +1 are bounded, they are not infinity, but it is not a constant value as well. It is not settling to a value. It is always changing. So that's why finite value theorem will not be applicable, but initial value theorem will always be applicable. Your system must be causal, that's it. That is one thing. Your system must be causal. Okay, so that's how you remember the formula for sinusoid and cosinusoid. So if you enjoyed this, hit a like button and comment down below if you are finally able to remember the mapping. So yeah, then there is damped sinusoid. How will you remember? Damped sinusoid basically meaning I am multiplying exponential with sin omega t. That is called a damped sinusoid because at infinity the value is going to 0. So simply whatever property I have told you, right? I have told you this property that if I have some x of t, the Laplace transform for it is x of s. If I am multiplying e raised to power minus at into x of t, the Laplace transform for that would be s plus a into x of sorry, not this. Sorry. So I have to do x of s plus a. That's it, right? So similarly, in this case, our x of t is sin omega naught t. So what is the Laplace transform of sin omega naught t? It is omega naught by s square plus omega naught square. So what will be the Laplace transform of this e raised to power minus 8 into sin omega naught t? It will be simply, I will replace s with s plus a. Omega naught by s plus a whole square plus omega naught whole square. That's all. I'll replace my s with s plus a. That's all. Okay. So that will be the Laplace transform, as you can see. Similarly, you can derive for e raised to power minus 80 cos omega naught t. Please put it in the comments below and tell me that yes, I was able to derive it for e raised to power minus 80 cos omega t. Pause the video. Try it now. So then we have this pulse kind of signal, right? So for this, you can again break it down into two parts. You can find out the Laplace transform of this, you can find out the Laplace transform of this, and your final resultant will be, subtraction will be your final answer. Okay, yeah. So yeah, differentiation in so this I already have. So one more thing is there, yeah. So while taking the derivative, right, just be careful here. Just be careful here, because I will tell you, you will forget something. So let's say your impulse response is u of t, okay, which is basically 1. Oh, sorry, not your impulse response. Let's say your step response is u of t, which is 1. Right? It is 1 for t greater than 0, it is 1. Now, the question asks you to find out the impulse response. If they tell you that the step response is u of t and they're asking you to calculate the impulse response for the same exact system, what you will do? So you already know this particular thing, that it is derivative of step response. So you will differentiate one which is constant and you will say it is 0. The impulse response, you will say it is 0, and in one of the options 0 will be there and you will take it mark and move ahead, but you will be wrong. Be very careful whenever there is u of t, very careful. So you don't write it 1, right? You write u of t only. So what is your impulse response? It is the derivative of your step response. What was your step response? It was u of t. So your impulse response would be dd of t into u of t, which is equals to delta of t. It is not 0. So where will you make a mistake? I can say, so basically, let's say if your step response is t, what is your impulse response? It is 1. But if your step response is t into u of t, what is the impulse response? It is not 1. So you will use the chain rule here, t into u of t. So chain rule I can use. So first I will differentiate t, that will be 1. then, and first I will differentiate t, that will be 1, and I will keep the other term as constant, plus now I will differentiate the other term, that is u of t, that is delta of t, and I will keep the other term to be constant, that is t. T into delta of t, that's it, right? Chain rule, simple chain rule. Now you're very lucky here that if I'm multiplying by impulse, right, and we know impulse only exists for t equal to 0, it does not exist for any other value. So for any other value it will be always, this product multiplication will always be 0, and at t equal to 0 as well it is always 0. Why? Because I have here impulse, that is infinity, and with infinity I'm multiplying 0, so it will be 0 only. So you're very lucky, you'll get it as u of t. But one day something will happen. Let's say here, instead of t u of t, it will be t minus 1 into u of t. Then you will be gone. Okay. So yeah, pause the video and try to find out, if my step response is this, what is my impulse response? Okay, what is my impulse response? So just be careful, use the chain rule and solve it, okay, properly. Don't ignore u of t. Don't ignore u of t. U of t is very important. It is just like a function. U of t is just like a function. Don't ignore it. Okay, that was the thing basically. So similarly, yeah, integration property I have told you. So there is a differentiation property and integration property in uh, frequency domain as well. So if I am multiplying by t in time domain, that means I am simply taking the negative derivative in frequency domain. How can I understand this? So for t, so for u of t, the impulse response, sorry, the Laplace transform was 1 by s. For t into u of t, I'm just simply multiplying t into u of t. The Laplace transform was 1 by s square. So this, right, is nothing but the negative derivative of this particular term. If I take the negative derivative of this, it will be 1 by s square. Okay, I hope you have got this point. Now, similarly, for t raised to power n, this is the formula. So you don't need to remember this formula per se, just remember this particular relation, right? Again, if I multiply t, what will happen? This will be t square into x of t. Again, I will differentiate negative. So already I have dd of s into x of s minus. Again, I am taking the negative derivative, right? So minus can come out. So it is just a constant. This will be d square of ds square into x of s. That is the thing over here. D square by ds square into x of s. Right? I hope you have understood this point. Yeah, that's all. So like here, if I put n equal to 2, this will be same as this formula. So don't remember this formula per se, you can remember it like this. You just remember this, and from that you can derive for higher values simply, right? You can derive for higher values. Okay, similarly, if I divide by t, it is nothing but the running integration. Okay, this is another property, but we will not use this property actually. We will mainly use this property, that's all. Okay, don't worry about this property, mainly we will use this property. So here I have this kind of, so pause the video, I have this kind of signal. First of all, you can calculate the y of s. Before that, you have to write your y of t in terms of your step signals. So this will be u of t. So pause the video, try out by yourself. This will be u of t minus 3 minus u of t minus 1. Simple. Okay. So simply you can do it. Sorry, I'm also making a mistake. So basically, first of all, right, what is happening? This is a combination, this pulse signal is a combination of two step signals with a subtraction sign. Two step signals with a subtraction sign. So I have here, so actually this is incorrect. This will be, y of t minus 1, e of t minus 3. So that's all. So yeah, so yeah, so now what shall I do? Yeah, so like I hope you understand, like this is my first step signal. At t equal to 1 I'm getting a step signal, and again another step signal I'm providing at t equals to 3, and I'm basically subtracting these two because the pulse duration is from 1 to 3, so it will be 1 between 1 to 3, otherwise it will be 0. That's why I'm taking the subtraction. So I hope I don't need to explain here much, you can understand it. Now I hope you can also don't forget the magnitude. This will be 10. Okay, this will be 10, this will be 10. Don't forget the amplitude of the step signal, and of course then you can take the Laplace transform, as you can see. And they are asking you to find y of s. Y of s would be this is all your y of s basically. And here I have this h of s. Can you find out the Laplace inverse of this? So you have already seen the solution, but it's very simple. You will break it down in partial fractions, right? That is what I have done here, and I know what is the, so I hope you know how to find out the partial fraction. I will not teach you that thing. So this will be 1 by s plus 2 plus, if I put s equal to minus 3 here, this will be minus 1 by s plus 3. That's all. So yeah. So what will be the Laplace inverse of this? This will be e raised to power minus 80 2t into u of t. Don't forget the u of t. Write the u of t. And this will be e raised to power minus 3t into u of t. Okay. So that's how you solve it. Very basic, plain and simple. So Laplace transform of this also you can find out. So if you know the Laplace transform of e raised to minus t ut, that is simply 1 by s plus 1. If I multiply by t, what will happen in the frequency domain? I have to take the negative derivative of this, right? That is what I am doing here, just taking the negative derivative. Okay. So yeah, these are the few things basically. So there are few Laplace transform of passive elements. This I think you have already learned in network. Again, I will go through those once again. So I have resistor. Yeah, I have resistor, inductor, and capacitor. So resistor, right? It is like a constant value. So what is the Laplace transform? So if I take the Laplace transform of this whole equation, it will be v of s. This will be I of s, and this will be simply r. There is no difference, right? This Laplace transform of r is just r. Right? So impedance is the ratio of voltage in Laplace domain by current in Laplace domain. Similarly, for inductor, your VL is equals to L dIL by dt. So if it is L dIL by dt, what will be the Laplace inverse? So I know if I am differentiating in time domain, that means I am simply multiplying by s in the frequency domain with the Laplace transform of this internal signal, that is IL of s, and L is just a constant. So the ratio of voltage upon current in Laplace domain is my impedance in Laplace domain, that is s into L. So it is frequency dependent basically. If I replace my s equal to j omega, so I see it is directly proportional with omega, and this you have already studied. Similarly, for capacitor also you can do the same thing. It will come out to be 1 by Cs. So this is the summary. You must know this, and I know you already know this, but just revising few things. Now let's discuss about system. So what is a system? It is a group of physical components which gives proper output for a given input. This is my system. So this is just a block. I will give it some input like step signal or any signal, and I will get some output. So I can have a integrator as a system. So if I give it some input, it will just integrate the input and give it to me as the output. So in control system, we will be discussing about LTI systems. LTI meaning it has to follow the property of linearity, and it will be also time invariant. What do we mean by time invariant? So time invariant basically means if I shift the input by a amount t naught, the output also will be shifted by the same amount t naught. It will so basically, let's say for a step input, let's say I have a integrator as a system. So what will be the output? It will be a ramp input. Sorry, ramp output, right? The response will be simply ramp. Correct? R of t, which is basically t into u of t. So let's say now I shift this. If I shift this t minus 5, what will happen then? What will be the integration? If you calculate the integration, your integration will come out to be exactly r of t minus 5. That will be equals to t minus 5 into u of t minus 5. You can verify this, you will get the same value. If you simply integrate this, you will get something like this. I am not getting into the maths right now. When it will not follow, so let's say I have an input something like this. So okay, I have not given any example here. So for this kind of system, wherever my y is equals to x square of t, okay, so in that case, if let's say my x, so for y equals to x of t, right, y of t equals to x of t, this is also a system. Simply I am getting the output, it is a buffer. So if I shift, if my input is u of t, my y of t will be u of t. If my input is u of t minus 5, my y of t will be u of t minus 5. But let's say, so if my input is r of t, my y of t is also r of t only, right, because y of t is equals to x of t. And if my input is r of t minus 5, that is simply equals to t minus 5 into u of t minus 5. So now let me take an example. So let me take an example, my y of t to be equals to x, or yeah, t into x of t, right? Y of t is t into x of t. That is example. So there will be some transfer functions for this system. I don't care about that. So now if I say for input u of t, what is my output? Output is t into u of t, right? Now if I shift my input u of t minus 1, what will be the output? Output will be just this input I have changed, right? I have not changed this time. So your output is y of t equals to t into u of t minus 1. So is it, let's say for this, right, this is my response, right? Let me write this as y1. So is my y2, let's say this is my y2, is it y2 of t, is it equals to y1 of t minus 1? Because for the input as well, I changed t to t minus 1. Did it happen? No. If I replace my t with t minus 1 in y1, sorry, sorry, y1 is not this. I'm extremely sorry. Y1 is this. Yeah, this is my y1, right? T into ut. Simply this is my y1. Okay. So for this particular input u of t, the output is y1 of t, that is t into u1 u of t. And for this particular input x2 is simply, x2 of t is simply what? x1 of t minus 1, right? x1 of t minus 1. So is my output as well y2 of t is just y1 of t minus 1? Does it follow this relation? No, it does not. If I do y1 of t minus 1, I will replace my t with t minus 1. So it will be t minus 1 into u of t minus 1. So it will be t minus 1 into u into t minus 1. That's it. Correct? So here are this value and y2 of t, is it same? No, there is t minus 1, there is t. So these are not same. It is time variant. Basically time variant means basically my output will be dependent on time. If I'm shifting my input by some value t naught, output will not be shifted by the same amount. Output will be something else. But in case of time invariant systems, if I shift my input by t naught, output also will be shifted by t naught. What is example? This is a very basic example, right? So if I was shifting my input to t minus 5, right, my output was what? T minus 5 into u of t minus 5. So this is nothing but y1 of t minus 5. I'm going a bit fast here because these things will be taught to you in signals, and this is not the main focus area. Just I'm giving you a bit of intuition. Got it? Okay. Like causal, non-causal, mainly we'll be discussing about causal systems, so don't worry. Okay, and one more thing, basically impulse response I have discussed. What is my output? Output is convolution of my Where is it? Yeah, output is convolution of my input. Where is it? Impulse response I have discussed. Where is output? Where is that thing written? Yeah, here. So my output will be convolution. This is the convolution sign. Don't get scared because no one will ask you in control system. No one will ask you about convolution. This will be asked in signals. Okay, cover it in signals. Don't worry. So whatever are the important things that I have already discussed. So transfer function is nothing but the ratio of the Laplace transform of the output over input. So it is also called as the impulse response. Why? Because as it is output over input, right? And if my input is impulse and I know the Laplace transform of impulse is 1, so it will be output over 1. So transfer function T of s is simply output, Laplace transform of output when the input is impulse. That's why it is called as impulse response. Okay, that is the thing. Also, the roots of my new denominator are actually called as poles and they define the stability. Very, very important thing. I will come to it. So basically, if I have, let's say 1 by s plus 3 into s plus 2, and this is a transfer function, right? And all my poles are lying on the left half plane of s plane. So this is also called as sigma plus j omega plane. So s is equal to sigma j omega, right? What are the pole locations? Sigma is the real part, omega is the imaginary part. So do I have any imaginary poles here? No. All values. So pole basically means whenever my denominator will go to 0. So at what value of s it is going to 0? S equal to minus 3, s equal to minus 2. At these values it is going to 0. So this is my location of poles. So poles are denoted by a cross symbol, minus 2 and minus 3. All these are real values. All these are real values. So I will write them in the real axis. If they would have been something like this, if my poles would have been s square plus 1. So what are the pole locations? S equal to plus minus j1. So these are imaginary. So I will show my poles like this on the imaginary axis. I hope that is clear. So this is my S plane, sigma plus j omega plane. Now the interesting fact about this thing is, if my poles are lying on the left hand side of S plane of the transfer function, remember I'm talking about the transfer function. There is another term known as OLTF. OLTF is the open loop transfer function. Of course, I will come to it. And this transfer function is also called as the closed loop transfer function. I have not discussed about loop, so don't worry about it. Not discuss about feedback. So if I have a transfer function that is also called as closed loop transfer function, and if all the poles are lying on the left hand side, the system will always be stable. How? If I am providing an impulse, what will be the response in time domain? This will be, again you can like this, for this we have derived the time domain expression, right? There will be some e raised to power minus 3t and there will be some e raised to power minus 2t. I don't worry about the constants for now. And of course at t equal to infinity, all these are decaying, right? What if this was s minus 3? Then I would have had a pole on the right hand side of j omega axis. J omega axis, right? On the right hand side of j omega axis. What is the problem? The problem is due to this particular pole, due to this right hand pole, I will get a exponential term which is not decaying. I will get a exponential term which is increasing. It is not decaying. So if it is increasing, what will happen at t equal to infinity? It will be unbounded. So of course the impulse response is unbounded. The output for a finite input, the output is going unbounded. That is a problem to us. So we don't like these kind of systems. We don't like our output to go unbounded even though for I'm providing it some proper input. That is a problem to us. So we hate this kind of system. So that is what we will analyze in control system. So I hope that part is clear what exactly we will do in control systems. Okay, I hope that part is clear. So yeah, we will not discuss about non-LTI systems. Here we have, are we seeing like this is a non-LTI system, this is a this is a time variant system as well and non-linear system as well. So not non-linear, time variant system. Don't worry, this will be taught to you in signals and system. So don't worry about this for now. LTI, non-LTI, don't worry. Okay. Yeah, that's pretty much it. So these are few easy way to find out the transfer function. Let's say generally they will ask you to find out the transfer function and they will tell you what do they mean by transfer function. It will be V of s by V of s. So what is a V of s over Vi of s? Simply you can take the Laplace transform and simply you can use the voltage division. What if they would have defined this current I of s? Okay, or let's say this current II of t, and you have to find out the transfer function VO of S over II of S. What will be it? So this II of S is also flowing here, right? II of S. So simply I know the voltage across this resistor because this current is same. Here there is no current. I know the current across this resistor. So the ratio of these voltage and current in Laplace domain will be just resistor. So your transfer function will be R. So actually generally they will ask you this voltage gain transfer function only. Mostly they will provide some input voltage and they will measure the output voltage. 99.99% of the cases this will happen. But for 0.01% of cases, maybe they can ask you this transfer function. And don't worry, they will tell you, they will define you that you have to find out this particular value. So they will tell you that. Don't worry about that. Okay. So yeah, that is one thing. That's that. Yeah, I think that's pretty much it. So okay. Yeah, let's discuss about few more things. Now there is one more thing about regarding the order of my transfer function. So order, right, is defined by the total number of independent energy storing element. What is order? Order is basically the highest power of my polynomial that is present. So if I find out the transfer function here, the highest polynomial, the order of the degree of the highest polynomial, like highest degree of the polynomial in the denominator is 1. So I have one independent energy storing element, but this might change. But mostly, if I have one energy storing element, the order will be always 1. Okay. But sometimes what will happen? Sometimes let's say I have this kind of like this statement always holds true that number of independent energy storing element will be equals to the order of my system. Right? This statement will always hold true. What do I mean by independent energy storing element? Let's say I have this capacitor here and C1, C2. Can you tell me what is the order of this particular transfer function if I have Vi of S here and Vo of S here? Actually, this is a zero order system. How? So your Vo of S over Vi of S will always be equals to simply C1 over C1 plus C2. Okay, you can simply apply the voltage division. It will always be this value. That is very interesting. Correct? So this is a zero order system because there is no value here, right? The polynomial term, there is no S term present, right? So I have S raised to power 0 into this. So that's why it is called as zero order system. Why is it called so? So I have told you that order of a transfer function is defined by the number of independent energy storing element. So this capacitor can have an initial voltage across it. I can set any value of any initial value across this capacitor that is independent of whatever the circuit I have. I can have 1 volt as the initial voltage, 2 volt as the initial voltage, 3 volt as the initial voltage, and so on. Correct? Now here what is happening is if I set here, let's say 1 volt, that it will never be 1 volt actually. As soon as I will provide some input, let's say 2 volt I provide, that instant only voltage will be simply divided. It does not matter whether I have 1 volt here. Automatically that voltage will be overwritten and instantly voltage will be shared at t equal to 0. So I hope you have studied transient enough. So I will not discuss about transient here. So I cannot actually set this voltage independently. As soon as I will provide input, right, this voltage will change. Or basically, right, if you set this voltage to 1 volt, what will happen if I short this, right, instantly that voltage will change. Okay. So this voltage, like, you will not be able to set the voltage. In layman terms, just understand this: if your degree of the denominator is 0, it is called a zero order system. Okay. So yeah, we will discuss more about state variables, all those things we'll discuss about it. So again, you can find out the order here. Now, interesting fact is, few students, what do? They understand the transfer function of this, right? RC, and what they do is they do a bit of like over smartness. So they assume that okay, I have some voltage here. Let's say, let me assume this is some VO dash of S. So what I will do, I know what is my VO dash of S over VI of S. That is simply this RC filter. For that, I think no, we have not discussed, but you can calculate. And they will again calculate this value. So this is also RC, right? So they will multiply this again. So whatever transfer function they got, let's say this is one by, like this is the transfer function, 1 by 1 plus SRC, and this is also 1 by 1 plus SRC. Okay. So what they will do is they will simply multiply these two, and they will say this is my overall transfer function. This is wrong, because there is an effect of loading here, right? So you cannot simply multiply. So what do I mean? So basically, right, I'm telling this for the students who understand this. Let's say I had this kind of setup, R, C. Then what I'm doing is I have a buffer. Okay. Positive side is grounded. Okay. Simple buffer I have. Yep. No, let me make it a buffer only. So positive side is only grounded. Buffer does not need a ground. So buffer basically has infinite input impedance for the students who understand a bit of analog electronics. And then I provide this RC. What will happen now? Now if I measure this VO, now your VO by VI would be actually equals to this value, which is correct, because there is no effect of loading. As soon as you remove this buffer, what will happen? I will have R, C, R and C. Now you cannot simply multiply the two transfer functions. You cannot multiply individual transfer functions. You cannot do that, because there will be effect of loading here. Here, right, what was happening? Whatever current was coming here, the same current was leaving, because buffer has infinite input impedance. So no current was going into the buffer. But here, whatever current is coming I here, it is not getting to the capacitor. It is getting divided, I1 plus I2. So that's why we say there is a effect of loading of this RC. So that is the problem here basically. Okay, that is the problem. Here we don't have that kind of problem. We don't have that kind of problem, right? So whenever, because you are very accustomed to seeing this, right? I know you have studied control. So you will see there, let's say I have a block here 1 by S, and then another block here 1 by S. So what is the overall? Let's say this is my X of S, this is my Y of S. You say what is my overall transfer function? My overall transfer function will be simply the multiplication of these two, right? Y of S upon X of S would be 1 by S square. You will say how it happens, but here there was an effect of loading, but here you are saying there is no effect of loading. So internally what we assume, we connect a buffer in between. We don't write it, but actually that is what we are doing. We are connecting a buffer between the two stages. That's why we see whenever we are implementing multiple stages, multiple gain stages, we always implement a buffer, or always implement the next stage should have very high input impedance. If you have studied analog, you will understand this. If you have not studied analog, ignore. Finally, for the students who understand the significance of this, how can I simply multiply this? If you're enjoying this, please hit a like and obviously comment down below that yes, you have understood the concept of buffer and the effect of loading effect. I hope that part is clear. Okay, so yeah, so for solving this, you have to simply apply KCL and then find out the transfer function. I will obviously not solve it. So yeah, control system will be what will happen is, control system will be a combination of controller and system. Control meaning I'm controlling, system meaning it is system components of multiple things. Now what happens is, let's say you have a AC, right? You have AC and you want to set the temperature. So you set it to 25 degrees centigrade. So what will the AC do? AC will simply send cool air, correct? But the question is, till how long will I send cool air? Like if you just put your hands near the AC, you will see you're getting cool air. But till how long? How will the AC understand that I have to send cool air till what point? Because if I keep on sending cool air, what will happen? Initially, let's say the temperature was 30 degree. If I keep on sending the cool air inside the closed room, the temperature will reduce 28, then 26, then it will go below 24. But did you ask it to reduce it to 24? No, you asked the AC to reduce it to 25. Why? Because if it goes below 25, you will feel cold. You will feel cold. That is what you don't want, right? You want a good temperature, not too cold, not too hot. But how will the AC know that I have to stop here? So if I keep on setting the cool air, that particular system is this, right? So there is a controller, remote control, through which you send the direction that, okay, control it to 25 degree. So AC, what it does, AC controller sends the signal that, okay, send cool air. System does something, right? In the background, it has some many components, and ultimately the output is cool air. That is the output of the system. But there is a problem with this system, right? Output doesn't know what is happening to the input. What is the input? Input is you telling the AC to go to 25 degrees. But there needs to be a reference which the output can be compared to. So output is my output temperature. Currently output temperature is 30 degree. So AC needs to reduce the temperature by 5 degrees. Now we are getting somewhere. AC has got a number. I have to reduce by 5 degrees. So slowly, so AC understands I have to reduce. So I have to send cool air. If I have to increase, so I would have sent hot air. So as I have to reduce, so I will send cool air, and the temperature got decreased to 28 degrees. Now AC will again compare the input. Basically input is the 25 degree because I want my temperature to be 25 degree, and the output. Currently it is 28 degrees, but I want it to 25 degrees. So again, I have a delta of 3 degrees. So I will keep on sending the cool air. There will be a certain point where my input is 25 degree and output is also 25 degree. So there is no delta, no error. So AC will stop sending the cool air. So that's why if you have seen AC, you will see it is not always running. It sometimes stops in between. Why? Because it is measuring the temperature. As soon as it reaches the desired temperature, it stops for certain few minutes, and then again what happens, as it stops, it is not sending cool air, and the atmosphere around the room is obviously hot. Outside the room it is hot. So slowly what happens, slowly the temperature increases to 26 degrees. Again the AC sees, okay, my output has become 26 degrees, but I am supposed to give 25 degrees. So again there is a delta of 1, so it will again reduce it to 25. Again the AC will turn on and it will send cool air. So that's how AC saves electricity. AC does not always continuously send cool air, otherwise there will be huge loss of electricity. That is the beauty. So that is actually called as feedback. So we use negative feedback. So there is some kind of sensor which uses feedback to measure the temperature and send the data to the controller, and of course controller decides whether I have to send cool air or hot air. So these are all the things. I will not go through too much of things, like, yeah, basic idea I have given you. So this is the basic block diagram of control system. So we love negative feedback, right? Why negative? Because I am measuring the error. So this R of S minus, sorry, this R of T minus this C of T, right? Output is called as the C of S. In time domain it is called C of T. This is called as the error function. So we want our error function to be 0. What was my input? 25 degree. What was my output? 30 degree. So I want it to be 0, right? Then only I will reach my desired temperature. When my output is exactly equals to my input, I will reach my desired temperature. So that is what this my error function is. Of course, don't go by the units, don't worry. Just I'm giving an example. Units can change. Unit of error function will change. Okay, that is the thing. Now how do I find out the, so if I have a simple block like this, what is the transfer function? X of S upon Y of S. This is my transfer function, correct? So if this is my transfer function, sorry, this is my block diagram. This is also called as the block diagram basically. So y of s upon x of s would be my transfer function ratio of input upon output upon input, that is g of s. Okay, basically, right, what does this block mean? This block means, what is the signal here, x of s, just multiply by the signal with the gain of this block, and that will be the output. So this output would be simply x of s into g of s, that's it. So this node is what, y of s. So y of s is equals to x of s into g of s. Y of s is equals to x of s into g of s. That's all. So yeah, that is the thing over here. Now what about this case? So let us derive. So this is my transfer function. What is the transfer function here? C of s upon y of s. Very C of s upon r of s. Input upon output. So again, you write here, what is C of s? C of s is this node, right? So what will be the output here? This output would be C of s into h of s. That is my output, and that is fed to this point, correct? So this point is r of s. Now this, right, is called as a adder or subtractor. In this case it is subtractor. So here this r of s signal will be added, and this particular signal, whatever is at this node, this will be subtracted. So this point will be r of s minus c of s. That is what my so not c of s, sorry, c of s into h of s, because the signal at this particular node is c of s into h of s. That is the signal here, and if I multiply by this gain with this signal, I will get my c of s. So c of s is equals to g of s into this particular signal, and if you solve this, right, solve for c of s by r of s, you will get this value. Pretty interesting. You will get g of s upon 1 plus g of s into h of s. Now this should be your bread and butter, right? Remember it, because everywhere else you will use it. Everywhere in control system you will use it. So remember it. Now this is called as negative feedback, because I am subtracting the output. There is a thing called as positive feedback. Like negative means it tries to keep the output and the input to the same level, right? Positive means it increases the output. Whatever is the difference, it will increase the output. So positive, that's why positive, I'm increasing, right? So in real life, positivity is good, but in control systems, sometimes positivity is not great, because positive feedback systems mostly reduce the stability, because it further increases the output, right? Further enhances the output. So maybe there will be a bit of, like, output can go unbounded. That is the problem with positive feedback. Similarly, if you derive the formula for positive feedback, this will be a transfer function. So you will say, we will use negative feedback only. No, sometimes we use positive feedbacks as well. For oscillators, Smith triggers. Why oscillators? Because in oscillators, right, my output, if you see, is always, like, I tell it to go to some frequency, right, and output is oscillatory in nature. So it always requires some energy input, right? It always requires some energy input. So yeah, that is why we provide all this. So yeah, these things will be there. So oscillators and Smith triggers, positive feedback systems are used, and some place, other places as well it is used. So you can see, like, you can go through this point. I will not go through all these points. You can go through these points, pause the video, and understand the difference between positive feedback and negative feedback. So yeah, I was discussing about this open loop transfer function, closed loop transfer function. So open loop transfer function is just a terminology to represent this, that I have this feedback. What if I just slowly remove this? Then what is the output that I'm getting here, right? And that ratio of this output upon input is called as the open loop transfer function. Basically, it is the product of the forward path gain. So this is actually called as the forward path gain, and this is called as the feedback factor. How much feedback I'm amplifying, basically taking the feedback. So this product of the forward path gain and the feedback factor is called as the OLTF, open loop transfer function. So again, if you derive the OLTF, it is simply the product of G of s into H of s. So you can actually write your actual transfer function in terms of OLTF. Okay. So yeah, I think how. So your actual transfer function, right? CLTF, closed loop transfer function. That is your actual transfer function. It is equals to G of s upon 1 plus G of s. Now what happens? Mostly people remember this. They write this as equals to OLTF upon 1 plus OLTF. And I know you have also remember it, right? In your semester examination. But this is only valid in the case when your H of s is 1. If your H of s is 1, that is unity negative feedback system, and that is the like 90% of the cases, your H of s will be 1. We will solve it for unity negative feedback 90% of the cases. So in those kind of cases, what happens? Your OLTF is what? Your OLTF is simply G of s. So this all, your CLTF is what? G of s upon 1 plus G of s, and your OLTF is also G of s. So it is actually OLTF by 1 plus OLTF. So that is the thing here. Okay, we have understood this particular thing. So that is the thing over here, right? Yeah. Yep. So yeah, that's all. So that's why you see that CLTF is equals to OLTF plus 1 plus OLTF, but this is only valid when H of s is 1. So don't remember this. Remember this thing and this thing. These two things you remember, and you can always get back to this. 90% of the cases this will be valid, 90% of the cases, but sometimes it will not be valid. So you will be in a pickle. So don't mug up these things. So let's solve the let's understand another thing, that is DC gain. What is DC gain? So DC gain of the OLTF for the following CLTF. So if I have, so DC gain is nothing but the gain of any transfer function in Laplace domain at s equal to 0. So if you put s equal to 0, whatever the value that you get is DC gain. So let me explain this with example. Let's say I have this G of s, right? G of s that is 10 upon s square plus 1. What is the DC gain of G of s? Just put s equal to 0. That is 10, right? If I had, let's say, 100 upon s plus 2, what is the DC gain? Put s equal to 0. 100 by 2, that is 50. That's it. DC gain is also, basically DC means like I'm providing DC input, no frequency. Frequency is 0. That means omega is 0. That means s is also 0. That's all. Okay, that's how we say it, because in frequency domain s equal to j omega. This is also one more thing that you have to remember. In frequency domain, Laplace domain s is complex frequency, but in frequency domain s equal to j omega. This also we'll use sometimes. Okay, so that is the thing. So yeah, now if I have, so DC gain of G of s is 10 upon s square plus 1, but let's say they have given you a closed loop transfer function, but they're asking what is the DC gain of OLTF. So you have to find out OLTF. Now first of all, they have not told you whether this is a unity feedback or not, right? Because if I say what is my transfer function, they have not even mentioned whether it is a negative feedback or a positive feedback. Like there are two kinds of feedback, positive feedback and negative feedback. They also have not mentioned, like if H of s is 1, it is called as unity negative feedback. Otherwise it is simply called as negative feedback, and the gain can be something else, some non-unity value. It is called as non-unity negative feedback. Non-unity negative feedback meaning your H of s is not 1, it is something else. It is not 1, it is something else. Now by default, in the question, in control system, if nothing is mentioned, you will always assume unity gain negative feedback. If nothing is mentioned, always assume unity gain negative feedback. Always assume this. Now, if I assume unity gain negative feedback, then your transfer function is OLTF upon 1 plus OLTF. Otherwise, I would not be able to calculate my OLTF. Not possible, because the numerator is G of S. And if it is not in non-unity feedback, you will not be able to calculate it. But here I will be able to calculate. So you can use this basic trick, bit of component or dividendo, okay, and you will see that you are getting your OLTF to be this. You can use bit of trickery, and this will be your OLTF. (50 upon s square plus 20s plus 350). Now if I put s equal to 0, what will happen? S equal to 0, if I put, this will be basically equals to 50 upon 350. So the DC gain of OLTF is actually 1 by 7. What about the DC gain of CLTF? DC gain of CLTF, I'll just put s equal to 0 here. This will be 50 upon 400. That will be 1 by 8. That's how you calculate the DC gain. Now there can be bit of confusions. DC gain is also called as the steady state value, steady state gain. Steady state meaning at t equals to infinity, right? That will be the value of my output. That's why it is called DC. Okay, don't worry about it, just understand steady state. Now the thing is, if I say I have a transfer function t of s equals to 100 upon s into s plus 4, right? What will be the DC gain? So I have seen many students do this. What they'll do? Okay, if I put s equal to 0, right, this is going to infinity. What is the problem term? The problem term is this one. So what I will do? The DC gain I will write s into 100 upon s by s plus 4, and I will make limit as s tends to 0, and this will be my DC gain basically. They will say DC gain would be 100 by 4. S is gone. S is not the problem. So this will be 25. So they will say 25 is my DC gain. Okay, 25 is my DC gain. So 25 is my DC gain, and you will be wrong because it does not have a valid DC gain. You cannot put s equal to 0 here, right? It will go to infinity. So it is not settling basically, right? So yeah, so simply you cannot find the DC gain. DC gain does not exist. And I know in GATE someday they will ask a question from this, right? So just be careful. Just be careful. Now one more thing is there. Let's say I have this block diagram. Do I need to use here OLTF? No. OLTF is just a term. That's it. OLTF is just a term. So what is the OLTF in this case? No, OLTF is just a term. I don't know what is the OLTF. OLTF is used for closed loop system only. The term OLTF will be used for closed loop system only. So here I can say, definitely say, what is the OLTF? G of s into h of s. H of s is 1, so it is g of s. But here what is my OLTF? I don't know, because it is a open loop system. So we don't talk about OLTF, open loop transfer function, in open loop system. No, we talk about OLTF in closed loop transfer function. Okay. So now let's discuss about one more thing known as sensitivity. So basically sensitivity in intuitive terms, actually layman terms, it means how much I am able to sense my output, right? If my sensitivity is very high, that means that for not output, sorry, for huge changes in input, right, output will also change very fast. So basically if you see the formula of sensitivity, it is change in A upon change in B. How much will A change if B is also changing? If this value is very high, A will change very high. So basically I can write that my change in A or delta A equals to sensitivity into delta B. So if sensitivity is low, let's say some low value 0.1 or something, then even if there is say delta B of 100, change in B is 100, change in A will be only 10. But if sensitivity is let's say 10, So if there is a delta B of 100, then change in A would be 1000. So that is the only difference that sensitivity tells us. So it tells me how much will my output, like, of course I'm just telling you for intuition, but you can find out the sensitivity for any two parameters. How much will A change with respect to B? So it has a formula, that is del A upon, so change in A is represented by this. Basically, actually it is represented by this delta A upon A, but this delta A can also be written as del A upon A. Why we write it like this, I will explain. Similarly, change in B will be represented like this. This can be further modified like this. This will be delta A upon del B into B upon A. Okay, B upon A. So that is the thing basically. So yeah, we will solve for a few cases. Let's say I have this transfer function. Okay, sometimes we write this gs as g upon 1 plus gs just for our convenience. We write transfer function as a function of g and h. Now I want to find out how much will my transfer function change with change in OLTF. No, not OLTF, sorry, yes, with change in, not OLTF, with change in g. And how much will my transfer function change with change in h? This is a very, very important thing. I want my transfer function to be stable. So if I see that, if I find out the sensitivity, right, what will be the formula? Formula would be, for the first case, delta t upon t, change in transfer function, upon delta g upon g. So this will be equals to delta t upon del g. So this will be delta t upon del g into g upon t. So what is delta t upon del g? So delta t upon del g would be, this would be differentiation of this particular function with respect to g. This will be 1 plus gh whole square. Remember, we are doing partial differentiation. This will be 1 into 1 plus gh minus g into h. This will be, gh will be cancelled. So this will be 1 by 1 plus gh whole square. And let us compute this value. So similarly, if you compute this value, I think there is a solution here. Yeah. So you can directly see, hold on a second, this should be okay. Don't you just do this, this is the differentiation value, right? Don't forget g by t is also there. Okay, don't forget it. So n2 will have to multiply this by, this is the differentiation value, we have to multiply this g by t. What is t? T is g upon 1 plus gh, g upon 1 plus gh. So 1 gh will be cancelled, gg will be cancelled, ultimately it will be 1 by 1 plus gh. Similarly, if you solve it for this one, you will get this result. So this one will be always higher than this one. So basically my transfer function of the system is hugely sensitive to the feedback gain. This is called as the feedback gain. Just give me 1 second. Yeah, feedback gain. It is hugely sensitive to the feedback gain. Whatever is the feedback gain, it is hugely sensitive. So we have to be very careful. That's why mostly we keep this unity 1. We don't change it. Mainly what we do, we change the forward path gain. This is called as a forward path gain. So we don't touch the feedback. If I touch the feedback, it is hugely sensitive. The overall transfer function is hugely sensitive to feedback gain. So I don't change the feedback gain. That is the sole reason why we keep it unity, because unity is the easiest way, right? Unity, like, it is very simple, just connect a wire. That's why mostly in undergraduate we study unity negative feedback systems. If you have finally understood why we use unity negative feedback systems, put a like and comment in the video. Of course, hype the video, new feature. So yeah, these are the things. I hope you've understood. Yeah, I am extremely sorry. Like, I was here only, I was telling you about negative feedback, then for some reason the recording got stopped, like the screen recording of my tablet got stopped. Basically here I was like, let's say if I want to find out the sensitivity of this, right? I was explaining this thing only. So if I want to calculate the sensitivity, what will be the sensitivity? It will be simply 1. Why? Because what is my transfer function? Transfer function would be c by r. So here I have this block g. So r into g would be c. So c by r would be g. So if you calculate the sensitivity, you will see it is to be 1, and it makes sense as well physically. Why? Because my transfer function is g only. So whatever will be there, whatever changes will be there in g, the same changes will be reflected in t. So that's why sensitivity is 1. So similarly, let's solve for this case. We have been given that this ratio is plus minus 15%. What will be del t upon t? I remember this by this is actually my sensitivity of transfer function with respect to g. Correct? So this is my del t upon t by del g upon g. So somehow if I am able to calculate sensitivity, and I already know del g upon g, so I will be able to calculate del t upon t. So let us calculate sensitivity. What is it? It is del t upon del g. Now in actual examination, you will actually calculate this value, because although we have derived this formula, but I will not tell you to remember this formula. No need to remember it. Calculate it. Okay. But here, as we have already calculated, so I will use it directly. So this will be sensitivity will be actually 1 by 1 plus gh. Now what is g? G is 50. Okay, sorry. Sorry. We don't even have feedback, right? What I'm doing. That's why you don't remember the formula. Sorry. Yeah. So basically, what is my transfer function here? It is simply g, right? Transfer function is simply g. C by r is g. So it is very simple. Sensitivity for this case is simply 1, right? Sensitivity is 1. So if sensitivity is 1, correct? So yeah. So my del t upon t would be simply also plus minus 15 percent. Yeah. Yes. Sensitivity will also be plus minus 15%. Huh? What if I had a feedback here? Then the sensitivity will change. You will see it is much smaller. Like, what is the problem? I hope you can see the problem. What is the problem? If I have an open loop system, and if there is some change in the open loop gain due to some disturbance, because there will always be some errors, external noise. If there is some change in the open loop gain, the transfer function will also change by a large amount, and that will change my output by a large amount. But if I put a feedback, then even if there is huge change in the open loop gain, the change in the whole transfer function of the system will be very small. I can show you. So basically the output will change very small. So what will be your sensitivity in a closed loop system for a negative feedback? It will be 1 by 1 plus gh, right? This we have derived. This is equals to del t upon del g upon g. So here, what is this value? 1 by 1 plus gh. G is 50, h is 5. So 1 by 1 plus 250 equals to del t upon t into del g upon g, that is 15%, right? So like this will be very small in percentage. If I calculate this value 15 upon 251, this will be very small. Del t upon t would be 0.06 percentage plus minus, right? So as you can see, like even if there is huge changes in the open loop gain, this del g upon g represents the change in the open loop gain, but the change in the overall transfer function is very small. So overall my output will not change much. Basically, if there is sudden disturbance due to external noise, the output will not change by a large amount. That is the only thing, right? That is the advantage of feedback. That is also another reason why we add feedback. I hope you can understand this as well. In open loop system, the sensitivity will be highest, that is 1. So we don't prefer open loop system. One reason is to obviously find out the reference signal, error signal, and reduce the error. Another reason to add feedback is sensitivity. So in interview, if you say this, right, your interviewer will be very impressed, because most of the people will say yes, it reduces the error. That is true. That is important. But this is also another reason. We want to reduce the sensitivity of my transfer function with respect to the forward path gain. Now there is one thing, if you calculate the same thing, your homework is to calculate the same thing with the closed loop, like with a feedback gain. So you calculate the sensitivity with respect to h, right? You will see this will come out to be high, right? We have already calculated this value. This is supposed to be coming out to be your minus of gh upon 1 plus gh. So this value is actually higher. So you must not vary this h. So basically you have to, your feedback systems will be very costly, because this gain should not vary. If this gain varies, that means your whole transfer function will also be varying. That means your output will also be varying. So you have to put a very costly system here, so that this gain does not change even if there is some external disturbance. That's why you will see the feedback system will be very costly. In most cases, the feedback system will be the most costliest part of a whole machinery. So this point is should be also very clear. So I think I have solved the same thing here. If you see, if I find out this will be roughly equals to 1. Change in the transfer function with respect to h will be minus 1. Minus or plus does not matter. Ultimately, like plus minus, there is plus minus 15%, right? You're multiplying plus minus 15 with minus, so does not matter. So your change in transfer function with respect to h will be plus minus 15%. Okay, if your age varies, 15 plus minus 15%, the change in transfer function will be very high. If your g varies plus minus 15%, your change in transfer function will be very small. So you have to be very careful. So there, of course, there will be some drawback. You cannot gain everything. So there will be some drawback. This is drawback. So we have to choose a very high tech system, so that the feedback gain does not vary. So these are the things basically. I hope you have these points are clear by you. So there are a few key points. You can see, go through the pause the video, go through the key points. I will just repeat the same thing, so it's better for you to go through it. Yeah. So sensitivity, you can find out the sensitivity. I will not solve much questions. You can solve these questions. You can find out, like pause the video, find C. First of all, you have to find C by R. So what is C by R? C by R, if you want to find without the change, you just find C by R transfer function without the change. So they have given you this gain, without the change you find C by R. What will be it? So simply it will be G upon 1 plus GH, right? 100 upon 1 plus GH, that is 100, 4 by 100 into 100, that is 4. So it is 20. So your transfer function will come out to be 20, and then you can of course calculate the sensitivity, right? Very simple. Sensitivity is 1 by 5. So if there is a variation of 5%, so your transfer function will change by 1%, right? So if your initial value, actual value, ideal value was 20, so it will change from 20 to plus minus 1%. What is 1% of 20? You can calculate 0.2. So that's it. So basically your transfer function will change 20 plus minus 0.2. I hope this point is clear. So that is what this percentage means basically. Percentage meaning from its base value. Here also plus minus 5 meaning from its base value. So it can go plus minus 5, because 5% of 100 is 5 only, right? These are the things basically. So concept of poles and zero I have already explained when we get it. So zero we represent by a circle, poles we represent by a cross. That is our notation, and that is everywhere. That notation is constant everywhere. Okay, so we think we have discussed about few things. We have discussed about right hand poles, all those things we have discussed. Pole determine the stability, all those things. These things already we have discussed. Unstable system already we have discussed. Okay. So yeah, poles lying on the imaginary axis, we will get a sinusoidal. This is a marginally stable, because although it is bounded between certain ranges, but it is not settling to a constant value. That is the problem. This is stable system, because you will see you will get a damped sinusoidal if you find out the Laplace inverse of this, right? If the poles are there. Unstable system already we have discussed. This will be unbounded sinusoidal, like this will keep on increasing. So yeah, these things already we have discussed. So I don't think repeated poles also we have discussed what will happen. These things are discussed. Yeah, now let's come to time constant. So time constant, basic definition of time constant is basically reciprocal of magnitude of negative real root for a stable system. Time constant is only defined for a stable system. It is not defined for a unstable system. What do I mean by stable? I hope you know what is stable system. So all the poles that lie on the left hand side, for those only time constant is defined. So let's say I have two poles that is lying here, here and here. So if I have two poles that is lying here and here, and let's say the location of this pole is minus 2 plus j, and location of this pole is minus 2 minus j. So what will be the time constant? time constant would be basically negative inverse of the real part, magnitude of negative inverse of the real part. So magnitude of negative inverse, magnitude of this is what, 2, and take the inverse of the real part. Remember, it is the real part, right? Magnitude of negative inverse of the real part. So what is the real part? Minus 2. I will take the magnitude of this and I will take the inverse of this. So time constant for this particular system, okay, will be 0.5 seconds. Now physical significance of time constant is something else. Basically, this you already have studied in network theory, that if I have, let's say, a RC circuit like this and I am providing it, let's say, is 1 volt, right, at t equal to 0. I am closing the switch. So of course, what will happen is that if I plot the VO, this will be 1 volt. So what time it will be 1 volt? Approximately. Of course, it will never settle, it will take infinite time, but approximately at 4 tau we say it settles. So here the tau is actually called as time constant, where we say like basic definition that 63.2%, but no need to remember all those things, just understand this time constant, and for this case time constant is RC. So basically if you write the transfer function in Laplace domain, what you will see, this will be 1 upon 1 plus SRC. This is like a low pass filter, correct? Low pass filter. So what if I draw it in the pole 0 diagram? I have a pole at minus 1 by RC. So what is the time constant? Time constant is RC, right? We already know. So time constant is negative inverse of this, right? Negative 1 by RC, inverse RC. So these things match. So that is the simple definition. Let's say that's it. Don't use any extra brain. That is it. Now let's say if I have another pole, let's say minus 4 here. So this system will have two time constants. One will be 0.5, another one will be 1 by 4, that is 0.25. Correct? That will be 0.25. That's it. Right? 0.5 and 0.25. Yeah, that's about the time constant. Basically, it is the term that comes with the exponential. Right? Here, if I have 4 here, it will be the negative inverse of this, right? That is my term. So these are the things about time constant. I hope I don't need to explain, but time constant only exists for stable system. For this kind of system, time constant does not exist because the pole is lying on the right hand side. So time constant will definitely not exist. Just be careful regarding this. So this is a normal transfer function with a time constant format. So here if I write S tau, so negative inverse of tau will represent the pole location. Okay, negative inverse of tau will represent the pole location. Just like here, if you see, I had 1 by 1 plus SRC. So this was 1 by 1 plus S tau, correct? So negative inverse of tau was representing the pole location, right? Negative inverse of tau was representing the pole location. So that is about the time constant. Okay, now time constant, what it says, it basically time constant is directly proportional to the settling time, because settling time is equals to 4 into time constant. So higher the time constant, higher time it will take to settle. So higher the time constant, lower the speed. So if I want to have higher speed, my settling time must be lower. It will be inversely proportional. So basically my speed is inversely proportional to time constant. Again, a very important relation. So if I want my system to respond to changes faster, I need my time constant to be smaller, because it will take less time to settle. So it will respond much faster, right? So you can plot the graphs, you can see like which system is much faster. So C reaches its steady state much faster, then B reaches, then A. So C will have the lowest time constant. then B, and then C. So these are the things basically, effect of feedback. So one more thing is there, is feedback. Feedback of course gives us that error signal, right? We can get to our reference. Feedback improves the sensitivity with respect to the forward path gain. Always remember, with respect to the forward path gain. Also feedback improves the stability of the system. So what happens basically, if let's say I initially had a pole on S plus 2 and S minus 2, basically right hand pole, if I add, this is the open loop gain, right? Let's assume that open loop system, and G is equals to 1 by S minus, let's say S minus S minus 2, okay, or S minus 0.5 or S minus 0.5, let me add S minus 0.5. Now if I add a feedback, the transfer function is same as G only for open loop system. If I add a negative unity feedback, what will happen? If I add a negative unity feedback, this will be G upon 1 plus GH. So this will be G upon 1 plus G only, S minus 0.5. So this will be actually 1 by S plus 0.5. So it shifts the pole, makes the pole on the left hand side. So actually it can make the system stable. Even though previously my system was unstable, it made it stable. So it improves the stability, but there are few drawbacks. If let's say already my system was stable, and if let's say I add any feedback, here I added a feedback with 5, so your transfer function will become this. So if you find out the time constant, your time constant actually, okay, it makes it even better. Time constant is 1 by 7. So time constant, previously what was the previous time constant? Previous time constant was, if you see it as 1 by 2. So time constant has reduced, so your speed will improve, okay, and your bandwidth also will increase. So okay, I think there are few drawbacks. These are not the things, but yeah, adding feedback will improve the speed of the system because it is pushing the pole further towards left. So if it is pushing the pole further towards left, this negative value is increasing. So inverse of this will decrease, which will reduce the time constant. Hence, speed will increase. So these are the things basically. So negative feedback, these are the effects of negative feedback. Okay, improves stability, all these things are there. If I add positive feedback, it will shift the pole on the right hand side. Okay, pole shifts on the right hand side, it will make it more unstable. So that's why we don't use positive feedback in control systems, but in analog electronics sometimes we use it, oscillators, for our own purpose. Okay, it depends on purpose. Mostly in control system we will not use positive feedback. Now initial value theorem, you learn more about initial value theorem in signals system, but for control system only this much is enough. If I want to find out the initial value of a initial value of any signal, what I can do is the value at 0 plus will be simply equal to limit as s tending to infinity s into x of s. So similarly, let me take an example. Let's say I have this example, right? My x of s is this. What will be the initial value of this particular function in the time domain at t equal to 0? In the time domain, the initial value would be, I can take the inverse Laplace, that will be 100 e raised to power minus 40, and at t equal to 0 the value is simply 100. But I can use this formula as well, right? S into x of s, limit as s tend to infinity. So if I solve this limit, it will be 100. So both are coming out to be same. So hence this is the initial value theorem. Will be helpful in a lot of places, as I have shown you in sinusoids as well. We can take this property to remember the formula of sinusoid and cosinusoid for Laplace transform. Now the thing is, here remember, initial value theorem is only applicable for causal signals. Okay, it is not applicable for non-causal signals. Just be careful. It is applicable for unstable signals as well. So even if my signal is unstable, let's say 100 upon s minus 4, initial value theorem is applicable because there is no problem here, right? Even though the signal is unbounded, I don't care about the value at t equal to infinity. I only care about the value at t equal to 0, which is 100. So no problems. So it will be valid here. Okay. For marginally stable systems also it will be valid. It will always be valid. Okay. It is valid for stable as well as unstable systems, but it is not valid for non-causal systems. Basically, and in control system we are discussing about causal system only, so you don't have to worry. In signals, this relation will be modified, this property will be modified. So in signals you can learn about that. Final value theorem is the most important one. Please don't mess this up. So it is similar to initial value only. Let's say if I want to find the final value of any waveform, so what do I have to do? I simply have to write as x t tending to infinity, x of t, x of infinity will be equals to limit as s tends to 0 s x of s. It is simply the desecant, but not exactly the desecant. I have to multiply a s with it. So what is the initial value here? If I multiply s into 100 upon s plus, sorry, not the initial value, final value, it will be 0, right? If I put s equal to 0, it will be 0, which makes sense because it is exponential and it is settling to 0. Now, for this kind of system, what is the final value? It is infinity, right? Even if you use the final value theorem, you will get 0, but actually it is settling. Is it settling to 0? No, it is settling to something unbounded. So that is a problem. That is a problem basically, right? So these are the things basically that you have to understand here. So for marginally stable systems as well, your final value will not be applicable because final value is not like, you don't have any final value here, right? Doesn't have a final value. So final value theorem is only applicable for absolutely stable system. It is not applicable for unstable or marginally stable system. Okay. Consider a transfer function which is given, whose S plane is given here, pole diagram is given, and a desecant of 100. Roots of the characteristics equation. What are the roots? So basically, right, transfer function will have a numerator of s upon denominator of s. The roots of the characteristics equation. So the characteristics equation is called as the, whenever I make the denominator equal to 0, this equation is called as my characteristics equation. Okay, very important, it will be used everywhere. And the roots of this are called roots of characteristic equation. Also, these are called as the poles of my system. So basically, roots of this will be poles of my system, that is -4 and -1. These are the roots of my characteristics equation. Frequency of oscillation. So frequency of oscillation represents the frequency, like if there is some value of the system where basically when the poles lie on the j omega axis. Like, so are any of my poles lying on the j omega axis? No. So there are no complex conjugate poles. So whenever you will have some complex conjugate poles, you will say, let's say I had a pole here at -2 plus j, -2 minus j. So then you will say the frequency of oscillation will be 1 radian per second. But there are no complex, so the imaginary part of the pole will always be the frequency of oscillation, but there are no imaginary parts. So you will say no, system will not oscillate. So there is no frequency of oscillation. Because why it happens? So if we see in this case, right, this was the there was a plot here, damped sinusoid. Yeah, this one. So here, right, if you plot, yeah, I'm getting a complex conjugate poles. So here, of course, it has some frequency of oscillation, right? It has some frequency of it is oscillating, although the amplitude is reducing, but it is oscillating. So the frequency of oscillation is defined by the imaginary part, and this real part is defined by the time constant. If you see negative inverse time constant, right, and this 2 is represented by the imaginary part of the pole. So now I hope it is clear that what do I mean by frequency of oscillation. I hope that part is clear to you. Does it have any frequency of oscillation? No, it does not have any frequency of oscillation. No frequency of oscillation. Initial value of the transfer function. So initial value, we can use the initial value theorem. So if I write the time constant format, how can I write the time constant format? So I will have, do I have any zeros? No. So the numerator will be simply 1. I don't have any zeros. Numerator will be simply 1. I have a pole at s equal to -1. So what you do is you write s by 1 plus 1. This is the time constant format. So you write the pole in the bottom. Okay. And again I will write s by 4, the pole at the bottom, magnitude of the pole. plus 1. Okay, what it will do is, if we put, like, when does this equation go to 0? At s equal to -1 and at s equal to -4. Exactly, that is what we are expecting. Correct? Okay, and a DC gain of 100. Okay, that is interesting. How can it have a DC gain of 100? It can, okay, it can have a DC gain of 100. Yeah. So now DC gain, what does DC gain means? DC gain basically means whenever I put s equal to 0, the value of the transfer function, right? So if I put s equal to 0, the value of the transfer function currently is 1, but it should be 100. That is what is told in the question. So that's why it will be 100 by s by 1 plus 1, s by 4 plus 1. Like, why do I write it like this? Because it is very easy to form the transfer function. Yeah, I know you know like this. So you will say, okay, my transfer function, I have a pole at s equal to 1, so I will write s plus 1. I have a pole at s equal to 4, I will write s plus 4. Now here, right, the calculation of the DC gain would be very difficult. So here if I write k, I know at s equal to 0, the value of my transfer function is 100. So it will be k by 4 equals to 100. So from here my k comes out to be 400, which is very confusing. So if I want to write the transfer function, right, so this is also another way to write. And this is totally valid, no problem with this, because ultimately, right, if you multiply by 4 on both sides, you will get back to this value only. But better way is to write this, because this will give me more information. Exactly, it tells me where are the location of poles, and exactly it tells me what is the DC gain. Here 400 will not give me any information. Correct? That is why this is called as the time constant format. Now, what if the pole was lying on the right hand side? Then you will just put a negative sign, that's all. Let's say this was plus 1, right? You will just put a negative sign, that's all. So we'll get a pole at the right hand side. Okay, just I'm giving you examples. Don't, like, this is not the answer, I'm just giving you examples. I hope that part is clear. So that's how you form the transfer function. Here these are the transfer function. Now what is the initial value? So for initial value, what do I have to do? I simply have to multiply this transfer function with s and put s equal to infinity. So if I put s equal to infinity, this will go to 0, right? Only taking the higher order terms, this will go to 0. So initial value is 0. What is the final value? Final value will be s into g of s into transfer function. If I put s equal to 0, if I put s equal to 0, this also goes to 0. Correct? Hold on a second. Infinity, yes, this also goes to 0. Yes, time domain expression, it's very simple, right? So the expression is 100 upon s plus 1, s by 4 plus 1. So I can use partial fractions. So s equal to -1. I hope you can break it down into partial fractions. Minus 3 by 4. -1 3 by 4 -1 by 4. Hold on a second. S equal to s equal to -4. If I put, this will be minus 100 by 3. Okay, yeah. So if I take the Laplace inverse, this will be 400 by 3 e raised to power minus t minus 100 by 3 into e raised to power minus 40. Correct? If I am not correct, s plus a, sorry. Hold on a second. No, this will be, so the formula was 1 by s plus a was equals to e raised to power minus 80. Correct? So let me put it down into our standard formula. So if I put it down into standard formula, so I have to multiply by 4 on both sides. So this will be s plus 4 and this will be 400. Yes. So this will be 400 by 3 e raised to power minus 2t. Sorry, not 2t, 40. Okay, like you can do this basic things, I will not do it. Okay, You can do these basic things. Yeah. So your ultimately time domain expression is 400 by 3. I can take common, e raised to power minus t minus e raised to power minus 40. Now if you put t equal to 0, you are seeing that yes, it is going to 0. If I put t equals to infinity, then also it is going to 0. So our final value theorem and initial value theorem both are valid. System is stable. Okay, these are the things basically. I hope you understood this part. So you can calculate, get the final expression. So there is one last thing about the dominant pole. What do I mean by dominant pole? So let us try to understand this transfer function. So I have two poles at s equal to minus 2 and s equal to minus 12. Now if I take the Laplace inverse, you can do it, take the Laplace inverse, not that difficult. In time domain, you will see this one, y1 and y2. If I plot these two functions, you will see this one dies down much faster. Why? Because its time constant is much lower, so its speed will be much faster. So you see this one will die down much faster. Y1 will die down, sorry, hold on a second. This time constant will be much smaller. Oh, sorry, what I'm saying. So what is the time constant here? 1 by 2. What is the time constant here? 1 by 12. So this, right, dies down much faster. This will die down much faster. This will die down to a bit slower. Okay. And if I add these two transfer functions, what will happen is that you will see that overall, if I add these two, right, basically I am representing this as y1, y2. Ultimately, my final solution is y1 minus y2. So what is happening is this y2 is contributing to very little, right? Because for most of the period, it is 0. Approximately for this whole period, it is approximately 0. So my x of t is equals to approximately y1 only, right? y1 only. So approximately the response is dominated by y1. So the response is dominated by the pole that is more nearer to the origin. That's why it is called as the dominant pole. Out of these two poles, the response will be mostly dominated by the pole that is more nearer to the origin. So we can ignore this pole. Roughly I can say, I can simply ignore. Roughly I can simplify my calculation. What I will do is I will write x of s roughly equals to some DC gain k value. I will come to that, s plus 2. I can approximate it. So my response will be e raised to power minus 2t into k. It's very easy to calculate the Laplace inverse of this. It will take us some time. Look, for now there is only one pole. What if there were three poles? S plus 100. So finding out the Laplace inverse, it will not be difficult, but it will be time consuming. So we can take few approximations. This is only used to take bit of approximation. Okay, so we can simply ignore. So significant pole is referred to as dominant pole. Dominant pole exists near the origin in the left hand side of the S-plane. So of course, again, your system must be stable, then only we can discuss about dominant pole. Otherwise, don't discuss about dominant pole. First of all, your system must be stable. Time response due to significant pole is slower than the insignificant pole. So we can neglect the insignificant pole of the transfer function. So till what ratio can I neglect? So there is no standard value, but generally what we follow is this 4. So if my insignificant pole by significant pole, the ratio is more than 4, I can simply neglect the insignificant pole. So in this case, what is the ratio? 12 upon 2, which is 6, which is greater than 4. So I can neglect the insignificant pole. But make sure once you apply the approximation, the DC gain should remain same. You should not change the other properties of the transfer function. All I considered here was the speed. Why DC gain should be same? Because DC gain represents the steady state value, and the steady state value of the transfer function shall not change. So here the DC gain must remain same. So what is the DC gain here? S equal to 0, the gain is 120 by 2 into 12. So it is basically 5. So DC gain here also should be 5. Currently, if I put S equal to 0, the DC gain would be simply 60, which is wrong, right? So I have to do one thing. I have to write k upon s plus 2, s plus 2. So if I put S equal to 0, I should get 5. So k will be equals to 10. So actually this will be your dominant pole approximation. So I think the same thing I have written over here. This is not the exact transfer function. Your dominant pole approximation would be 10 upon s plus 2, not the exact transfer function. Just we're concerned about the speed, that's it. Because here, if I apply the initial value theorem, right? Okay, if I apply the initial value theorem in both cases, s equal to, no, initial value theorem if I apply here, right, it is going to 10, correct? Sorry, not 10 upon 5, that is 5. S tending to infinity, sorry, it is going to 10 only. 10 only. Here if I apply the initial value theorem, it is going to 120, it is going to 0. So although the initial values are not same, right? So we are not concerned about the initial value. We are concerned about the final value. Final value must match, right? In both cases, final value is 0, right? And the DC gain must match. Basically, the gain at DC frequency must match. So these two things you have to be careful. So consider a transfer function like this, right? So if I locate the pole locations, so I have a pole at s equal to minus 10, and I have two poles at s equals to minus 1 plus minus j. Okay, I have two poles at s equal to minus 1 plus minus j. So yeah, now yeah, so if I see, compare the real parts. Okay, compare the real parts. So I have a pole at s equal to minus 10 and I have a complex conjugate poles at minus 1 plus j and minus 1 minus j. So if I compare the real parts, right, the real part here is minus 1 minus 10. So the ratio is greater than 4. So I can take help of dominant pole approximation. So I can neglect this particular pole. I can neglect it, right? So if I neglect this particular pole, approximately it will be k upon s square plus 2s plus 2. This will be my modified transfer function. But the DC gain must remain same. What is the DC gain here? DC gain is at s equal to 0, it is k upon 2, and here at s equal to 0, it is basically 100 upon 2 into 10. So k would be equals to 10. So your value, your modified transfer function will be s square plus 2s plus 2. That is your modified transfer function. Yeah, I hope that part is clear. Correct. So that's how you can take the dominant pole approximation. Just hold on. Yeah, here I think I have done the same thing. Yeah, that's how you can take the dominant pole approximation. Already we have discussed about impulse response and step response. I will not discuss about this much. Okay, so step response will be integration, impulse response will be this. Already these things have been. So I can solve few questions. Let's say we have been given we have been given a, hold on a second. Okay, what am I solving here? I'm just thinking. I think we missed a question. Okay, no worries, no problem. Yeah, let's solve this question. So we have been given a step response, right? We have to find out the impulse response. So impulse response will be very simple. So if the step response is given, impulse response will be just the derivative. Okay, impulse response would be just the derivative. So you can easily calculate the impulse response. You will differentiate. So if they have given you the step response, you will differentiate the you will differentiate the step response to get to impulse response. This has been discussed at the starting, right? So if I differentiate this function, just be careful, right? Just be careful. So use chain rule. So I will have minus 2 into e raised to power minus 2t into u of t, and plus e raised to power minus 2t into delta of t, and if t is equals to 0, then this will be 1. So this will be equals to into delta of t, right? Because at t equal to 0 this is 1, other than that this is always 0, right? So it won't matter basically. So basically, right, if I have any function x of t into delta of t, so this can be written as x of 0 into delta of t, because any time other than 0 it will always be 0. Similarly, if I have x of t into delta of t minus t naught, so anytime other than t naught, delta of t will be 0. So this will be x of del t naught into delta of t minus t naught. All this will be taught to you in signals, but I'm just giving you an overview. So this will be the step response. Okay, most of the students only will write this part, but no, there will be an impulse signal as well. So be very careful. One day gate examiner will ask you and you will be not able to solve it. So if let's say okay, now let's say if I would have asked you if this was my, instead of it being the step response, this was my impulse response. If this was my impulse response, what will be the step response? So step response will be simply the integration, right, of the impulse response. So integration of this dt from minus infinity to t, running integration. So of course t less than 0, this is 0, so integration will be converted into 0 plus to t e raised to power minus 2t, u of t will be converted into 1. So this integration is very simple. It will be yeah, minus 2 hold on a second, yeah, 1 by 2 1 minus e raised to power minus 2t by 2. Yeah, that will be the step response. So I hope this part is clear. How can you calculate the step response? How can you calculate the impulse response? Of course, don't forget to write a u of t, because this is only valid for t greater than 0, right? For t less than 0, this is always 0, because I have integrated from t equal to 0. Signal is 0 for t less than 0, so integration also will be 0. So that's why you have to multiply a u of t. So that's how you can convert from step response to impulse response. Okay, I think here one page has been, for some reason, has been deleted. Yeah, don't have to worry about the convolution, those things you don't have to worry about. Okay, this here if you see, yeah, so you can always, again, like this was the method 1, right, where you can easily simply, sorry, where you can simply approach in time domain. So there is a frequency domain approach as well, transfer function, right? So what we can do, if I know the step response now, right, so what is the step response? Step response meaning the output, right? C of t is e raised to power minus 2t u of t. So what will be the Laplace transform C of s? It will be 1 by s plus 2. 1 by s plus 2. That is the Laplace transform. Now, what do I mean by step response? Response, so response of the system when my input is step. So basically, C of s also can be written as the transfer function into the R of s, because C by R is transfer function. So when my input is step, that is 1 by s, the output is what? Output is 1 by s plus 2. So from this I can easily calculate what is my transfer function of the system, and we know that the transfer function of the system is actually called as the transfer function of the system is actually called as the impulse response, right? Laplace inverse of this will be the impulse response. So yeah, I cannot simply calculate the Laplace transform. So what you can do is you can again convert this, right? You can write this as s plus 2 s plus 2 minus 2, that is equal to h of s. So it will be 1 by 2 by s plus 2 equals to h of s. So yeah, now if I take the Laplace inverse of this will be Laplace inverse of 1 is delta t minus 2 into e raised to power minus 2t. I'm just doing it this in a rough, okay, but you are seeing that yes, we are getting the exact, here I will have u of t, right? I'm getting the exact solution, right? I'm matching. So transfer function method works. So in both ways it will work basically. So yeah, let's solve a basic question, and with that we'll end like the first chapter, and we will start with few gate PYQs. So we have been given this unit impulse response of a unity feedback system. Nothing is mentioned, you will assume negative unity feedback system. Okay, the open loop transfer function is, this is also a gate question but very old gate question, so you will not solve it, I know. So what will be the open loop transfer function? So first of all you have to identify the, this is given as the impulse response. So if I have been given the impulse response, this is simply my transfer function, right? Impulse response is called as a transfer function in time domain, which is, if I take the Laplace inverse, which will be my h of s. So they are asking me open loop transfer function. So in like they are talking about the in S domain. S domain, what will be open loop transfer function? This is a negative unity feedback system. So if we know h of s, not h of s, sorry, our transfer function, that is equals to, let me write it h of t only, that is equals to OLTF upon 1 plus OLTF, right? For a negative unity feedback system. So what is this h of s? I know what is c of t. C of t is this, that is my h of t. So let me find out the Laplace inverse of this. So what is Laplace inverse of minus t into e raised to power minus t? So I know the Laplace transform of e raised to power minus t, that is 1 by s plus 1. What will be minus of t into e raised to power minus t? You remember multiplication in time domain represents differentiation in frequency domain with a negative sign. How to remember? Just remember it like this. If I have u of t, the Laplace transform would be 1. If I have, or let me not do, if I have 1 or delta of t, the Laplace transform is simply 1, right? If I have u of t, the Laplace transform will be, sorry, not u of t, what am I doing? Okay, sorry. Okay, so if I have, yeah, if I have 1, the Laplace transform, or sorry, if I have u of t, the Laplace transform was 1 by s, right? If I have t into u of t, the Laplace transform was minus 1 by, sorry, 1 by s square. Laplace transform of positive 1 by s square, right? It was plus positive 1 by s square. So this is how you can remember. I am differentiating and adding a negative sign. So I will differentiate this, right? And then I will add a negative sign. So this will be actually 1 by 1 plus s square. That's all. Okay. Okay, and another negative sign is already there. So this will be minus actually. That is interesting because this will be minus. Yeah, because I'm adding a negative sign, right? Yeah, this will be minus. So this will be minus 1 by s square. Be very careful. This will be minus 1 by s square, right? Minus 1 by s square. Because already if I multiply t, I already have a negative sign, right? Again, if I'm adding another negative sign, this will be plus. So simply just differentiate this. If I differentiate this, it will be simply minus 1 by s plus 1 whole square. And what will be the Laplace inverse of this? It will be 2 by s plus 1. So overall, this will be 2 by s plus 1 minus 1 by s plus 1 whole square. So this is my h of s. So overall, if I write this in a neat manner, this will be 2 into s plus 1, that is 2s plus 2 minus 1, or 2s plus 1 divided by s plus 1 whole square, right? So what will be the OLTF? This can be written as this s square plus 2s plus 1. So this is my OLTF plus 1 plus OLTF. So what I can do, I can use componendo dividendo. So if I use componendo dividendo, I can subtract the denominator with numerator. So this will be 2s plus 1 s square plus 2s plus 1 minus 2s plus 1, and similarly here OLTF 1 plus OLTF. We can do it, right? I hope you know what is componendo dividendo. So simply the right hand side will be OLTF by 1, that is simply OLTF only. That is simply OLTF. So my OLTF would be equals to simply 2s plus 1 upon s square. That is what your OLTF is. That is the answer of this particular question. Okay. So let us now solve few gate PYQs on basics of control system. This is the first one. A differentiator has a transfer function. What? So what is a differentiator? It will differentiate the input. So I will have a input, let's say x of t, and I will have a output y of t, and the output will be differentiation of the input. Now the thing is, they're talking about it varies linearly with frequency and these things, right? So let me convert this into transfer function. I have to find out the transfer function. So anyways, I have to find out the Laplace transform of this. So what is the Laplace transform? So the Laplace transform would be y of s would be s into x of s. Y of s by x of s equals to s. Okay, that is what my Laplace transform is. Now if they're talking about frequency domain, right, you will replace, whenever they're talking about frequency domain, you will replace your s with j omega. This thing also you have to remember, replace s with j omega if they're talking about frequency, right? So if I replace s with j omega, this is my transfer function h of s. So if I replace s with j omega, h of j omega would be j omega. So phase increases linearly. What is the phase of this? So the phase would be what? Phase is always 90, right? It is always imaginary. There is no real part here, right? No real part. So angle of h of j omega is always 90 degrees. Okay, angle of h of j omega is always 90 degrees. What about the magnitude? Magnitude is always omega. Like I hope you know how to calculate the magnitude and phase of a complex number. So phase increases linearly with frequency, wrong. Magnitude remains constant, no. It is a function of omega, frequency itself. Magnitude increases linearly with frequency, yes, because if I plot the magnitude, you will see that with frequency for positive frequencies, because they should have mentioned for positive frequencies, magnitude will only increase linearly. So this yeah, third option is correct. Now magnitude decreases linearly with frequency, no, option D is incorrect. Magnitude will not decrease linearly with frequency, magnitude will simply increase with frequency. Yeah, magnitude will simply increase with frequency, not decrease. So option C will be the correct answer for this question. Let's solve the next question. This is the next question. This was asked in gate BM. So a unit step input applied to a system with impulse response h of s, this, right, at t equal to 0. The output of the system y of t at t equal to 0 plus would be. So if I am applying a unit step input, right, whose impulse response is this, what will be the output of the system, right, for the same step input? So let me first, because what will be the output? Y of s, let's see, let me write y of s. Y of s would be input r of s into h of s, right? H of s is given to me, r of s is also given to me. It is unit step. So r of s is simply 1 by s. H of s is what? H of s is simply 1 minus s by omega z by 1 plus omega p. Now they are asking me the value at t equal to 0 plus. What will I do? I will use the final value theorem. Now omega p and omega z, they should have mentioned both are positive and the poles are lying on the left hand side. So definitely I can use the final value theorem. So what I will do? I will write limit. So y of, so not final value theorem, what am I doing? Initial value theorem. It does not matter wherever the poles are. I can use the initial value theorem. So y of t of 0 plus will be equals to limit as s tends to infinity s into, I can use the initial value theorem, into y of s, and y of s is this value. So this will be s will be cancelled, 1 minus s by omega z upon 1 plus s by omega z. So if I solve the limit s tending to infinity, this will be, so omega p, this will be omega p minus omega p by omega z. So option C will be your correct answer for this question. Pretty simple, straightforward. Let's solve this one. The input x of t to a system is related like this with a differential equation, right? This is interesting. What will be the transfer function? Now this you will learn in signals and system as well. Here also I'll teach you the basics basically. If you don't understand this question, don't worry, you will study this again in signals. Okay, so basically transfer function is what? Transfer function is Laplace transform y of s upon x of s. So my main aim will be to convert this differential equation into its Laplace domain. That's it. Okay, so what is the Laplace transform of this? It is simply s into y of s. Now, for now, I am assuming there are no initial conditions, but there will come a stage where there will be initial conditions. So it will not be just s into y of s, it will be something else. So that will be taught to you in state space. For now, there are no initial conditions. Nothing is mentioned. There are no initial conditions. And for anyways, if there are initial conditions, you will not be able to find out the transfer function. So if they are asking you to find out the transfer function, then there is no initial conditions. For the students who understand, great. For the students who don't understand, ignore this part. Ignore it. Okay, so s into y of s plus Laplace transform of y of t would be what? Simply y of s. This will be y of s equals to 3 into x. Now what will be the Laplace transform? So x of t has a Laplace transform of x of s. So Laplace transform of x of t minus 3 will have this, right? If there is shift, this will be e raised to power minus 3. Hold on a second. Yeah, e raised to power minus 3s x of s. Because I always, what do? I always get confused, right? Whether this will be minus 3 or plus 3. So how can I remember? So I remember if I have minus at, then the Laplace transform was s plus a. So there is a sign reversal here. So if there is a sign reversal here, this will be not, there will not be any sign reversal. Okay, that's how I remember it. Okay, so yeah, this will be 3 into x of s. Of course, there will be another e raised to power minus 3s into u of t minus 3 is already there. So yeah, it is anyways a unit step. Unit step on it exists only for t greater than 3. So it, this part is fine. Okay. So yeah. So if I take my y of s common, if I take my y of s common, this will be s plus 1 equals to 3 into e raised to power minus 3s x of s. So your y of s upon x of s equals to 3 into e raised to power minus 3s upon s plus 1, which is present in option B. So option B will be your correct answer for this question. Pretty straightforward. Let's solve the next one. Okay, signal flow graph is given. Sorry, this is not supposed to be here actually. I will change it. This will be moved to the next chapter. Yeah, so this will be actually fourth question. Just a typo from my end. Okay, g of t is this, f of s is this, where f of s is the Laplace transform, then the value of g of t at t equal to 0, right? G of t is the differentiation of f of s. So what will be g of s? It will be simply s into f of s, correct? And they are asking me the value of g of t at t equal to 0. So I simply have to apply the initial value theorem. So it will be s square limit s into g of s, right? So this is simply s square into f of s, right? So that is 1 plus s upon, so this will be tending to s infinity. Yeah, initial value it is like it is infinity basically. This will be infinite, or this will not be. Hold on a second. This is s times this. G of s is s times, they are asking me, then the value of g of t at equal to 0 multiply s. That is interesting. G of t Yeah, I just checked this. This is coming out for me. It is coming out to be infinite because it seems that there will be a impulse signal. So the value of impulse at equal to 0 would be infinity. So it seems like they have given the option A. I feel it is wrong. I think option D would be correct. Okay, that is my understanding. You can solve in the comments below. You can let me know if you get someone. Like what you can do is you can find out the time domain expression g of t, and from there you can solve. That is the homework for you. Calculate the time domain. So what you can do is first of all you can calculate f of t, right? And then you will differentiate, and if I differentiate, I'm expecting what will happen. You will differentiate one of the step and there will be a delta t term. Due to that the magnitude will be infinity, but for some reason they have given A. I think option A is not correct and they don't check BM paper, so they give wrong answers. Okay, a continuous time system that is initially at rest is described by this. Okay, where x of t is this, then the impulse response of the system would be. So impulse response is nothing but the Laplace inverse of my transfer function, right? So transfer function is c by r or y by x of s. So let me write this as s into y of s plus 3 into y of s equals to 2 into x of s. So your y of s upon x of s would be equals to 2 upon s plus 3. Now if I calculate the Laplace inverse, this will be 2 into e raised to power minus 3t u of t, which is present in option C. So the impulse response would be option C. Okay, I think this will be in which year I don't know, but okay. '23. Okay. Yep. Let's solve the next question. So here we have been given the transfer function and we let u of t be unit step input, x of t that results in a steady state sinusoidal output where y of t is sin pi t. Okay. So the input x of t that results in a steady state is okay. Okay, there are no options here. I have to maybe like there will be some option. I will solve it basically. So the transfer function is given, right? For what input I will result a steady state output. So if my output is sin pi t, right? Output is sin pi t. So there are two ways to solve. Like you can take help of magnitude and phase condition using LTI system, eigenfunction, eigenvalues. Okay, that will be taught to you in signals. I'm just doing the basic approach. So y of t is this. What is the Laplace transform of this? What is y of s? It will be omega naught, right? Because initial value theorem, if I apply, it should come out to be 0. So omega naught is pi in this case. Pi upon s square plus omega naught, that is pi square. That is the Laplace transform. And y of s I know. What will be x of s? So x of s would be simply s plus pi upon s minus pi into y of s. That is pi upon s square plus pi square. Correct? Now for this, then put calculating this will be but tedious task for us. Okay, so what we can do is we can put s equals to, okay, this will be a bit tedious for us. S equals to j pi. If I put s equal to j pi, simply this will be gone, right? This will be gone. So if I put s equal to j pi, this will be, okay, there will be two roots actually. I'm just thinking how can I easily solve it, because I have three roots, right? That will be a bit hectic for me. Okay, like there will be two roots, right? S equal to plus minus j pi. Okay, I'm just thinking how do I break it down. Okay, yeah, let us do one thing. Let me put s equal to plus pi. If I put s equal to plus pi, like I'm just doing partial fraction, this will be s plus pi. So what I want is I want to break this down into this, right? A upon s minus pi plus b upon s square plus pi square. This will be easier for me. So actual transfer function is s plus pi upon s minus pi into s square plus pi square. So if I multiply by this term, this will be pi into s plus pi equals to a into s square plus pi square plus b into s minus pi. So basically a into s square plus b into s. Right. So I can compare the coefficient. So a has to be 0, right? A, no, sorry, hold on a second. Yeah, this will be s square plus pi square, and this will be s minus pi. Yeah, correct. So a has to be 0, right? Yeah, a has to be 0. A is 0. That is convenient for me. Okay, a is 0. Oh, then it, okay, then it, like, b is what? That is not convenient at all. That is not convenient at all. Okay. Just thinking of something. How can I solve it easily? Okay, we have to use the eigenvector eigenfunction only. That will be the easiest for us. So basically, right, what we do is I'll teach you one thing. So if my output is this, right, sinusoid function. So if let's say I had an input x of t, that is some a naught sine omega naught t, and if I have a transfer function like this, the output also, if I'm providing a sinusoid, output also will be a sinusoid, but with some different amplitude and different phase. Frequency will be same, but phase will be different, and this phase will be what? Actually, this phase will be the angle of my transfer function h of j omega, right? And this amplitude will be magnitude of h of j omega. These are called as like eigenfunctions. So this will be taught to you in signals. If you don't know, अब क्या कर सकते हैं भाई, याद कर लो. But I hope you know, like, ये पता होगा तुमको, or like you will remember this. So output is given to me, right? I just need to find out the input. So what is the magnitude of my transfer function h of j omega, right? J omega, basically put s equal to j omega, that's it. Whenever you're talking about sinusoids, put s equal to j omega. This will be j omega minus pi upon j omega plus pi, and they have told you that the frequency of the output is pi, right? So omega will be replaced with pi. So this will be pi, I can take common, this will be j minus 1 upon j plus 1. Okay, if I take calculate the magnitude will be simply pi. Okay, so magnitude of my transfer function, right, is simply sorry, yeah, this is the output will be magnitude of the transfer function into a naught. Okay, into a naught, amplitude will be multiplied, this amplitude will be multiplied by the magnitude of the transfer function at that particular frequency. This will be equals to, given to us as 1, right? Amplitude is 1 of my output signal, and magnitude of h of j omega naught is simply pi. So a naught would be simply equals to 1 by pi. That is what my a naught is equals to. What about the phase? I see, sorry, this will be angle of h of j omega plus angle of my input x. So this will have some theta, right? Theta x. So this will be added here. Okay, so I'm not going into the details here, I'm just telling you how to solve this. So what is angle of h of j omega? So if I find out the phase at this particular frequency, right, this will be what? The real part is negative and the imaginary part is positive. So it is 180 minus theta. So 180 minus theta would be tan inverse 1 by 1, that is 45. So this will be, the top one would be 135 degrees and the bottom one will be simply minus 45. So yeah, 135 minus 45 degrees, right? It will go on the top. So this is plus 45 minus 45. So overall angle would be 90. So angle of the transfer function is minus 90 plus theta x, and overall the angle is supposed to be 0 because at the output I see there is no phase difference, 0. So this is supposed to be 0. So basically your theta x would be 90. right? So basically your x of t, a naught would be 1 by pi, and this will be sine of omega naught t. Omega naught is supposed to be pi t plus 90. Now what is sine of pi t plus 90? So this is my sine, this is my cos, right? So sine pi t plus 90 is simply 1 by pi cos of pi t. That's all. Okay, it is 1 by pi cos of pi t. That's all. Right? So option C, like okay, there is no other option here, but I think this option will be valid. So this will be answer. So you can use bit of property of eigenvalue eigenfunction. This is taught to you in network as well. I think this I have taught to you in network as well, and this will be taught to you in signals as well. But if you don't know now, you know. So basically, if I have some input, sinusoidal input, the output will be just the function of the transfer function multiplied by the amplitude, and the phase will be shifted by the phase of the transfer function at that particular frequency plus the phase of the input. Okay, let's solve the next question. The impulse response, like mostly they will ask you questions on transfer function only. Rarely they have asked sensitivity, but I am expecting they will ask some question on sensitivity. The impulse response of an LTI system is given. The input signal x of t is this. The output would be what? So if I know the impulse response, right, I can find out the transfer function h of s. H of s would be, this is 1 plus 0.5 or 1 by 2 into e raised to power minus 4s. Okay, this is my transfer function, and input signal is given. If input signal is given, right, your output signal also will be a cosinusoid. Okay, but it will, its magnitude will be h of j omega naught into the input magnitude amplitude, that is 1. Input amplitude is 1. It will be cos, frequency will be same 7 pi by t plus theta. This theta will be angle of the input, that is 0 degree, plus the angle of the transfer function. So if I put s equal to j omega, that is 7 pi by 4, right? So h of 7 pi by 4, this will be 1 plus 1 by 2 e raised to power minus 4, 7 pi by 4, right? Okay, what will be its magnitude? That is interesting. So j omega, j 7 pi by 4, so this will be j 7 pi basically, minus j 7 pi. So what I can do is I can write this like this. This will be e raised to power 1 plus 1 by 2 e raised to power minus j pi raised to the power of 7. I can do this, right? Now what is e raised to power minus j pi? E raised to power minus j pi. So e raised to power j0 is here. E raised to power minus j pi would be here, right? Minus j pi would be here. That is minus 1. So this is nothing but minus 1 raised to power 7, right? 1 plus half into minus 1 raised to the power minus 1 raised to the power of 7, correct? So yeah, I thought yeah, minus 1 raised to the power 7. So this will be a odd number. So this will be 1 minus half, which will be simply half. So your h of this, right, is half. What is the magnitude? That is half. So what will be output? Output will be half into 1, that is half. So either it will be this or this, right? Now what about the phase? What is the phase of this? 0 degrees. So there is no phase shift between the input and the output. So yeah, if there is no phase shift between the input and the output, so only option A is valid, because 0 degree, so cos. If there was 90 degree, it would have been sine, minus 90 or something, but it will be cos. So that's how you solve these kind of questions. Okay, so just check the magnitude and the phase. That's it. I think we will have one more question. Right, this is the last question. The input x of t and y of t are given. Like mostly they will ask these things only. Laplace transform of the impulse response. Laplace transform of the impulse response is nothing but simply the transfer function, right? So it is the ratio of the y of s upon x of s. So y of s, this will be y of s plus s into y of s plus 0.5. Like mostly they are asking you this transfer function type questions only. Now what will be d square f? So here I will have a s square term, right? For double derivative I will have a s square term. Just be careful. Okay, so if I am differentiating twice, I will have a s square term. S square into y of s equals to x of s plus 0.1 into s into x of s. So y of s upon x of s, this would be equals to 0.1 into s plus 1 upon s 0.5 into s square, 0.5 into s square plus s plus 1, that is present in option C. So it's like not that. Okay, hold on. This is correct only. Yeah, s square is there, so this will go on the bottom. Yeah, sorry, s square will not be there, right? This should not be s square actually. This should be s. Yep. This is correct. Option B. Option B is correct. It should be yeah, 0.5. Not option A. Sorry, option B is correct. Yeah, 0.5 into s square plus s plus 1. Yeah, that's all. So that's it basically with basis of control system. Now we will start with SFG and block diagram reduction techniques. So let's start with signal flow graph and block diagram reduction technique. And trust me, you don't have to remember anything except two things, right? The Mason's gain formula and the misconception of Mason's gains, like where Mason's gains formula is not applicable. Except those two things, trust me, you don't have to remember anything. Very easy chapter. Like why do I need this block diagram? First of all, we will study block diagram reduction. So let's say I have this block. So for this, the transfer function is g upon 1 plus gh. So what we can do is I can write this block completely as a single block for our own convenience, because this is very complex. If I just want to find out the ratio of c by r, I can write it like this. G dash will be same as the transfer function here. So there are many techniques to do block diagram reductions, like positive feedback, negative feedback. I will not tell you anything. Okay, just these things you remember. Like if I have two blocks in cascade and there will not be any loading effect, because I have told you internally there is a buffer, right? So simply the transfer function will be g1 into g2. Now if let's say this g1 was g upon 1 plus gh and this g2 was some g1, or yeah, g upon 1 plus gh, and this g2 is some x upon 1 plus xy. So overall the transfer function would be g into x upon 1 plus gh into 1 plus xy. That's it. Okay, just giving you examples. And don't worry, you don't need to remember all this, right? Very simple. These are very simple. Like parallel connection, I hope you understand. Like if I have a summer here, right? If both are plus sign, so I will simply add all of them. If there is a plus minus, then I will add the first one, I will subtract the second one. So these are very simple things. I hope I don't have to explain these things. Okay, don't worry about these things, because trust me, the way I will teach you, you don't have to remember anything. Where is no need to remember all these things. Let's solve few questions right here. What you need to do is whatever is very difficult, right? Assume that to be x. Whichever node is unknown to you, assume that to be x or any variable. So let us take an example. So I know this node, right, is C, but here I have a adder. So I am not able to assume anything here, correct? So what I will do, let me assume like this is a common node, right? This is connected to here and here as well. And this node is what? R. So this node is also R. It is a wire, right? So this node is also R. And just give me 1 second. Just let me turn off the Wi-Fi. So this node is R, this node is R. So here I'm adding R, right? So this term is R, but I don't know what is this. This is also R. So let us assume something, right? Let me assume this to be X. If I assume this node, this point to be X, correct? What will be this node? This will be simply S into X, because this is S, right? So I'll multiply gain into X. Remember, if I'm writing just X, right, it means I'm writing X of S. It is a function of S. So it is understood internally by you that if I'm writing x, that basically means I'm writing x of s. Everywhere I will not write x of s, it will be very confusing to us. That's why. Okay, so s into x, and here I have r. So ultimately my c, right, is equals to r plus s into x. So I need to calculate this x value. How will I calculate? So I know this value is x, right, and this value is also r. So r into 1 by s, that is r by s, and this side is also r. So I'm adding these two values. So x will be equals to r by S plus R. This is my x value. So your question is solved. Your question is solved because I have to find out the ratio of C by R. Ultimately, they will ask you this ratio C by R. So I know what is x in terms of R. So I will write that it is R plus S into x is R by S plus R. So this will be C will be equals to R plus S into R. So C by R would be 2 plus S. That is simply your answer. That's how simple it is, right? Do you need to remember anything? No, nothing. No need to remember a single thing. So there are methods to which like take off point, this, that. No. We don't do all that, right? That's how simple it is. And that is your block diagram reduction technique done. So the first topic is done. Signal flow graph is a bit difficult. So not difficult actually, like, you have to remember a few things, that's all. Okay. And they ask questions like this. Trust me. Okay. So if you enjoyed this method, hit a like and comment in the video below, and of course hype the video. Okay. So that is what I have also solved here. Now let's understand signal flow graph. So there is a formula. So let me go to a very basic example. I think there will be a example. Where is it? I think yeah, this is fine. Yeah. So this we can do actually. This we can solve. Or yeah, let us solve for this one. So let us solve for, because we already know what is C by R. C by R is G upon 1 plus GH for a negative feedback system. So let me solve this using signal flow graph. In signal flow graph, what you do is you assume each node to be a alphabet basically. So I will first of all plot the nodes. So this will be a node. Okay, this is the input node, and then I have a summer. Sorry, not summer, subtractor. So let me name the node. So this is just input node, so I can avoid naming this node. I can name this node to be M. Okay, or let me name this node as well A. Let me name this node as A. Let me name this node as B, the summer basically. And between this node and this node, what is the gain? It is just simply a wire. So if it's just simply a wire, you will first of all write the direction of the wire, right? It is going from left to right, and the gain. If it is simply a wire, it will be 1. Let's say instead of wire, I would have had a gain of any value, let's say 3, and here I have this subtractor. Then instead of 1, I will write 3, and direction will be direction of this wire will be denoted by the direction of this arrow. That's all. So this is my B. Now again, so let me first of all mark the node. So this is A node, B node, C node, and D node. Correct. So between each node there will be some gain. So between B and C, what do I have? Gain of G, right? What is the direction? Direction is this. So this will be the direction. Gain is G, and between B and C, I have this node. Between C and D, I have simply the output, right? So this is my C of S. And between B and C, again I have another feedback node. Now remember what is the direction, right? Direction is this. So we'll write the direction like this. What is the gain? Gain is H. But as it is a subtractor, I will write here minus H. If it was a adder, I would have written here plus H. So if it's a subtractor, you will have to write negative sign, because somehow you have to integrate the negative, like implement the negative sign as well, right? You have to show the negative sign. How will you show the negative sign? That's how we will show the negative sign, with minus H. Now what is signal flow graph? So what is Mason's gain formula? So this is my signal flow graph. So I hope you have understood how to convert from a block diagram to signal flow graph. Now Mason's gain formula can directly tell us what will be the transfer function, what is the ratio between C by R, or what is the ratio between any two nodes. That is what Mason's gain formula tells us. Whenever I am writing C by R, you have to understand that I am writing C of S by R of S. Okay, I am not writing bracket S, because that will be just hectic for us, right? Yep. Okay, C by R. So if I'm writing C by R, so here how will I solve it basically? So here, right? Yeah, Mason's formula tells us that you find out the sum of the forward path gain into the delta k, delta of that particular gain. What is delta? I will explain. Divided by the delta. Okay, I will explain what is this. What is it basically? So, in how many ways can I reach the destination node from the source node? So, in this case, our A is the source node, D is the destination node. How many ways can I reach it? So, if I start from A, B, C, D, so don't forget the arrow. So, if I go along this path, I can reach my destination. If I go along this path, can I reach my destination? No, because whenever there is arrow, right, so you are supposed to only travel along this direction. You are not supposed to travel along this direction. No. So I cannot reach my destination with this path. So there is only a single forward path, that is this one, and that is the reason why my G is actually called as the forward path gain. So what is the forward path gain? Simply whatever values you are seeing, whatever gains, this is also one, right? Simply whenever there is a one, simply one. Whatever gains you are seeing, just multiply that. That is your forward path gain. First of all, you determine what are my total number of forward paths. What are my total number of forward paths? Only one, a valid forward path. Now, what is the forward path gain for that particular? So k equals to 1. What is the forward path gain? That is written as P1. What is the gain? It is 1 into G into 1. So that is simply equals to G. What will be delta? Now delta is interesting. Delta 1. First of all, let me calculate delta. What is delta? Delta is basically determinant of the whole signal flow graph. It is simply 1 minus sum of all the loop gains, then plus sum of all the non-touching loop gains. What do I mean by non-touching? I will come to it. For now, just understand this. For us, for this particular question, we will only solve till this point because there is only a single loop. So there is no concept of touching or non-touching, right? So we will come to this non-touching part later on. For now, just understand this, that for this question, your delta is actually this value for this question, as we have only a single loop. So what is the loop gain? Loop gain basically means if I follow this loop, what is the gain that I am getting? It is G into minus of H. That is my loop gain. So it will be 1 as I have only a single loop. So it will be G into minus of H. So this will be equals to one plus GH. Okay, that is what your forward path gain is equals to. Sorry, that is what your delta. So delta I have got. What about delta 1? Delta 1 is the same formula, but you have to exclude those loops which are touching my node. So let's say if I remove my forward path, so what will be left? If I remove my forward path, I will have this, right? This will not be there actually. I am removing my forward path, only this is there. Okay. So do I form any loop here? Loop basically means, if I start from B point, I should be able to come back to the same point B. So what is the forward path? It is A, B, C, D from source to destination. What is the loop? Loop is B, C and then again B. Loop basically means I will come back to the same point. If I start I should come back to the same point. That is what loop means. But if I remove my forward path, will there be any loop? Because this path has been removed, so I will not be able to go from B to C. There is no path for going to B to C. From C to B there is a path, but from B to C there is no path. So actually there is no loop gain. If there is no loop gain, so delta 1 will be 1 minus 0, because the gain is here is 0. So that is simply 1. So now if I put this in the formula, this will be forward path gain, that is G, into 1, because it is delta 1. Because I have only a single loop, so K is 1. I can have multiple Ks, upon 1 plus so delta is 1 plus GH. So this is the same formula that we derived earlier as well. Very simple, but this was just to show you how to use the Mason's gain formula. We will discuss about this, right? We will discuss about few other things. Let's come to this question. So the block diagram is shown. Solve using the Mason's gain formula C by R. You can solve using block diagram reduction technique as well, using Mason's gain as well. So let us solve using both ways. So first let us solve using Mason's gain. So first of all I have to convert this, like normally they will give you, directly the signal flow graph. If they have not given you the signal flow graph, they have only given you the block diagram, then solve using simple block diagram reduction technique that I taught you earlier before SFG. If they have given you the signal flow graph, then you will use SFG. Otherwise it will consume some time to convert your block diagram to SFG. In that time you can anyways solve using block diagram. Okay, so yeah, let us solve. Let me convert this into block diagram reduction technique. So yeah, this will be RFS, then I have G1, G2, like this is a node, right? So all this must be, so I'll name the node. This is let me name this A, B, C, D, E. So these are all my nodes basically. So I have a node A where I have my input, then I will put the gain, that is 1, then I'll put here, so I should not put it like this, then I should put the gain here, that is G1, then I should put here, this shall be G1, then I should put here G2, this shall be D, this is B, this is C, then I should put G3, then I have this E node, right, where I have C of S. Now I have to include this loops as well, right? So here I have a subtractor at point C with H1. So from E to C, I'm traveling to H1 with minus of H1, right? Because I have a subtractor. Now what I do is, actually I don't like this, right? I don't like to take anything from directly from the output node. So what I do is I write additional nodes, that is just for my own convenience, and that is what you should follow as well, because Mason's gain, right, has bit of limitations. So I will prefer you follow this method. So what you do is, because I'm taking directly from the output node, right, so I can do one thing, right? I can write an additional node. Let me write this node as F. Okay, and this is my output node, C of S, and I will write a gain of 1. This will not make any difference, but it will be good practice to follow. Why? Because there are a few limitations. Also, don't directly write the input node. What you do, you take an extra node. You can name this node anything. Let me write this as O node, and this is my R of S. Okay, that is just better actually. So there is a reason behind this. Just hold on. Okay, so this is O. Give me 1 second. Yeah. Yep. So okay, let me name this nodes again. So let me name this node. This is O node. Then I have in A node, then B nodes, then C node here, D node here, then E node here, and F node here. Okay, that is just for my own convenience. And of course, there is another loop back here from D to B. D to B. I have a loop back. D to B. Right. Gain is minus of H2 because it is a subtractor. If it was a adder, it would have been plus of H2. Now let us use our formula. What is the forward path? So actually, there are two loops I can only have. So maybe those questions are not there. I'll solve those questions as well. How many forward paths I have? Only a single forward path. Otherwise, I will not be able to go. Right? I have only a single forward path. Now, few students might have a doubt, sir. What if this? No, this will not be a valid forward path because you should only cross a node once. For a loop, you will come back to the same place and you will cross any node only once. For any path, you should only cross a node only once. So if I choose this to be my forward path, I am crossing B and C twice. Not valid forward path. Only this is my valid forward path. From here to here, this is my valid forward path. Rest, these are all not my valid forward path. So I have only a one valid forward path. So what is the forward path gain? P1. This is also a wire of 1 gain. So 1 into 1 into this is G1 into G2 into G3 into 1. So this will be G1, G2, G3. Okay, G1, G2 and G3. So now what shall we do is we shall increase this, right? So now what we will do is so now we will find out the determinant. So for determinant it is very simple. 1 minus sum of the loop gains. So what is this is my first loop and this is my second loop, correct? First loop and second loop. So what is the loop gain here? Loop gain here is G1, G2 minus H2. So G1 G2 minus H2. What about the other loop gain? Other loop gain is this, right? So G2 G3 minus H1. G2 G3 minus H1. Now there is a third term that will include plus sum of two non-touching loops. Sum of two non-touching loops. So what do I mean by non-touching loops? Here I have two loops, right? And if all the nodes are unique, there is no common node between the two loops, that means they are non-touching. Basically the loops are not touching each other. Here I see C and D is common for this loop as well as for this loop. So they are touching. So then you don't need to worry about the third term. Okay, the third term will come, but as it is touching, so only you will write till the second term. So this will be 1 plus G1 G2 H2 plus G1, sorry, G2 G3 H1. Okay, so this is what my loop is, 1 plus G1 G2 H2 and G2 G3 H1. That's all. Correct. So yeah, that's about it basically. So this is my delta. What about delta 1? Delta 1, what will be delta 1? So delta 1 would be 1 minus the loop gains, sum of loop gains, if I remove my forward path. If I remove my forward path, do I have any loops present? If I remove my forward path, do I have any loops present? No, no loops are present. So it will be simply 0. So this will be 1. So ultimately my transfer function C by R would be equals to forward path gain into delta 1, that is simply 1 upon delta G1 G2 H2 plus G2 G3 H1. Now it is taking me some time because I am explaining, but for you it should not take you much time. It should take much lesser time because you will be pro at this. Correct. So I think, yeah, we have already solved this. Yeah, this is the answer. Now there is another way to solve this using block diagram reduction technique. So let me solve this using block diagram reduction technique. So let me remove the nodes here. So here this will be, this node is C, right? So I'm multiplying this with H1 and I'm reaching here. So this point value is C. Just give me 1 second. C into H1. And okay, this node I don't know. This node value is unknown. So let me assume this node to be X. So what I can do is if I multiply X into G3, I will get back to this node. So X into G3 is C. So X is actually equals to C by G3. So try to reduce unknowns as much as possible. So this will be actually C by G3. This was one of the block diagram reduction techniques. So you don't have to remember it. Just use it, right? C upon G3. So this value is C upon G3 and this value is C upon G3 because it is the same wire. I have to multiply with H2. So this value would be C upon G3 into H2. C upon G3 into H2. And this value is R, right? So what will be this node value? I am subtracting. So this will be R minus C upon G3 into H2. And then again I am multiplying this with G1. So this value will be C R minus this into G3 H2 into G1. So and this point is C into H. This node value is C into H1. So again I am subtracting, right? So this point value will be what? This will be, let me write this as some Y. Okay, Y into G2 will be C by G3. So C by G3 is actually equals to Y into G2. And what is Y? Y is simply the subtraction of this and this. So let me replace it over here. So C upon G3 into G2 equals to Y. Y simply C into H1 minus R minus C by H, I guess it will be C by G3 into H2 into G1. This, right? This is my value. So if I solve this, like, this will be a bit hectic, but you can solve it. Okay. So if I solve it, this will be C. Okay, let me take the C terms together. 1 by G3 G2 plus H2 G1 by G3. Minus sign is there, right? So this will be anyways minus only. That is interesting. Minus should not be there actually. Okay. Oh, sorry. Here I have minus, right? So this will be minus C into H1. Sorry, this will be negative sign. I'll have a negative sign here, right? Because I'm subtracting, correct? So this is actually with positive sign only, right? Because this is in the plus, this is in the minus. Okay, my bad. So this will be plus. This into G1, correct? Okay, and this will be plus into H1. This is equals to R into G1. Okay, R into G1. Now if I multiply, if I write C by R, this will be equals to G1 G2 G3 upon, so if I multiply this with G1, this will be G1 correct. Okay, let me keep, okay, this is already, sorry, I don't need to multiply this by, so if I multiply this with G2, right, this will be converted into, because I need to make a common denominator, so G2 G3 is a common denominator, so this will be 1, this will be G1 G2 H2 plus G1, sorry, G2 G3 G2 G3 H1, right? You can solve this equation, like I'll not tell you how to solve. So you are seeing that whatever we have solved here, right? What did he solve here? Same value, same value. We are getting the same value here. This is in small, but I hope you are gonna understand. We are getting the same value. No difference. So yeah, that's how you can solve using block diagram reduction. So I have given you the lengthy way, like you can see the proper way. Now there are a few limitations. Okay, before limitations, maybe we should actually take for the case. Okay, what are the questions? Okay, so I have to solve, okay, before this, right, I have to solve one thing. Let me, okay, just try to see. No, these are not great. Like I just want to choose a question where I have two loops basically. Okay, two non-touching loops. Okay, that's great. Let me choose a random question only. So if I will choose a random question, okay. Let's say we have a loop here, we have a loop here, we have a loop here. Three loops. So I'm just not writing the nodes for now. Okay, let me write the nodes also. One, gain 1, then 2, then 3, then 4, then 5, minus 2, minus 3, minus 1. Okay, so yeah, this is R of S and this is C of S. Now can you tell me how many non-touching loops I have? Pause the video, tell me how many non-touching loops I have. I have two loops that are non-touching. This, let me name this as loop L1, L2, L3. I have three total, I have three loops, correct? Three loops, out of which two are non-touching. These and these are non-touching because they don't have any node common. This loop L3 and L1 is touching, L2 and L3 is also touching because they have few nodes in common. Excuse, sorry for that burp. Okay, sorry. So yeah, now how many forward paths I have? So I'll just change this just a tiny bit. Okay, just be patient with me. Change this to this. Okay, 6. Just sorry for that. I will change this. Now can you tell me how many loops I have? Can you tell me how many loops do I have? Previously I had 3 loops. Do I have 3 loops still? No. Actually now I have 4 loops. Interesting, right? How? So if I start from this point, I am coming back to the same point without crossing a particular node twice. So I get 4 loops. Now I have 4 loops, but again L4 is touching, it has common node, right? It has common node between the both the other nodes. So it is touching with everything. So it is not isolated by itself. Okay? It is not isolated by itself. So now how many forward paths do I have? I have 2 forward paths. This one and this one. So how can I solve it? So what you will do? You will find out P1, right? Let me choose, this is my first forward path. What is the forward path gain? 1 into 2 into 3 into 4 into 5. So it is 5 factorial, which is simply 120. What about this? What is the gain here? 1 into 2 into 6, that is 12 into 5, that is 60. So your next forward path gain is 60. Okay. Now what you do is, what about the determinant of the loop? So it will be 1 minus sum of all the loop gains, right? Sum of all the loop gains. So what is the loop gain of L1? It is minus 2, plus what is the loop gain of L2? It is 4 into minus 3, that is minus 12, plus 3 into 4. Now is this a loop? No, this is not a loop actually. This is a loop, right? This is a loop. L3, 2 into 3 into 4, that is 12 into 24, 24 into minus 2, that is minus 48. Minus 48. Then I have this loop, 2 into 6 into minus 2. Okay, this is 12 into minus 2, that is minus 24. Okay. Now next I will write plus. The signs will always alternate. Okay, if I have minus here, I will have plus here. Signs will always alternate. It will be sum of all the non-isolated loop gains multiplied together. Sorry, not non-isolated, isolated loop gains multiplied together. So here, right, which loop gains are isolated? Basically not touching, L1 and L2. So L1 and L2 are not touching, so I will multiply L1 into L2. Gain of L1 into gain into L2. What is gain of L1? Gain of L1 is minus 2, gain of L2 is minus 12. So 2 minus 2 into minus 12. Only I have only a single combination of 2 non-touching loops. That's it, right? I don't have anything. All the other loops are touching. Now similarly, this formula will be continued actually. Here I will have again minus sign and summation of all the 3 isolated loops. Multiplication of 3 isolated loops. In this case, I am lucky, I don't have no 3 loops that are totally isolated. What can happen? Maybe I can integrate another loop here. Okay, just for the sake of it, I can integrate a loop here. So here, right, L1, L2 and L5, all 3 are isolated. So that will be coming here, right? L1, gain of L1 into gain of L2 into gain of L3, sorry, L5 will come here, right? 3 I will multiply and will put it here, okay? And this will keep on happening. This pattern will keep on happening, but you are very lucky. Maximum, they will go till this point, okay? Very rarely I have seen them go for 3 isolated loops. Maximum, they will go for 2 isolated loops. That's it. Otherwise, formula, like the question will be lengthy. And that is my prediction, that they will go till 2 isolated loops. So just be careful for 2 isolated loops. That's it. Okay, yeah, that is one thing. So yeah, you can solve for this. I will not solve. Now what will be delta 1? Delta 1 will be basically your loop gain with this removed. If I remove this, right, none of the loops are complete. So delta 1 will be simply equals to 1. If I remove this particular thing, actually, if I remove this particular thing, right, remember this node also will be removed. This node also will be removed actually. If I remove this forward path, this node also will be removed. So anyways, this L1, L3 are anyways gone. Your L4 is also gone. L2, you might have a confusion. If I remove this node, will I be able to compute L2 or not? No. If I remove this node is gone. Removing this node is gone. So this connection is gone. So L2 is also gone. L2 is also gone. So delta 2 also will be simply 1. That's all. So these are the things that you have to keep in mind for SFG. Now let's come to few limitations. Yeah. So you cannot have self loop like this. Okay. Your transfer function, you will get it as infinity. Something, there will be some problems if I have self loop, right? Okay, self loop is not a problem. Because yeah, self loop is not a problem. But if your self loop value, right, if you find out the transfer function of this will be a transfer function. If your self loop is unity, if this magnitude is 1, right, if it is unity, then this will be a problem actually. This becomes a problem. If it becomes 1, right, then your transfer function will be infinity. Then system will become impractical. Your transfer function will be infinity. One more thing I forgot to tell you is your Mason's-Gain formula is not just valid for this particular 2 nodes. It is valid for any 2 nodes. Let's say I change it now. Okay. Let's say I change my input and output. Let's say my input is here. My output is here, C of S. Now what you will do, Mason's-Gain formula is still applicable between these 2 nodes. So if this is my input and this is my output, you can still apply the same formula, but you have to find out the forward paths. So what are my forward paths here? So if I start from this node, I can I reach my C of S? No, I can never actually reach my C of S. So here my forward path gain is simply 0. I don't have any forward path gain, right? So your transfer function will be simply 0 because you will never be able to reach your input. So it is valid for any 2 nodes actually. So if I put this to be in the other direction, then this will be valid. So now I can see that if I start from, this is my input node, if I start from here, I get one forward path. If I start from here, I get another forward path. If I start from here, I get another forward path. Remember, you must, in this particular forward path, you must not cross a particular node twice. Of course, you will say, sir, I'm crossing this node once here, again in another forward path, again I'm crossing this node. So will that not violate? No, that is a different forward path. That is fine. In the same forward path, you must not cross a particular node twice. So here, I must not cross a particular node twice. I'm not doing that. I'm not violating anything. So this is fine. Okay, so Mason's-Gain formula is applicable for any 2 nodes in the SFG. Not only for this and this node. No, it is valid for any 2 nodes. So that is the advantage of Mason's-Gain formula. That will be used in state space. So be careful of this. Okay, limitation I have told you, self loop is not a problem. Okay, self loop is not a problem. You can have a self loop of gain. Self loop basically means that it has only a single node. That is the self loop. It is coming back to its own node. That is why it is called as self loop. That is not an issue. But the issue becomes when the gain of the self loop is 1. Right? Then your transfer function will be infinity. Then it will be a problem. So what we do? is we simply remove the self loop. Okay, if I have a gain of 1, we will remove the self loop and then compute the uh, transfer function. Similarly, like here we have an example, what is y by r. So what we can do is like there are many ways to solve. First of all, I will solve using SFG. Okay, so what is the forward path gain? So I have a forward path here and only one forward path, that's all, right? And if I remove this forward path, I will not have any loops. So my forward path, I have only a single forward path, that is 2 into 3 into 4, that is 24, and my delta 1 is 1. Okay, if I remove this forward path, all these loops are gone. Now what is delta? Delta is 1 minus sum of the loop gains. This is minus 1, this is minus 3, so minus 1 plus minus 3 plus minus 1 into minus 3. Because these are non-touching, these are isolated, so I will multiply, right? There will be a plus sign here. If I had 3 loops, there will be another minus sign and those 3 will be isolated with each other. Okay, so this will be equals to, delta will be equals to, this is 1 plus 4 minus 3, so 1 plus 1, that is 2. So delta comes out to be 2. Does it come out to be 2? Just hold on a second. Sorry, this is plus, right? Minus into plus. Sorry. So 4 plus 4, that is 8. Delta comes out to be 8. So your y by r will be P1 into delta 1, that is 24 into 1 upon 8, that is simply 3. There is another way to solve this as well, right? Using basics. So you can choose this node to be C1, C2, and you can write equations here. So I can write this equation that my C1 will be equals to 2 into R1, because I am multiplying 2, gain 2 with R, not R1, sorry, R. And of course, C1 into minus 1, because these two, at this particular node, what is incoming? These two values, right? What is outgoing? C1. C1 is the outgoing. So C1 is equals to 2 into R minus C1. Okay, from this I can get the value of C1. C1 would be equals to R. So this value actually is R. Now what is C2? C2 is equals to 3 into R and minus 3 into C2. So your C2 is 3 by 4R and your Y would be equals to 4 into C2, right? The incoming value basically. So Y will be equals to 4 into C2. So this will be 3 into R. That's all. That is what your Y is equals to. So it is pretty simple, not that difficult to understand. So yeah, that's all. So Y by R is what? Y by R is 3. Okay, that's all. Y by R is 3. So that's how you also can solve, or you can simply solve using Mason's gain. Now there is another problem. If I have any, like, this is fine, but if this loop gain becomes 1, then there is a problem. How? So if this loop gain becomes 1, right, then if I write the equation here, this will be plus 1 into C1. So C1 will automatically be gone. So R will be equals to 0. That is not valid, right? So R is any input. So R is set to 0. So R becomes 0, then your Y upon R tends to infinity. So which is wrong, correct? So that is the problem basically. So that's why you cannot have a gain of 1. Now here, if I have any gain at the input node, that is invalid. Okay, any gain at the input node is also invalid. So you must remove this self loop in the input side. You must remove it, otherwise you will not be able to solve it. So if I write the equation here, right, so you have to, this is the rule. So if I write the equation here, this will be what? This will be R is equals to, what is incoming here? Minus R, correct? So 2R becomes 0. Again, it is a problem to us, correct? So any gain you provide here, R is set to 0. If R is set to 0, this ratio will go to infinity. Problem. So you must remove the input loop. Anyways, they will not give you these kind of questions, but there can be a bit of problems for solving Mason's gain. So if there is any input node right, with this self loop, remove it, or what you can do, the better approach would be to take an additional node here, as I was doing. You can take an additional node. That's all. That is one thing that you can do. Okay. So these are the two things that you must keep in mind. So I think you can find y by r. I will not solve y by r. That is the homework for you. Okay. Put in the comments below what will be y by r in this case. Pretty simple, pretty straightforward. If you remove this, right, y by r is simply 6, right? Not 6, sorry. Y by r is simply 24. Not much to think. If I remove this loop, so it will be 20. So 6 into 4, yeah, it will be 24. That's all. It will be simply 24. Okay. So yeah, now let's start. So here the same thing is written over here. We have to remove the loop, and like then you can solve. Like this is a different question, so I have solved a different question. That's all. So now let's start with the gate PYQs of signal flow graph and block diagram reduction, and this will not be very difficult. It will be very simple. Trust me. Okay, this is the first one. Which of the following options is equivalent representation of the signal flow graph shown here? Okay, equivalent meaning all of them should, these to have same transfer function, right? If they have same transfer function, then they are said to be equivalent. Okay, is and they have asked only a single, so only it will be single, correct? So what is the transfer function here? So what is the forward path gain? So for I have only a single forward path. I don't have any other single forward path. So P1 is equals to AD. What is delta 1? Delta 1 is equals to, so delta is equals to 1 minus ADE. ADE, this is my loop gain, one of the loops. I have one loop here, right, another loop here. So ADE and DC, right, plus DC. That's all. And do I have any isolated loops? No, none. So basically, and what is delta 1? If I remove this forward path, will I have any loops left? No. So it will be 1. So your transfer function would be P1 into delta 1 divided by delta, that is 1 minus ADE plus DC. That is what your transfer function is, and I should be able to get the same transfer function out of here as well, right? So if I see here, again I have a single forward path gain. So this forward path is A into D plus C. So I will never get A into D plus C, right? That is not valid. So anyways, this is anyways gone. Okay. If for some reason D plus C will be cancelled, then I can think, but just how I can think in the option. So here also I will not get A plus C into D. No. But this can be possible, right? This is possible because I am getting here A into D 1 by C minus D. This is a possible answer because I am getting A into D. A into D. I am getting A into C. No. So option C will be a correct answer. Okay. Of course, you can solve it. No problem. Let me solve it as well. Correct. So if I solve it here, again, what is the forward path gain? Only this is the forward path. So it is A into D by 1 minus C into D. Right. What is the delta 1? It is 1. Because if I remove the forward path, I will not have any loops left. What is the loop gain? It is this loop only, right? This ADE by 1 minus C into D. So delta would be equals to ADE. So I have basically 1 minus ADE by 1 minus CD. That's all. So if I solve this, right, forward path will be AD divided by 1 minus CD. This will be 1 minus AD 1 minus CD. So this will be AD 1 minus CD minus ADE, which is exactly same, right? This only. Actually, this should be negative, right? Don't forget, I have a negative sign here. So yeah, so option C is matching. So option C will be correct. So I have solved using lengthy method. Obviously, I have told you how to eliminate the options as well. Let's solve the next one. So yeah, let me solve this one. So the block diagram is shown, the transfer function would be what? Very simple, right? Again, don't do anything, right? Just assume whatever is unknown. So this node is unknown to me, right? So assume this to be x. So if this is x, right, this will be h into x. And okay, I'm stuck here, h into x. So if this is x, right, what will be this node? This will be x by g1. So you can do that basic thing, right? You can assume here y, and then write y into g1 equals to x. So the y will be x by g1. So you can do that, right? You can do that. So this will be x by g1 only. Now this is x by g1. Interesting. What will be this? Okay, it's x. Okay. So one thing is there, right? So I am adding these two and I'm getting x by g1, correct? Because this is the output. This is just the output, right? These are the summers, subtractor, and these are, I'm just taking the output here, right? So x. Okay, sorry. They have already given here x, right? So you cannot assume x here. So just be careful. You can assume anything else. What shall I assume? A. Okay. Just assume any other variable, right? Don't assume x because x is already given to you. Otherwise, there will be confusions. Okay. So if I add these two, right, I'm already getting this, right? Because this is the output of the subtractor. So x minus h into a. Remember, h is h. So basically, remember, a is a of s, right? That is understood by you. So h into a is equals to actually a by g1. So this value is actually a by g1. Anyways, I don't need to solve for a, but you can solve for a. That is also fine. So this output is actually a by g1. So this will be also a by g1 only. Same output, right? A subtractor will give the same output. It cannot give different output. Okay. So this will be what? This will be a into g2 by g1. So basically, first of all, I can write my, what is this equation? I can write my a in terms of x. So x will be equals to a, if I take common, this will be 1 by g1 plus h1 so okay, so my a is equals to actually x into g1 upon 1 plus g1 h1. Okay, and this value, right, if I'm adding these two values and this is my output, so y is equals to a plus a into g1 upon g2 upon g1. So this will be a into 1 plus g2 upon g1. That's all. Okay, and I already know what is my a is equals to x into g1. So okay, interesting. So why is this a g2 by g1? Okay, I'm just thinking. Okay, so y by x will be equals to g1 by 1 plus g1 h1 into g1 plus g2 by g1. Okay, so g1 will be cancelled. It will be g1 plus g2 divided by 1 plus g1 h1. g1 plus g2 divided by 1 plus g1 h1, that is present in option C. So your option C will be the correct answer for this question. Like I've just solved this in a small rough way, but I hope we can solve it, right? Just solve simply the block diagram reduction, assume variables, and you will get your output. There should not be any problems. Okay, so let's solve the next question. For the closed loop system, so what is the transfer function, correct? So the transfer function E by R, it's very simple, right? Okay, they're not asking you C by R. They are not asking you C by R. They're asking you E by R actually. E by R, okay? They're not asking you C by R. So be very, very careful. So interesting. So what is this node value? This will be E into G. This node value is E into G. This node value is E into H into G. So what will be the output of the subtractor? R minus E into G into H, that is equals to E. So E into 1 plus GH equals to R. So E by R, that is what they have asked, is actually 1 upon 1 plus GH. It is not G upon 1 plus GH. They have given this option as well. It is 1 upon 1 plus GH. So option C will be your correct answer for the question. Pretty simple and straightforward. Let's solve the next question. The signal flow graph is shown the expression of y of s upon x of s. Again, we can simply use the Mason's gain formula. How many forward paths do I have? This is one forward path. This is another forward path. And remember, the arrow is here, this side, right? So this is not a forward path actually. Not, because arrow is on the opposite direction. So I have two forward paths. How many loops I have? So this is a loop and this also is a loop, correct? So I have two loops. One loop is this, right? Another loop is this. So P1, what is P1? P1 is G1, G2 into 2. That's all. P2 is G1, G3 into 2. Okay. P1 is G1, G2 into 2. P2 is G1, G3 into 2. Now, yeah. Now the thing is that what about the loop gain delta? What is the loop gain delta? It will be 1 minus the loop gains basically. So this loop is G1, G3 into minus 1. So it is minus of G3 plus this loop is G2 into minus 1. So it is minus of G2. So do I have any isolated loops? So if I remove, so if this loop is covered, right, already I am covering the two nodes of the other loop, right? So I don't have any isolated loops. So it becomes very simple. It is simply 1 plus G2 plus G3. So it is 1 plus G2 plus G3 and these are my forward path gains. So basically it will be 2 into, now what is delta 1? If I remove this forward path, sorry, this is my delta 1, right? This is my P1. If I remove this forward path, will I have any loops left? No. If I remove this forward path, will I have any loops left? No. So simply this will be gone, right? This will be gone. So it becomes very simple, right? Delta 1 is simply 1, no loops. Delta 2 is also simply 1. So simply it will be P1 into delta 1 plus P2 into delta 2. So it is 2 G1 G2 plus 2 G1 G3 divided by the delta, that is 1 plus G2 plus G3, that is present in option A. So option A will be your correct answer for the question. Pretty simple and straightforward. I hope I don't need to spend much time around this. Okay, let's move on to the next question. So in the following block diagram, R of s and D of s both are inputs. The output y of s expressed as a sum of G1s into R of s plus G2f into D of s, then the value of G1 and G2s are given by what? Okay, they have not given you the options, unfortunately. So yeah, I have to solve it myself. So basically, right, whenever you have this Mason's gain formula and whenever you have multiple inputs, you can calculate the ratio of y of s by R of s by making one of the input to be 0. What do I mean by it? So if I make D of s to be 0, what will be y of s upon R of s? It will be G1. If I make my R of s to be 0, my y of s upon d of s would be g2. So this is a response due to r of s. This is a response due to d of s. As my system is LTI, linear time invariant system, I can use the property of linearity. So overall my output, I can use superposition. My output will be summation of g1 into rfs, right? Because this is my initial output due to r, right? That is r into g1, and this is my another output, that is d of s into g2. Okay. So yeah, g1 rfs plus g2 into d of s. That's all. Okay. So yeah, we will use the same thing basically. So first of all, I will calculate r upon y when this d is 0. So if this d is 0, right? If this d is 0 here, this node is y. So this node will be h into y. This node will be simply y because this node is the same node, correct? So this node will be r minus y, and this node is 0, right? So this will be r minus y minus y into h. So r minus y minus yh into g will be my y. So I can use that. So r minus y minus yh into g is my y. So now I can say that rg equals to 1 plus g plus gh. So y upon r equals to g upon 1 g gh. So this is my g1 basically. Okay, this is my g1. I got my g1, g upon 1 plus g plus gh. Okay, you can match the options. I forgot to, I think I forgot to take the screenshot of the options, unfortunately. So this will be in one of the options, y upon r. So I will write it properly actually because then you will say, sir, सही से नहीं लिखा आपने सर, ऑप्शन नहीं मैच कर रहा सर, एस नहीं था सर, एस नहीं था सर, क्या कर रहे हो सर, एस नहीं था. So I will write it properly. I know you will be confused. So it will be g of s upon 1 plus g of s into h of s plus this was what? This was g plus h, yeah, plus g of s. Okay. So this is one of the options. What about g2? g2 of s, right? So g2 of s would be equals to yeah. So for that again I'll just delete all these things. Now I will make r of s to be 0. This will be still valid actually. Sorry, this will be still valid, this will not be valid. Okay, now I will make my r of s to be 0. So r of s is 0. So if this is 0, correct, then this will be simply minus of y, right? This input is 0, right? So this is r minus y, r is 0, so this is minus y. This will be minus y minus yh plus d. D is here, d is not 0. So d minus y minus yh into g would be my y. So d minus y minus yh into g would be my y. So y upon d. So okay, just solve. Let me solve it. This will be d into g minus minus y into g minus g yh equals to y. So y by d is equals to y by d is equals to this. So that is g upon one plus g plus gh. It is same actually. Okay, that is interesting. Both are same. So this is equals to my g2 as well. Okay, that is interesting. So both are same, coming out to be same. So this will be your answer. Both of them will be equal. Okay. Let us solve the next question. This one. For the block diagram shown in the figure, the transfer function y of s upon r of s is this. Correct? Okay, what will be the transfer function? So again, we can use simple things here. So we'll assume this to be y. So this node is y, right? 1 into y is y only. So now this node is r. This is also r. So this will be 2r. This will be 3r. So this will be 2r plus y. So 2r plus y into 1 by s. So 2r plus y by s. So this will be 3r plus 2r plus y by s. So 3r plus 2r plus y divided by s, and yeah, that is equals to my y. So okay, so if I take common r, this will be 3s plus 2, and if I multiply this over there, this will be s minus 1 into y. Interesting, I'm getting a pool on the left hand side, so right hand side. So y upon r would be 3s plus 2 upon s minus 1. Okay, so your option B would be correct for this particular question. Pretty simple, straightforward. I don't feel I have to explain here much. Okay, mostly block diagram reduction are these only. Okay, very simple, very easy. So again, you have to solve for c by r. Again, very simple, right? Not that difficult. So this is your c. This will be c. This will be c. This will be r minus c. This will be r minus 2c, because already r minus c is there. Okay, this is already getting subtracted, right? So don't mess this up. So minus of r minus c plus c, because this is getting added. So actually this will be 2c minus r into g. So 2c minus r into g is equals to c. So okay, c will be 2g minus 1 equals to r into g. So c by r would be equals to g by 2g minus 1. Okay, g by 2g minus 1, g by 2g minus 1, but it is not present in the option, right? G by 2g minus 1 is not present, but g by 1 minus 2g is present. So what I can do is I can take the negative sign as common. So if I take the negative sign common here, this will be minus g upon 1 minus 2g. So minus g upon 1 minus 2g is present in option D. So option D is your correct answer for this question. Let's solve the next one. This is the next question. Consider the system represented by the block diagram shown below. Which of the following signal flow graphs represent correctly? So again, you have to compare which of the following signal flow graph represents. So it is a multiple select type question. Basically, again you have to say, like, equate the transfer functions. Whosever transfer functions will be same, then that will match. So it is a multiple select, so unfortunately I may have to solve for all of them. So first of all, let me write what is the transfer function here. Okay, so first of all, what do I see? If I see this and this signal flow graph, right, these are exactly identical. So this option B is anyways correct, right? It is just the representation. So option B is anyways correct. Okay, it is matching exactly, no problem with that, right? What about for other options? What do I see for other options? Okay, so option B is matching. If it's a single correct, then that is your answer. But if it's a multi correct, right, then you have to further solve it. Okay, so what is the transfer function here? So this would be basically here, if I have x, this will be x into g1, and okay, and this will be x by g1 here. Okay, this will be okay. What is my x? So r minus x into g1, r minus x into g1. Is equals to, this value is x by g1, right? X by g1. Okay, sorry. So this node is x only, right? This is x only. What I'm doing, this node is x. Okay, yeah, is equals to x by g1. So r x into g1 plus 1 divided by g1. So x is equals to g1 1 plus g1 into r. That is what my x is equals to, and this value would be x plus x by g1, sorry, x plus this into g2, right? This into g2. So g2 by g1 into x. That is what my y is equals to. So my y over x, or y is equals to, I can replace my x with r. This will be 1 plus g2 by g1 into, this is g1 by 1 plus g1, correct? Okay, so if I multiply this, g1 will be cancelled into r. So y by r would be actually equals to g1 plus g2 upon 1 plus g1. That is what your y by r is equals to. Now I have to actually solve. It will not take you much time because these are easy only. So what about this one? So I will solve in a quick manner. So what is the forward path? I have two forward paths, and of course I have loops. This is one loop, this is another loop. I think we have solved a question like this. And of course, like there is no delta 1 is 1 basically, right? Delta 1. So p1 is g2. Let me write g1 only, and p2 is g2. So this is p1, this is p2. Okay, delta 1 is 1, delta 1 is 1, delta 2 is 1. Delta is basically 1 minus this loop gain minus g2, that is plus g2, plus this loop gain, right? Plus g1. So yeah, now if I solve it, right, Yeah, if I solve it, this will be g1 plus g2 upon 1 plus g2 g1. That is wrong actually. That is wrong, right? G1 plus g2 upon 1 plus g1, not g2 plus g1. So this is gone. So yeah, this one also will be kind of similar, only instead of 1 I have -1, that's all. So what will happen is, okay, both these loop gains will be basically negative, sign will change. So this will be g1 plus g2, let me do g1 plus g2 upon 1 minus g1 g2. This is also wrong. And here if you solve this, what is the forward path gain? I have two forward paths. One is this g1 path, one is this g2 path. So g1, what is delta 1? Delta 1 will be simply 0, right? 1. So delta 1 is 1 plus g2, and delta 2 is also 1 only, right? What is delta? Delta is, I have how many loops? This is this a loop? No, this is not a loop, but this is definitely a loop, and this is also a loop, right? So this will be 1 plus g1 plus g2. Again it is wrong, right? g2 plus g1 divided by 1 plus g1 g2, that is wrong. I just need g1 in the denominator, 1 plus g1. So again it is wrong. So of course option D is also not correct. So option B will be only your correct answer for this question. I don't know whether it was MSQ or MCQ, but with that we are done with SFG and block diagram reduction. Now we will start with the most important topic, time domain analysis. Let's start with time domain analysis. Also sometimes it is called as time response. Okay, response in time domain with respect to the input, right? So there are a few points that I want to go through first. So time response basically means how the response behaves in accordance with time when a specified input test signal is provided. Generally, either it will be an impulse signal, and mostly it will be a unit step signal. Okay, so the time response of a control system is a combination of transient and steady state. So of course, if you have seen this waveform, right, I have this simple RC circuit, and the voltage output, I have this curve. If I am providing it a unit step 1 volt, the curve would be somewhat like this, right? So this particular state is actually called as the transient state, and this particular state is actually called as the steady state. That's all. Okay. So yeah, the transient part of the time response reveals the nature of the response, oscillatory or natural. So what will be the nature initially of the response, and also gives an indication about speed, basically how fast will it settle to. The steady state response reveals the accuracy and the steady state error. So basically how fast I will reach to a stable point, that is what the transient part tells me, and what is my stable point, and how far I am from my reference, that is what my steady state part will tell me. Okay, very important points. So I can show you a few things like this, right? If I am providing a unit step, so unit step, this has two components. The voltage waveform, if you write the voltage waveform, it will be 1 minus e raised to power minus t upon tau, okay, which is 1 t upon RC into u of t. So it is made of two components. This is the steady state component, and this is the transient component. Steady state meaning at t equals to infinity, what is the value of the output? It is 1. That is why it is called as the steady state component. And this part is transient because it is changing, right? Initially the value is dominated by this, like how the change goes and how fast will it become 0. That will determine the speed of the system, right? If it goes to 0, I will settle at a much faster rate. Okay, so these are the few things. Next, there is type of the system. What do I understand by type? Why is it important? It is important regarding error. Okay, that obviously will be discussed later. But the definition of type of a system is simply the total number of poles at the origin in OLTF is called as the type. That's it. Or type of any particular function, right, will be simply the number of poles in origin. So let's say h of s is equals to s plus 1 upon s plus 2 S plus 3. What is the type of the system? It is a type 0 system because it does not have any poles at the origin. Now similarly, if I put a S here, this will become type 1 system. Okay. Now sometimes what happens, generally type is defined for OLTF, generally, most cases. Okay. But sometimes they will just give you this value and they will ask you the type. Nothing will be mentioned, right? Then you will assume they are talking about this is my OLTF. Then you will assume that this is my OLTF. But let's say if specifically they mention that this is your CLTF, closed loop transfer function of a negative unity feedback system, then from this CLTF you will find out your OLTF, and then you will identify how many poles are at the origin, and then you will comment whether it is a type 0 system, type 1 system, type 2, whatever it is. Got it? So if they don't tell you anything, just give you this h of s equals to this and they ask you type, so you just directly see how many poles are at the origin and then you will say accordingly. But if they tell you h of s is a generally in gate, it will be very standard, so they will tell you that h of s is a closed loop transfer function and you have to find out the type of the open loop transfer function. And generally we discuss about type for OLTF only because it gives us the intuition behind steady state error. That is why type is very important. But generally they will tell you, okay, this is my closed loop transfer function, can you please tell me what will be the type of the OLTF? But even if they don't tell you, then also actually you should always comment about the open loop transfer function only. And don't worry, in gate they will specifically tell you which, like for what function you have to calculate the type. Don't worry, in gate this confusion will not be there. In other examinations this confusion will be there because type is generally associated with OLTF. Now order, what is order? Order basically means the overall number of poles of a closed loop transfer function, or you can say order of a system, right? Order of a system. Type of a system is defined by the number of poles at the origin of OLTF. If they ask you, now also in the question, if they ask you what is the type of the system, a negative unity feedback is given and simply they are asking you what will be the type of the system. Simply you will calculate the OLTF and you will say what is the type of that OLTF, right? How many poles are at the origin of the OLTF, that's it. Okay, so this is how you can calculate the order as well. Order of a system will be the total number of poles of CLTF. Highest order of the denominator of closed loop transfer function will yield to the order of your system. Okay, that's all basically. So yeah, transient I have already discussed, like how the transient part this happens. So we will provide different kind of steps inputs, not steps, sorry. We'll provide different kinds of test signals as the input. Okay, you see here I have block diagram, right? This is my input, this is my output, this is my feedback. So we can provide different kinds of input. So we can provide impulse input, okay, impulse signal, sudden shocks. We can provide step signal, sudden jump. We can provide ramp input, which will increase linearly. The input is increasing linearly. Or we can provide parabolic input, which generally is not discussed, and we'll discuss about this, but generally in exam very rarely it will be asked. Also we will provide sinusoidal input, that is not mentioned here. We can also provide sinusoidal input. Okay, that will be done in the frequency, that analysis will be done in frequency domain, frequency response part, and now we are approaching it with the time domain. I hope that part is clear. Yep. So let's analyze a basic first order system. Okay, if I have a basic first order system, if we solve the basic differential equation, you will see the transfer function will come out to be this, right? If I have this 1 by s tau, okay, as the OLTF, it is a type 1 system, so it comes out first order type 1 system. This is my closed loop transfer function, and I see that I have a pole at minus 1 by tau. Basically it is a stable system. So if I am providing an impulse input, right, the response would be somewhat like this. Response would be, for impulse input, the output will be this. Okay, it will be a decaying exponential, so which is fine. That is the impulse response. So this is called as the impulse response of a first order type 1 system. Okay, now if my poles were on the right hand side, then of course it will go unbounded. This we already know, this we have already discussed. Okay, so basically for a system to be stable, right, the impulse response should be absolutely integrable. What do I mean by absolutely integrable? Basically, if I'm integrating my impulse response, that is c of t dt mod of c of t magnitude from minus infinity to plus infinity, it will be some finite value. Okay, it should not be infinite. That is what we mean by absolutely integrable. Then only my system will be stable. So in simple words, your impulse response must die down, otherwise your system will not be stable. If instead of 1 by s plus tau I would have had 1 by s minus s tau, then I would have seen that this is my response. Okay, and if I integrate this, right, I see the area is only increasing, it is never reducing, it is only increasing, it keeps on increasing, correct? So if it keeps on increasing, then that is a problem. It is not absolutely integrable, then it is not stable, it is unstable. It is not stable, it is unstable. Okay, yeah, that's all basically. Now I think yeah, now how to find out the step response. So we know what is the impulse response. Step response will just be the running integration. So 0 to t is called as the running integration with respect to of impulse response with respect to time. That's all. Okay, so yeah, that is what my step response is equals to. So if you solve for the step response, you will get this value. Now there is one thing actually, you'll put here t equal to 0 and t equal to 1. How? If I put here t equal to 0, this will come out to be 1. Yeah, 1 by tau. Yeah, if I put here t equal to 0 and t, like this will be the response. So this is my steady state and this is my transient, already have been discussed. So if I am providing a step input, the response is somewhat like this. It is also settling to total 1. So if the input is 1, output is also settling to 1. Okay, this is for a negative unity feedback. So there is no steady state error. Steady state error basically means this particular point, right? E of t. What is the difference? R of t minus C of t. That is my E of t. Steady state basically means when t is infinity. So at infinity, what is the difference between the reference points? It is 0. So for a simple type 1 system, first order type 1 system, the steady state error is simply 0. Very simple, not that difficult for us to understand. That is my steady state error we have already discussed. You can see the definitions here, and I will of course come to this all these points. Now in the time domain it is this, right? So what if I convert this into Laplace domain? Because what I have to do, I have to find out E of infinity. So somehow I can use the final value theorem. If I use the final value theorem, that means I can use this limit as s tends to 0 s of E of s. That is equals to what? What is E of s? E of s is nothing but R of s minus C of s, because I have here R and this is a subtractor, and here I get the C for a unity feedback. This is valid for a unity feedback, right? This particular formula is valid for a unity feedback. And don't worry, I will teach you for non-unity feedback as well. Don't worry. So non-unity feedback as well I will teach you. So this will be S into R of S minus C of S. Now what we do, like we define a formula, don't need to remember this formula. Ignore this formula, okay? Just remember this till this point, that's it. Okay, no need to remember the formula. So yeah, if you see, like the steady state response for a step, like steady state error for a unit step input will be 0. Okay, you can solve it using this final value theorem as well. You will see that you are getting 0 as well here as well. Okay, you can see the calculation. I will not go through the calculation because that will just waste our time. Now for a ramp response though, if I am providing a ramp response, actually here the steady state error will not be 0. You will see, that is interesting. And first of all, your input this time is not a stable input. It is also a unstable, because ramp, right? Ramp is also not bounded, right? You're always increasing. So that is again not possible, but still we're assuming that we're in an ideal world and I'm providing a ideal ramp. So if I'm providing an ideal ramp, yeah, if I'm providing an ideal ramp, what happens if you solve the response, right? You will see that you're getting, like you can solve using partial fractions. The response would be somewhat like this. Okay, So your output is also not stable actually. It is also always increasing, right? So it is not stable. Anyways, your input is not stable, so output also will not be stable. Okay, of course you are not providing a stable input. How will your output be stable? You're always increasing your input, right? So that is the thing. Or you can, what you could have done, you could have simply integrated your step response. If I would have simply integrated my step response, I would have got my ramp response instead of solving using Laplace domain. That is what I have done here. You can see, and I'm getting the same exact value, carbon copy, right? What will be the steady state error? It will be R of t minus C of t. So R of t is TUT, C of t is this value. If I subtract, I'm observing that around t equals to infinity, right? When t is tending to infinity, there is a error of tau that can be seen from this particular graph as well. Okay, so your response is this and your input is this. So if we are always increasing your input, let's say I have AC and I am always increasing the temperature from 10 degree to 11, 12, 13, 14, 15, 16. I'm increasing my temperature. Okay, so although the output also will try to reach to 10 degrees, 11 degrees, but there will be always a lag, right? Because the moment AC will reach 11 degrees, I have pressed the button for 12 degrees. So there is a lag. It will never be able to reach the exact value. It has to predict. It has to predict, right? If I want to reach to, let's say, like next I will press 12 degrees. So AC has to predict, okay, Anish wants to go to 12 degrees. So instead of going from 10 to 11, I will directly go to 10 to 12. That is the prediction here. Now let's discuss about parabolic response. Although this is not important, like if I give some parabolic input, right, then what will be the response? Again, you can integrate the ramp response and you will get the parabolic response, or you can simply solve using Laplace transform. That is up to you. Okay, like that is not important to us here, right? Our error will be unbounded actually. Here our steady state error was something finite, tau, correct? And before that our steady state error was 0 in case of a step input. And for impulse input, we don't compare the steady state error because anyways our input is also 0, right? Input is also 0 at equal to infinity, so it does not matter ultimately. So yeah, it will be 0 basically, right? So we can see the comparisons here. For impulse input, this is my response. This was like I had no error because we don't talk about error in case of an impulse response, and we don't talk about steady state error as well because there is no concept of error, right? Because you are just giving an impulse. You are not comparing the input and the output because you are just providing a signal just at t equal to 0. That's it. So there is no comparison between input and output, right? In case of a step input, you are always constantly, you provided a jump and that input is always there, correct? So this is your output and this is your error signal, e raised to power minus t upon tau, and your steady state error would be 0, right? In case of ramp input, like there was a error concept here. Our error signal was this, right? If you compare the input and the output, error signal was this, R of t minus E of t, that is R of t minus C of t. This is my C of t, right? This is my error signal. So error signal is R of t minus C of t. Now this error is defined for a unity feedback system. For other kinds of feedback, when it is non-unity negative feedback, there is a different concept of error that we will learn later. Okay. So for parabolic input, there is no like error will be infinite. The steady state error would be infinite because your error signal is unbounded. It is not bounded. Okay. So mainly there are two parameters of a first order system. Okay. The two parameters are this, b by 1 plus s tau. B is the descent of the transfer function and tau would be basically the time constant. Right? For a first order system, mainly I have two parameters. Yep, that's pretty much it. So first order system with, now there are few variations. Basically, if I provide some time delay, if my transfer function, right, has some time delay, what will happen? Then, right, you cannot like this will be, this is first order, but actually this, right, will also provide some poles. Actually, if I do some approximation, that is called as Paide's approximation. You can search, look it up. If you do it, like basically it will behave as a second order system. So if I have some time delay, right, if I add some time delay, so I have two parameters, tau, b and all these things. If I add some time delay, then it will behave, the response would be as if it's like a second order system. So you don't have to worry about this. Mainly, like all these things will be asked. Don't worry. All these things won't be asked. So don't worry about these things. Okay. So yeah. So one more thing is there regarding the final value theorem. So we use final value theorem, C of infinity, and C of infinity is actually nothing but the steady state DC gain of the signal of the transfer function at when it is given in Laplace domain, right? So DC gain actually is basically C of infinity will be equals to C of 0. Now you will get confused, how is C of infinity is equal to C of 0? So C of infinity is written in time domain and C of 0 is written in Laplace domain, frequency domain. So when S is 0, it is same as infinity. It is similar to the final value theorem, right? We use the final value theorem, somewhat similar to the final value theorem. Okay. So, but not always the case, but just there is a relation. There is bit of relation. How? So if I say what is the steady state value of my output here? So let's say if my input, right, has a DC gain of B. Sorry, if my transfer function has a DC gain of B, right? And input I'm providing unit step, so it has a gain of unity. So what is the steady state output? It is B, right? Steady state output is B. Now what is the DC gain? It is B. So in this case we're lucky. In this case we're lucky that our DC gain is equals to the steady state value. That's why sometimes we say that C of infinity will be equals to C of 0. Basically C of 0 means when S is equals to 0. If I put S equal to 0, the DC gain, that is B. But this will not always be the case. This will not always be valid. This case, this time it is valid. Okay, but it will not always be valid. Also you can understand it like this, that this is valid only for a step input. This thing is valid only for a step input, right? Why? Because if I write R of S, right, it will be 1 by S, and if I use final value theorem, I will multiply S into 1 by S into the this transfer function, and that's why this S term goes away. So ultimately now I have to put S equal to 0, that is nothing but the transfer function equal to 0, that is nothing but the DC gain of the transfer function. This is the only reason why the DC gain is equals to the steady state value. But trust me, all other educators will just tell you DC gain equals to C of infinity. They will just tell you to mug this up, but this will not always be valid. So be very careful. You don't need to remember it. Just understand, okay, I am using final value theorem for unit step response. Okay, something like this can happen. Just keep this in your mind. That's all. Okay. So yeah, that's pretty much it basically. So then I have C of infinity is equals to limit as S tends to 0. So these things are there. Okay, these are already done. Okay, that was one thing. Now settling time. Settling time is basically when the output is around 2%, reaches 2% of its desired value. Let's say what is my desired value here? B, right? So if my output, right, of course I will reach B at infinity. We know exponential, it will never reach steady state. It will reach steady state at infinity. So we say it is very close to B, like 0.98 to B. Then we say it has settled. So the time at which it will reach to 0.98, that is actually called as the settling time. For a first order system, it is simply 4 tau. Very simple. For a unit step in response, it is simply 4 tau, right? It will reach steady state at 4 tau. Very simple, easy to understand. You have already learned this in transient. So I hope I don't need to explain much stuff here. Okay. Now there is bit of analogy between resistor and okay these things. So we'll ignore this actually. This is not required. This analogy is not required for us. Okay. Yeah, but this thing is required. So what happens if I have a simple RLC circuit, second order RLC circuit? If you solve the differential equation and or if you solve this in Laplace domain, so your VO of S over VI of S, the transfer function that we will get is this one. So this is my input VI of S. I'm providing a voltage input. It can be step input or it can be anything, and I'm getting a response at the output. That is the voltage across the capacitor. The transfer function is this. Now this we compare with a standard second order system. The differential equation is of a second order system is this standard. No need to remember it, won't be asked, but this is very important. Very important. The transfer function of a standard second order system. You have to remember it. It will be used everywhere. This is the transfer function of a standard second order system. Now, if my system is a negative unity feedback, unity gain, like negative unity feedback system, if my transfer function is a negative unity feedback system, then I can compare the OLTF. The standard OLTF of a second order system would be like simply omega n square will go away. It will be omega n square upon a square plus 2 zeta omega ns. This is the standard OLTF of a second order system. Very, very important. What is zeta and omega n? I will explain. Don't worry. Zeta and omega n are parameters. Okay. And remember, standard meaning here the DC gain is simply 1. If you put s equal to 0, the DC gain of a standard second order system is 1. Okay. Now what is called zeta? This is called as zeta. Zeta is called known as the damping factor, also called as the damping ratio. Why damping? Because if I calculate the impulse response of this, it will be a damped sinusoidal. We have already solved impulse response for this. Like here, right? If my roots are complex conjugate, then basically the waveform, the impulse response would be a damped sinusoidal. So depending on the value of zeta, because it will be e raised to power minus zeta omega n t into sine of omega d. What is omega d? I will explain. Omega d is the frequency of oscillation, damped frequency of oscillation. So like if I solve for this, right, I will get the impulse response to be this, which is a damped sinusoidal. So the amount of damping, basically by which the waveform will contract at a very fast rate or a slow rate, that will matter on the value of zeta. It depends on the value of zeta, correct? So it depends on the value of zeta. So yeah, so now that's why it is called as the damping ratio or damping factor. Higher the value of zeta, more damping I will get. Okay, this is factor 1. Now what is omega d? So omega d, like of course I will show you the formula later on. Omega d comes out to be 1 minus zeta square into omega n. Now you will say, sir, you are just telling me so many unknowns. Yeah, these are very, very important things. So you have to listen to me very, very carefully here. Okay, these are important. This you cannot neglect. Okay. Now omega d is called as the damped frequency of oscillation. Why? Because of course it is not normal. Like, okay, let me first explain what is omega n. Omega n is called as the natural frequency of oscillation. Natural frequency of oscillation. So what is natural? Whenever there is no damping present. When there will be no damping present, if zeta is 0. So if zeta is 0, this exponential term is gone. So my waveform will oscillate like this. There is no zeta. Correct? So now there is no zeta, so it will oscillate naturally if there is no damping present. That's why it is called as natural frequency of oscillation. Now if there is some damping present, then the frequency of oscillation changes actually depending on the value of zeta. So we say that this is called as the damped frequency of oscillation. This is the formula for damped frequency of oscillation is this multiplied by the natural frequency of oscillation. All these things will be written, don't worry, and we will use this formula multiple times everywhere in control system. Everywhere these formulas will be used, so you have to use these formulas. Okay. So these are the things here basically. So yeah, now the denominator, if I put this denominator equals to 0, this is called as the characteristics equation of my system. Very, very important. These are all very, very important things. Characteristics equation of the system, and the roots of this are called as the poles of my system, also called as the eigenvalues of the system. Many names. There are many names for this. Very, very important. Whenever this goes to 0, very important. So here I have derived the OLTF basically. You can see what will be the OLTF. This is my transfer. So OLTF is this for the standard second order system with unity negative feedback. Okay. So if let's say that the DC gain of the standard second order system is not equals to 1, then simply you write k. So k is not equals to 1, k will be some other value, whatever is the DC gain. So my transfer function, second order transfer function, is a function of DC gain. It is a function of the natural frequency of oscillation. It is a function of the damped frequency. Okay, I can add a time delay as well, but don't worry, we will not study regarding this. Okay, and my system will be stable if and only if my zeta is greater than 0 and my omega n is greater than 0. Otherwise, system will not be stable. Both zeta and omega n must be greater than 0. Okay, this is very, very important condition. both zeta and omega n must be greater than 0. Let us solve a bit of quotient. For the transfer function, find the damping factor or damping ratio, whatever, and the natural frequency. Pause the video and try to find the damping ratio and the natural frequency. So here, if I see for the first one, right, simply the transfer function is given. What was my, let me compare it with my standard second order system. It is k omega n upon s square plus 2 zeta. This should be in your brain always. 2 zeta omega n s omega n square. Okay, so if I make if I compare, right, I see omega n square equals to 400, so omega n would be 20 and 2 zeta omega n equals to 10 and omega n is already 20, so zeta comes out to be 1 by 2, sorry, 1 by 2, 20, this is right, 10, 1 by 4, zeta comes out to be 1 by 4. Okay, what about other cases? So for this case, again your DC gain k is 1, DC gain is 1, so k is 1 actually. Omega n comes out to be 4 here. Okay, but remember this is not in standard format, right? I have coefficient of s square to be 1, that is my standard format, but here I stopped because I see coefficient of s square is not 1. So what I have to do, first of all I have to make coefficient of s square to be 1, correct? So I will take common 4 from the denominator, so this will be 16 by 4, that is 4 upon s square plus 2s plus 4. Now it is fine. Yes, now it is fine. So yeah, now again the DC gain is 1, so k will be 1 and your omega n is 2, your zeta 2 zeta omega n is 2, so yeah, zeta is also 0.25 again, same, zeta does not change, it is 0.25. Okay, I hope I'm correct. 2 zeta into, sorry, so it will be 1 by 2, right? 0.5, zeta is 0.5. Okay, and here in this case, okay, hold on, again this has some sort of problem, I don't know, should be very careful, like this connection is very loose actually, that is the only issue. Yep, so I was here. So for the third case, is this my standard format? This is not in my standard format, so the response will be different basically. So what I can do, I can break it down. So 4 upon s square plus 2s plus 4 plus s upon s square plus 2s plus 4. Now I know the response of this, it will be like a damped sinusoid because here both zeta and omega n are positive, it will be like a damped sinusoid. Now what will be the response of the second signal? Now this, right, I have multiplied s, so it will be just a differentiation of this response. So I will just differentiate this and I will get this response, but this is not a proper standard second order transfer function, so I cannot comment upon zeta and omega n because ultimately I will add two signals and for them, right, there I will get something else. What about this one? Here again, is this in standard format? Yes. What is your omega n? Omega n is 1 by under root LC. Do you remember what was this in a simple RLC circuit? This was the resonant frequency. What is zeta? And this also I have taught in EC part of network theory. I hope you can relate, right? There also I have told this is my omega n, this is my omega naught, this is my zeta. There also I have told. So 2 zeta omega n, 2 zeta omega n, that is 1 by under root LC is equals to R by L. So your zeta, hold on a second. Okay, this will not work. This lags so much. Yeah, just give me 1 second. So your zeta is actually equals to uh, r by 2 under root L, sorry, under root C by L. Okay, I have also told you how to remember this formula. We know that L by C is impedance, right? Unit of impedance. So I can say if I have, you have to remember this R by 2. If you remember R by 2, that means I cannot have L by C because zeta is unitless. So I need to have here C by L, so that this unit will be ohms inverse and this will be ohm and they will cancel. So ultimately your zeta will be unitless. So that's how you remember this particular thing, that what is my zeta in case of a series RLC, or you can always write this. If you ever forget, you can solve and write, and yeah, that's all. So then I have discussed regarding this complex frequency. So this S is called as sigma plus j omega. Now S is called as sigma plus j omega, right? And here also if you see is normal standard second order system, the roots are actually this. If you solve for this, right, you will get two roots. Of course it is a second order system, so we can solve for the roots. It will be zeta omega ns plus under root g1 minus zeta square into omega n. That's all. And there will be j. Okay. You can solve. Of course, I think I have solved it as well. But these are the two roots. Now, if I observe, these are my two roots. Okay, and my assumption is zeta is less than 1 and greater than 0. That is my assumption. So, in that case, in that particular case, I will get two complex conjugate roots. So, I see that the real part of the pole is actually contributing to the damping, right? Zeta omega n, it will, because there is zeta and there is omega n as well. So it is contributing to the damping. So that's why this is called as the damped frequency, or in complex frequency, this is called as the sigma, real part, that is responsible for damping. Okay, this is responsible for the damping. It can provide positive damping, negative damping, all these things, right, to a signal. And your omega, this omega is simply called as the frequency, okay, which is responsible for the oscillations, right? So that's why the imaginary part is responsible for the oscillations, because this oscillation is equal to, this value is nothing but my omega d, right? This is nothing but my omega d. So the imaginary part is responsible for the oscillation. That's why it is called as frequency of oscillation or complex frequency, like simple frequency, natural frequency, and this part is called as the damping frequency. That's all. These is the two things that you have to understand. That's all. No need to understand anything extra. Okay. So now if I solve for the impulse response of a standard second order system, correct, you will so you will get two poles, right? These are my two poles basically. So assumption is there can be two cases. Either zeta can be greater than 1, it can be less than 1, or it can be negative. Okay. So we are considering first of all we considered for zeta equal to 0. If zeta is 0, right, if zeta is 0, this is gone. So basically I will get two poles exactly on the j omega axis. And do you know what happens if my poles are exactly at the j omega axis? Poles of what? Poles of the transfer function. Remember, poles of the transfer function, not poles of anything, any weird thing, right? Only poles of transfer function. If the poles of the transfer function are at j omega axis, if you remember, the impulse response was oscillatory. So if I am giving it some impulse signal, the output is oscillatory. So it is called to be as marginally stable, because although the output is bounded, but it is oscillatory in nature. So for bounded input, I am getting a oscillations. So that's why it is called as marginally stable. Okay. Now, if my zeta is positive, the system will always be stable. How? So if if zeta is positive, right? Zeta is positive and it is less than 1. Okay. Then this will be a complex number, but that does not matter. If zeta is positive, if it is a complex number, I will simply get complex conjugate pole, and if zeta is positive, omega n is positive, that is our assumption. So this term is negative. So the real part is negative. So my pole 0 diagram, the real part is somewhere here, it is negative minus zeta omega n, and I will have two complex conjugate roots because these are complex conjugate of each other. So I will have a root here, pole here, pole here, right? So I will always lie on the left hand side of S plane. So for any value of zeta greater, for any positive value of zeta, my poles will always lie on the left hand side of S plane. Poles of what? Poles of closed loop transfer function. Very important. Poles of what? Poles of closed loop transfer function. If my poles of closed loop transfer function lie on the left hand side of j omega axis, system will always be stable. We have seen response, right? It was a damped sinusoid, the impulse response. So this part is important. So poles will always lie on the left hand side, hence system will be always stable. Yeah. Now if zeta is negative, right, it does not matter. This is zeta square, so it does not matter. This term will be either it will be complex conjugate or I will get unequal roots. I will come to that. But if zeta is negative, this term will be positive. That is a problem to us. If this term is positive, my poles of CLTF will lie on the right hand side of j omega axis. That is a problem because we remember the impulse response for this kind of situation used to come as a unbounded exponential. That is a problem. So if zeta is less than 0 or negative zeta, system will be unstable. Okay. Damping I have already discussed. Oscillation also I have discussed. Movement around the steady state, that is called as damping, and influence to reduce, prevent oscillation in a system, that is called as damping. And oscillation is this. Okay. So if zeta is 0, the poles are basically at plus minus j omega n, and we have discussed basically there is no damping present, right? No real part present. So the impulse response will be simply oscillatory in nature. The impulse response will be simply oscillatory in nature. You can solve for this, you will get a oscillation. Okay. Final value is not defined, hence it is called as a marginally stable system. Now the second case, the most important case of control system. For this, all the parameters are defined. That is called as the underdamped oscillations. Underdamped means like the oscillations are not very high. There will be some oscillations, but due to damping it will reduce, but it will not reduce at a very fast rate, right? That's why it is underdamped. We will see for other cases when my zeta will be greater than 1, this is called as overdamped, because I will provide so much damping that there will be no oscillations at all. I will provide so much damping that there is no scope of oscillations. Okay. One more reason is there, critically damped. Okay. When my zeta is 1, so zeta 1, when my system is critically damped, that is the time when zeta is 1. So basically then it happens, what happens is there is absolutely minimum oscillation and it reaches its steady state at a very fast rate. Okay, we will see the differences. Then also we'll understand why it is called underdamped, overdamped, all those things. Don't worry about it. Okay, so if my zeta is between 0 to 1, you will get obviously two poles. Now they will not be lying on the imaginary axis, they will be complex conjugate of each other. This will be the pole 0 diagram of a standard second order system when my zeta is between 0 to 1. Now this is very important. Please make sure you remember these things, right? For a marginally stable system, my poles will be lying on the j omega axis and the poles will be plus minus j omega n. For a underdamped system, so for a marginally stable system, it is undamped. It is also called as undamped. Okay, no damping is present at all. So there my zeta is simply 0 in this case, and in this case my zeta will lie between 0 to 1. Now the response would be, if I solve for the response, right, you can solve it. the response will be like this. And we have already solved the response for this actually in the chapter 1, I think, as well, right? So it will be something like this. And this is also a very, very important part. This you don't need to don't need to remember actually, but the step response you might need to remember, right? This you can ignore, don't need to remember, but the step response might need to remember. So point to note about underdamped system, some damping is present, okay, but not enough. So actually I'm damping the oscillations, like oscillations are dying down, right? That is what damping means, but they are not enough that oscillations is totally eliminated, right? This like I will show you like this, you will understand more in step response. Don't worry, trust me, you will understand this more in step response. Here oscillations are dying down, right? Here there was no for impulse response, for a undamped system there was no damping, so oscillations were always present. But here oscillations are dying down, but not enough. So for that reason we provide critical damping. So in critical damping there will be no oscillations, okay, it will reach steady state very fast. So critical damping is the third case where my zeta is 1. So in that case the poles will be real, negative, real and equal poles. So pole 0 diagram, I will have two poles. So repeated poles we show it like this, right? Multiple cross marks. So this also you have to remember. For undamped system, I will have two imaginary poles symmetrical about the origin. For underdamped system, I will have two complex conjugate poles on the left hand side of j omega axis. For a critically damped system, I will have two negative real repeated poles. Say with me. For critically damped system, I will have two negative real repeated poles. Trust me, this property will help you so much. Trust me. If you understand this property, right? For critical damped, I will have negative real repeated roots. So when my zeta is 1, right? When my zeta is 1, this simply becomes a square function. Like this will be what? Zeta becomes, this is simply s plus omega n whole square, correct? So that's why I get two poles at minus omega n, basically like minus omega, yeah, minus omega n. I will have two poles at zeta is 1 basically. So I will have two poles at minus omega n basically, okay? So the response would be something like this. If you solve this, right, the response would be something like this. Okay, this will be the response. With this, you will not be able to understand much. But once we will see the step response, there we will understand actually what is happening and why is it called critical damping. But one thing you can surely see that there is no oscillation. So this is called as ideal damping because this is just the enough amount of damping for which I will not get any oscillations. Okay, reaches the steady state in minimum time. This we will like this we will derive from the formula for the settling time. Okay, the settling time for a critical damp system will be the least. And the fourth condition is overdamp condition, where my zeta is greater than 1. So if my zeta is greater than 1, you will get two poles that are negative but unequal. So for a overdamp system, you will get negative real unequal poles. For overdamped system, you will get negative real unequal poles. Okay, so the poles will be something like this. And if you somehow do the dominant pole approximation, roughly it will behave as a first order system. Okay, roughly we can say that our overdamped system behaves as a first order system. Oscillations are prevented because it will behave as a first order system. So the response would be like just like exponential. It will die down. Okay, but it will take more time to settle than critical damp. That's why it is called overdamp. I have provided too much damping that it is taking more time to settle. Okay. Now, critical damp is not practical because for only one value of zeta equals to 1, right? We are getting critical damp, and it is, trust me, it is very difficult to get zeta equals to 1. Why? Because even if you design your system such that your system is critical damp, but there will be some noise, there will be some errors in the system that will change the zeta, right? That will change the pole locations. So of course getting critical damp is very difficult. Our target is always to get critical damp, but we will never be able to get critical damp. Mostly what happens is we have underdamped systems. Most of our natural systems are underdamped. Okay, there is some oscillations. Okay, so Yeah. So damping ratio gives us the information about the stability of a second order system. How? So if zeta is negative, that means your system will be unstable. If zeta is positive, that means your system will be stable. So that's how damping ratio gives us the information about the stability of the system. So these are the plots basically. You can put this as your short notes. Of course, I will provide the revision X notes. From there you can like remember all these things, like just a summary. Whatever we have learned, all these are summary. So these things are the most important things that you have to remember, no matter what, right? At least you remember these things, and at least you understand how to find out the poles of this particular equation. Like this is a quadratic equation, should not be a difficult thing. I hope, I'm expecting, should not be a difficult thing for you to find out the roots of a quadratic equation. Okay, should not be that difficult, correct? Yep. So that is the thing. So if we compare the time constant, right, you will see that the time constant of the overtime system will be the largest, because it will take more time to settle, because one of the poles will be much nearer to the origin. Okay, one of the poles will be much nearer to the origin, due to which it will take more time to settle. This will be bit further away from the origin, and yeah, this again takes more time. Under dam system also takes more time to settle. Okay, ultimately critical damped is the one for which the time constant will be the lowest. It will settle at a much faster rate. Okay, now one more important thing, this I will use multiple times, so please listen to me carefully. So for a under dam system, right, I can relate the poles locations. So let's say if this is one of my pole location, correct, and this circle is of radius omega n, so this is the real part of the pole and this is the imaginary part of the pole. So what can you tell me, what is this distance? So this is just a complex number, correct? I have a pole that is just a complex number, that is minus zeta omega n. This also, if you remember, it's great, but of course you can derive the pole locations for a second order system. It will not take you much time. Plus j 1 minus, I'm assuming zeta is less than 1. That's why I'm writing 1 minus zeta square into omega n. Now this is just a complex number. What is the magnitude of my complex number? This will be this square plus this square. What will happen is you will see that this right will cancel this term, because here I have minus zeta square, this will cancel. Only what will be left? Only omega n square will be left. So magnitude will be omega n square under root. So that's why omega n would be a magnitude. Okay. So my pole will have a magnitude of omega n. Pole will have a magnitude of omega n. So basically the distance from the origin of this location is omega n. That's why I have drawn a circle of radius omega n. That is interesting. This distance is omega n, and this distance is how much? Zeta omega n, right? And from this I can derive all the relation, correct? And this distance is how much? Omega d, which is 1 minus zeta under root 1 minus zeta square into omega n. So I can write what is my cos theta. Cos theta is base upon hypotenuse. Base is zeta omega n, that is the length. Hypotenuse is omega n. So it is zeta omega n upon omega n, that is zeta. So I will use this thing thousands of times. Okay. And remember, what is the range of zeta here? Zeta must be between it can be minus 90 to plus 90. Minus 90 to plus 90. Okay, because this is also a zeta, right? Here also there is a zeta. So yeah, the range of zeta would be minus 90 to plus 90. It will not go beyond minus 90, below minus 90 or above plus 90. One more thing I will use is cot theta. Your maximum peak overshoot, right? MPO. This is one of the parameters of a second order system. It is e raised to power minus pi cot theta. A into e raised to power minus pi cot theta. AK into e raised to power minus pi cot theta. Okay, what is all this? I will explain later. But this cot theta is this theta, right? So what is cot theta? Cot theta is just give me one second. Cot theta is it is based upon height, altitude. Base is zeta omega n. Altitude is under root 1 minus zeta square into omega n. right? So it is simply zeta upon under root 1 minus zeta square. So this particular value is here, right? So I use my MPO to be this. So don't ask me, sir, what is e raised to power minus cot theta? I've already explained you. Don't ask me that during that time, okay? Now another thing I will use is sine of 2 theta. What is sine 2 theta? Sine 2 theta is 2 sine theta cos theta, okay? So cos theta I already know, that is zeta. What is sine theta? Sine theta is omega d upon omega n. Omega d upon omega n. Omega d is simply 1 minus zeta square into omega n upon omega n, right? So sin theta is 1 minus zeta square basically. So this will be 2 into under root 1 minus zeta square into zeta. This will be my sin 2 theta. This also I will use in frequency response. So these things I will use. So I am already telling you. So focus here. Okay, these things I will use. So you should be able to plot this and always understand what is sin theta, cos theta, cot theta, tan theta, all these things. So all these things will be used later on. So same thing I have written over here only. So these are the things that are written here, over here. So this theta is also sometimes called as angle of inclination. Okay. So the relation between theta and zeta is they are inversely proportional, because because if theta increases, cos theta will reduce, so zeta will reduce. So they are inversely proportional to each other. Okay. So yeah, you can find out for now what will be the angle of inclination for zeta equal to 3 and zeta equals to 0.5. You cannot, right? You cannot do cos inverse of this. So this, right, whatever I have discussed, this is only valid for a underdamped system, right? These things are all valid for underdamped system. These are not valid for any other cases. So this, right, what is angle of inclination here? So cos inverse of 3, it does not exist. Okay. Again, minus, so this is not valid for negative zeta. We will not use it for negative zeta. Okay. So we will only use it for positive zeta. So zeta range will be between, like, you can either write 0 to 90 or you can say between minus 90 to plus 90. Okay. Yeah. That is the thing over here. So yep, I think that's about it. So damping already we have discussed. So quality relation between quality factor and damping, I think you can do it. Not that difficult if it is under damp, critical damp. So for condition for critical damping, this can be asked. This we have discussed in network theory as well. So basically your zeta is this. So if you write your zeta to be equals to 1, that is the condition for critical damping. Okay, overdamp condition for overdamping, zeta has to be greater than 1. So simply you can derive the zeta. We have derived the zeta for a series RLC circuit, and you can say what is the condition for overdamp, underdamp, because you know in overdamp zeta will be greater than 1. So all these conditions you can derive, and for parallel RLC similarly you can do. I am not explaining these things. Okay. Now now the most important part, the step response of a second order system. Okay. So very important. Again, you have to, like, this is the summary table, and this all these notes will be provided. Revision X notes also will be provided, so you can take the summary from there as well. But yeah, this is a summary table basically. So yeah, these are the things. Now let's discuss. So these conditions you can don't need to remember it. Just understand what is my zeta, because zeta in series RLC circuit and parallel RLC circuit are different. So zetas are different. So just be very careful. But condition will be same. Always for underdamped zeta will be 0. Always for undamped zeta will be 0. For underdamped zeta will be between 0 to 1. For critical damped zeta will be 1. For overdamped zeta will be greater than 0. So these conditions will match, but the value of zeta, right, for series RLC and parallel RLC will change. So the conditions also here will change. Condition for zeta remains same, but the condition for R will change. So just be careful. Okay. Okay, yeah, step response. So if it is an undamped system, right, if I'm providing step input, I can simply integrate the impulse response and I can get the step response. So if I integrate the impulse response, what you will see is you will get a waveform like this. That is 1 minus cos of omega n t. 1 minus cos of omega n t is like this. So I hope now you can understand, if I'm providing a step input, my output, right, is never settling. It is always changing, oscillating. So that's why it is called as oscillatory or undamped. That is a step response, right? These things you can keep in mind. Okay, these things you can keep in mind. So here, right, They might ask you what is the average value for a marginally stable. Average value will be simply 1 in this case if the DC gain of my second order system is 1 and the input is a unit step. If let's say the input was AUT and the DC gain of the system would have been K, then this would have been 2 into AK. I can use the property of linearity, so this will be simply 2 into AK. So your average value, right, will be AK, where A is the jump of step signal, and this I will use later on as well, right, and K would be the DC gain. So this notation I will use later on as well. Okay, so simply these things will be multiplied. So the average value will be A into K. That's all. Now for underdamped oscillation. For underdamped oscillation, what will happen? For underdamped oscillation, again I can integrate the step response. If I integrate the step response, you will see that yeah, this thing you have to, like, this will be bit lengthy actually. This will be very lengthy. But if you finally solve this thing, actually, yeah, it is better if you remember. Okay, very important thing. It's great if you are able to remember it. Great if you are able to remember it. Or even if you are not able to remember it, right, what you can do is you can do this actually. It's great, it's good if you are able to remember it, because this will be used. Or what you can say, okay, because your input is not sinusoidal, there is no other option. There is no other way but to remember. How to remember it? So one thing, you know, this is for underdamped system. If it is for underdamped system, I know my system will settle to what? The input value. So if I am providing a unit step 1, so at t equals to infinity, this will be 1 because the impulse response was dying down. That's why there should not be any error. So I see, yes, it is settling to 1. That is the one thing that you can keep in mind. Now this term you have to remember, unfortunately. So this exponential term is not that difficult, right? This is the time constant basically, right? Time constant. If you see negative real part, what are my pole locations? These are my pole locations, right? Negative real part is zeta omega. Sorry, this is not the time constant. The inverse of this is my time constant. 1 upon zeta omega is my time constant, right? So here I will have e raised to power minus zeta omega t. This you will have to remember, divided by under root 1 minus zeta square. This also you have to remember, unfortunately. Okay, unfortunately you have to remember this. Into sine of omega d plus theta, what theta is nothing but the angle of inclination, that whatever we have derived. Okay, and omega d is simply the damped frequency of oscillation. Okay, that's it. So this equation somehow you have to remember, and we are seeing that this is the response. So the most common response, step response, it is settling to one value. Step response is settling to one value, but with some oscillations. Okay, so we are providing here, right? My output was never settling, but here at least it is settling, right? So although I am providing some damping to reduce the oscillations, but still there are some oscillations present. Okay, and in this case it is 1, but it can be A into K as well. I hope now I don't need to explain why it will be A into K. If my input is not unit step, it is AUT, jump of A, and the DC gain is K. Also your response will change to A into K. That's all. Okay, yeah, the same thing I have derived over here as well, A into K. That is just a constant number. Okay, that is not a problem. So this is the actual thing that you have to remember. No matter what, you cannot forget this. I also forget this, I do agree, but during exam I will remember it. Okay, I will remember it. So by default we will consider that input step has an amplitude of unity. Basically there is a unit step jump and the system has a DC gain of unity. If nothing is mentioned, we will assume these two things. Otherwise they will mention, don't worry. If nothing is mentioned, you will assume these things and proceed with the solution. Now let's come to the third condition, that is the most interesting one, critically damped. If it is critically damped, right, you will see I can simply integrate the impulse response. If I integrate the impulse response, you can integrate it, UV rule, whatever you want to do. This will be the response. Now you see, right, the response would be somewhat like this. Okay, if I plot this response, the response would be somewhat like this. There is literally no oscillations. Okay, and it settles to a very fast value. So similarly, if you solve for overdamped case, again if you integrate the step response, the response will be like this. So this is damping, but this is reaching its steady state very fast, but this will reach steady state, of course, but there will be over damping. Basically I am damping it more, I am reducing the output more. So if I am doing over damping, so it will reach steady state but at a slower rate than the step response. It will reach steady state at a slower rate than the step response. So that's all basically. These are the things that you have to keep in mind. Okay, so yeah, I have plotted this in MATLAB for different kind of cases. You can just pause the video and just see what is happening for each cases. So this is the actual summary. Okay, again very important summary table. These are all very important things. Okay, you have to keep this in mind. Now there is one small topic left. What happens if I provide zeros, right? We already know what happens if my poles are on the right hand side. It will totally damage the stability of the system. So zero also partly affects the transient response. So if I add zeros, right, what will happen? It can increase the initial change. Okay, so zeros affect the dynamic response. You can obviously add the zeros and then check the like y of t, what is the response, impulse response after and before adding zero, and you will see basically this input, right, will change and it will change the dynamic response, transient response. So zeros affect the transient response, poles affect the steady state response. Of course it affects the transient response as well, poles do affect the transient response as well, but it also defines the stability, right, and zeros also defines the transient response. Okay, also zeros help us to remove the effect of a pole by using pole zero cancellation. Let's say I have a pole at s equals to s plus 2 and s equals to 1, right? So what I can do is I can multiply this with a 0, right hand 0, right, and that will cancel the pole, so that will make the system stable. Okay, and there is one more thing about zero. So zero sometimes can cause the direction of my response to change. So let's say if it is supposed to go to negative, right, zeros can suddenly change it to positive because zeros affect the transient response, right, and in transient anything can happen. So this, you will say, what is the problem? This is a problem. Let's say I have a fan, right, and fan is supposed to move only on the clockwise direction, but for a certain second it moves in the anti-clockwise, so it can damage some things. So these are the problems with zero. So maybe they can ask you in interview, what is the effect of zero? So that's why I have told you the effect of zero. So everything they can ask. So I am teaching you not only for GATE, I am teaching you for interviews as well. That is the quality that we keep at PrepFusion. Now yeah, governing equation of first order system, already we have discussed these things. We have discussed. So there are a few things actually, parameters, performance parameters of first order system, right? So first thing is the rise time. So mostly they will not ask you this first order parameters, they will ask you the second order parameters, and that thing you have to remember. Okay, how to remember I will tell you, but that you have to remember. Rise time is basically the time for the response to reach from 10% to 90% of its final value. Response meaning unit step response, okay, or step response simply. So from 10% to 90%, I can simply calculate the time, right? You can calculate the time here. It is simply exponential function, and if we solve, it comes out to be 2.2 tau. So do you need to remember it? I will say no. Just remember the, like, no need to even remember the definition. Just understand, okay, there exists something like rise time, and they can ask you. And if they ask you the rise time for a first order system, my expectation from GATE examiner is that they will obviously tell you the definition of rise time as well, right? Because different books will have different definitions, so we have to be very careful. Okay, don't worry about this. Now the next parameter is the delay time. So delay time is basically the time taken for the system step response to reach from 0% to 50%. Okay, again you can solve for the relay time. These things are just normal things. Settling time is very important. Okay, it is the time by which it will reach the steady state within a certain error band. Error band basically means 96% of steady state, 95% of steady state. So 96% of steady state, it is 4% error band. 95% of steady state is called as 5% error band. Okay, so generally settling time is called as 4 tau. 4 tau is the time of 2% error band, right? So that is 98% of steady state, and generally we will use our settling time to be this only, mostly. If they will mention that calculate the settling time for 3% error band, that means you will not use 4 tau. Answer will be wrong. You will see at what time my response is reaching to 97% of its steady state value, and from there you can derive, and that is actually 3 tau, not 3 tau, sorry, whatever is that, right? So if nothing is mentioned, by default you will assume 2% error band. If it is mentioned, of course you will solve the equation and you will find out the time at which it reaches that particular time. Okay, again, now we have come to the second order system, right? For the second order system, what is the rise time? The time taken for the system to reach 100% of its final value for the first time. That is what rise time is. Okay, so again, these are important parameters. This, unfortunately, you have to rise time, I have never seen them ask rise time, but they can ask rise time. But this thing, rise time, you have to remember. Actually, rise time, you have to remember, there is no other option. Okay, it's better if you remember. Rise time is the first time my step response reaches its peak. Sorry, not its peak, sorry, it's 100% of its final value. Because what will happen, due to oscillations, it will reach its final value, but again it will increase. Then again, due to damping, slowly it will reach to steady state value. So rise time is a time from 0 to t rise. It will reach 100% of its steady state value for the first time. So if you solve this equation, you put steady state value is ak, you will get this relation. Okay, rise time would be pi minus theta by omega t. So this thing you have to unfortunately remember. This formula is only valid for underdamped system, because this equation is only valid for underdamped system. So this you have to remember, very important formula. This you have to remember. How do you remember? So if I have R here, I will have D, right? RD, R here, D, that's all. And I will have pi minus theta. Don't worry, at the end I will put a summary of the formula, and then we will discuss how can we remember. There are a few more things known as peak time. Peak time is the time at which the system or the response reaches its first peak. Here I was reaching 100% of my steady state value, that is A into K, right? AK. Here it is first peak. So it will basically reach its first peak at TP. If you solve right, it will be the sinusoidal. Whenever this sinusoidal will reach its peak, that is the time, that is basically pi upon omega t. Whenever this term will be p, like you can solve this, you will see that whenever this is equating, right? If I differentiate this, right, you can differentiate this equation and you will get a condition. Okay, the condition is simply pi upon omega d. So basic condition is this. This is the condition. Okay, unfortunately these things you have to remember, there is no other option. So this is the condition. Now there can be multiple peaks. This is the first peak, right? After this again I will reach another peak, but that peak will be of course of lower amplitude, because I have the effect of damping as well. Again I will reach another peak, but that peak again will be lower. So this is the first peak, the second peak, third peak, fourth peak, and this is the lowest value, right? This is called as the first overshoot, first peak or overshoot. Overshoot meaning over my steady state value, and this is called as the first undershoot, and this will happen at even multiples of pi. Like here, first peak I am receiving at pi by omega d, second peak I will receive at 3 pi by omega d, third peak I will receive at 5 pi by omega d, and so on. Similarly, first undershoot I will receive at 2 pi by omega d, 2 pi, this will be 2 pi by omega d. Second undershoot I will receive at 4 pi by omega d, and so on. and so on, right? This will keep on happening. So that is what the undershoot and overshoot is. Now there is one calculation of maximum overshoot. What do I mean by maximum overshoot? Basically this difference, right? Difference from the steady state value. So the maximum value, this is not actually some like good value. Okay, this is some weird value. Okay, we get some weird value. If we solve this, right, this is called as the maximum overshoot, basically maximum difference from the peak. So of course in the response you will put the value of TP and your output will be this. So if I take the difference of your steady state value and your peak value, this will be your maximum peak overshoot. Basically this will be your maximum peak overshoot, right? That is this value. This will be your maximum peak overshoot. So not this value, sorry. This difference will be your maximum peak overshoot, correct? Which is simply equals to ak e raised to power minus pi cot theta. So I will not explain what is cot theta. Now we generally measure it in terms of a percentage, right? This is not a good measure. We always try to define percentage. So we define MPO as a percent of my steady state value. So it will be y of peak minus y of infinity upon y of infinity. So your maximum peak overshoot comes out to be e raised to power minus pi cot theta, and this will be used everywhere. So this formula also you have to remember, and what is cot theta already I have explained. And if they are asking you percentage MPO, right, percentage maximum peak overshoot, you will simply multiply 100. That's all. Okay, these are the things basically. Okay, so your MPO, like, also remember the relation MPO is inversely proportional to zeta. How? Because if you vary zeta, right, what will happen to theta, and accordingly you can derive the relation for relation between MPO and zeta. Okay, you can do all these things. And the last one is the delay time. Not last one, there is one more thing. Delay time, the time taken for the response to reach from 0 to 50% of its final value. Now this is equals to 1 plus 0.7 omega d, sorry, zeta upon omega n. This is a formula, you have to remember it. Okay, now how will you remember this and rise time? So rise time, I had for rise time, it was pi minus theta, and I will not have omega n here, right? I will have here omega d, because I will remember there are two things. One is rise time, one is delay time. So if I have delay time, right, I cannot have d here, not possible. So I will have omega n. Now I have already used omega n once, so I will not have here omega n, I will use omega d. That's how you can remember. That's how you can remember simply. Already I have delay time and rise time, right? So if I have delay time, if I have d, this will not be omega d, this will be omega n. Okay. Similarly, if I have this, if this is my rise time, correct, I have already used omega n, so I will not use omega n here, I will use omega d. That's all. Okay, I hope you have understood that point. So this part is clear, right? Now settle time is basically the time for it to reach steady state. So this will be 4 tau. So approximately, right, if my zeta is between 0 to 1, your tau, right, tau is the negative inverse of the real part, which is simply 1 by zeta omega n. So 4 tau will be, settling time we will use 2% error band only, it will be 4 tau. Okay, 4 by zeta omega n. So these are the formulas which you have to remember. Now here, right, for overtime system, what you can do, you will simply calculate the roots. Okay, there will be 2 roots. Okay, for overtime system there will be SP1, SP2, correct? There will be 2 poles. Now if there are 2 poles, basically you will neglect the pole that is further away from the j omega axis. You will only include this pole. Let's say SP1 is included, right? So you know the pole and it is a negative real, so you will take the magnitude and you will take the inverse of this, and this will be your time constant, and you will multiply this with 4, and this will be your settling time. So for overtime system, you don't need to remember this formula, although you can remember it, but no need to remember, just simply, right, second order system, you can find out the poles. So you got the pole location, then you take the inverse, magnitude inverse, and you multiply it by 4, you will get your settling time, because this is what your inverse of this, negative inverse of this is your tau. Okay, I hope you understand these things. Now there are few more things, like what if I vary my zeta, omega d and theta, how these things will vary. Now I will just pause the video and you can see what is happening. I will not explain these things, right? So pause the video and see if so in the first case, right, in the first case what we are doing, we are keeping my zeta omega n constant. If my zeta omega n is constant, basically the real part of my pole is constant, so theta will change. If theta is changing, zeta will change, and your omega n also is changing, but your zeta into omega n is constant. So what are the parameters that are changing? You can just take a pause and see. and in the second condition, I am keeping omega d, my damped frequency, to be constant. Basically this part, right, the distance from the distance on the imaginary axis, I am keeping it constant. So your theta is again changing. What things are varying? So if I increase, like if I keep this same and if I move along the left hand side, what is varying, you can see in the picture. Okay, I will not explain all these things because that will consume a lot of time. Again in the condition 3, I am keeping the theta constant. Okay, if theta is constant, basically this angle of inclination is constant. So zeta omega n is also changing, your omega d is also changing. So then what happens, you can see through these things. I will not explain because of course there are so many things, and in exam point of view they might not ask you, but basic, you can, if you know the basics, right, what does each term means, you can understand. Okay, if I increase theta, what will happen? If I increase zeta, what will happen? What will happen to the MPO? What will happen to the rise time? All these things you can understand if you remember the formula. How to remember the formula also, I have explained it to you. Now let's discuss about steady state error. So these are all the performance parameters. What are the important formulas that you have to remember? How I vary, if I vary theta, what changes, right? You can derive it from the formulas. Rough idea you can get. I am not explaining everything because that is not too important. Now let's come to steady state error. So there are two things, right? One is steady state error for unity feedback, and we will discuss for non-unity feedback after unity feedback. For unity feedback, it is very simple, right? Here I have my output and here is my input. So I subtract my input from the output, and then this will be my E of t. So R actually is called as the reference. That's why it is named as RT. RT is actually called as the reference input and CT is the output, right? So I'll subtract my output from the reference input. That will be my error signal, and of course we want our error to be 0. We want our error to be 0, correct? So if our error is 0, then our task is done, correct? But of course it will not always be 0, it will be some signal, right? R of t minus C of t will be something. Okay, so we will see that. We will track, basically this signal will track the reference signal and it will try to make it 0. Okay, so if I solve this, right, in Laplace domain, if I take the Laplace inverse, what is my E of s? If I take the Laplace domain, right, it will be E of s will be equals to R of s minus C of s. Now there is one interesting fact. I know my transfer function T of s is output upon input, ratio of output upon input, right? So what I can do a bit of trickery here. I can take R of s to be common. So if I take R of s to be common, just give me 1 second. If I take R of s to be common, this will be R of s into 1 minus C of s upon R of s. What is this? This is nothing but the transfer function, correct? So your actual, so what is my steady state error? It is basically E of infinity at t equals to infinity. So it is equals to limit as s tends to 0. If I use the final value theorem, s into E of s. So this will be equals to s into limit s into R of s into 1 minus C of s upon R of s. Okay, which is basically T of s, right? So this is the formula that is written over here. Same thing is written over here. Do you need to remember it? It's your wish, but it will hardly take you 2 seconds to derive from here, right? You know what is E of t. It will hardly take you 2 to 3 seconds. So you don't need to remember it. Now I got the expression for steady state error. If my transfer function, right, for a unity feedback system is this, right? For a unity feedback system, my transfer function is this, g of s upon 1 plus g of s. Okay, so your equation will become this. Okay, finally if you put your t of s to be this, finally your equation will become this. Do you need to remember it? Again I'm saying it's your wish, it's up to you. Personally I never remember it, I directly use this. Okay, directly I write this and then derive. Okay, it's up to you. Now this thing is only valid for unity feedback, that is point 1 obviously. Second thing is, this thing is only valid if my system is stable, if my output is stable. Basically your poles must be lying on the left hand side of S plane. So because I am applying the final value theorem here, if I am applying the final value theorem, that means assumption is all the poles of E of S are on the left hand side of S plane, right? That is the condition for proper application of final value theorem. Otherwise final value theorem is not applicable. So be very careful, because in GATE they have asked a question where the poles are lying on the right hand side. So for that this formula will not be applicable, then your steady state error will be simply infinity. So be very careful, they have asked this, so I'm already telling you where you have to be mindful. That was for the unity feedback. Now what about for non-unity feedback? So like there are many methods, like there will be some formulas, position coefficient, all these things are there. I will tell you, no need to remember all this, right? Just understand this, that's enough. This is position error coefficient, velocity error coefficient, those things are there. I will tell you, no need to remember, but few conclusions you can understand, that will be helpful actually. So here are few conclusions. If let's say if it is a type 0 system, for a standard second order system, if it is type 0 system, basically there are 0 poles at s equal to 0. So your steady state error, right, for step input, steady state error for step input will be 0. Sorry, will be not 0 actually. It will be this value. Like you can solve using the formula. Do you have to remember it? Again I am saying no need to, but you should actually at least know like how it is coming, and you should be able to solve this in the exam hall. So for a step input for a type 0 system in unity feedback, negative unity feedback system, the steady state error is coming out to be non-zero. I have a non-zero steady state error, correct? That is a very important point. If I increase the type of the system, if it becomes type 1 system, then your steady state error will be 0. So you can solve, derive, I will not derive it, you can solve, it becomes 0. That is an interesting thing to note. So if my type is greater than 0 basically, or if my type is equals to or greater than 1, right, then the steady state error for a step input is always 0. Type of what? Type of OLTF. Type is, if nothing is mentioned, you will say it is for OLTF. Okay, very important conclusion. Now what if I provide a ramp input? So for ramp input you will observe that for type 0 your error will be infinity, system will not be stable basically, okay, because the poles will be it will not, final value theorem will not be applicable. But for type 1 system you will see that the error is some non-zero value, finite value, and for type 2 system it will again go to 0. For type 2 you will see the conclusion is for type 2 it will go to 0. So basically what is happening, if I am increasing the order of input, so from step I want to ramp, so in case of ramp what will happen, for type 1, for type 0 there will be infinite error, for type 1 there will be finite error, for type 2 there will be 0 error. Previously for type 1 I was getting 0 error. So these are the conclusions, just a good thing to keep in mind. Okay, so this happens if I increase the input order, right? Initially it was unit step which is 1 by s, now it is unit ramp which is 1 by s square. Now if I increase it to parabolic, so similar relation will follow. Now for type 2 I will get a non-zero error, and for type 3 and on there will be 0. So this is a table, summary table basically. You can, of course I will provide you the notes, you can take a snapshot of this and remember it on your own what happens. Okay, so let's solve a very basic question here. Find out the steady state error for an input like this. Okay, so don't need to remember any formula, nothing, just solve using basics, right? Solve using basics, that is the best way to solve error question. Let's solve this. So we have to find out the steady state error. I know the steady state error would be, this will be E of t minus R of t. Okay, so this will be basically R of t minus E of t, sorry, not E of t, sorry, this is my C of t, right? Y of t, that is my steady state error, that is my steady state error, that is equals to E of t. So this will be, again if I take the inverse, Laplace inverse, this will be E of s will be equals to R of s minus y of s. Again, I can take this common, r of s into 1 minus t of s. Correct. Now let me first of all calculate what is my t of s. T of s will be g of s upon 1 plus g of s, which is basically equals to 1 by s square plus s plus 3. I am directly writing it plus 1. Now if I solve this further, this will be equals to yeah, that's it. That is my transfer function basically. So first of all, you see where are my poles lying. So can I comment about the poles of E of s, right? So this is my E of s, correct? So this will be 1 by s cube plus 3s square plus 1. Now I don't know where does my pole, where are the poles basically. I don't know it, right? So what you have to do is you have to use Routh. Okay, that you will learn later on in the next chapter. You will learn how to check the pole location, like the pole like stability or not. Okay, so this system actually you have to check for the stability. Okay, let us check for the stability. So I will have here, this will be s. Then like for the students who don't understand Routh, don't worry. Okay, for the students who understand Routh, they can revise a bit. So if I write the characteristics equation, this will be s cube plus 3s square plus 1 equal to 0. Okay, so I will write here s cube first, that is the highest order, then s square, then s raised to power 1, s raised to power 0. The coefficient of s cube is 1, and coefficient of s raised to power, this will be 0 into s raised to power 1, right? So coefficient of s raised to power 1 is 0. Then I will have s square, and this will be 1, 3 and 1. So basically, right, for the system to, for any third order system to be stable, the internal product must be greater than external product. Don't worry, I know I am talking something that you don't understand because I have not taught you it, right? So just for your sake, just understand that this system is not stable. Okay, because internal product is not greater than 0, so not greater than external product. External product is, in our case, sorry, yeah, internal product is 0 basically. Okay, how it is 0? So I can write it properly, 3s square plus 0 dot s plus 1 equal to 0. So this is my internal product. Okay, 3 into 0, and external product is this, 1 into 1. So 0 is not greater than 1. This statement is incorrect, so my system is not stable. I know you don't understand what am I talking about. For the students who have learned Routh-Hurwitz criteria, they will understand this. But for the students who don't understand, no worries. Okay, I will teach you in the next part what is Routh-Hurwitz criteria. For now, just keep this in mind that my system is not stable. So whatever we are doing is actually wrong. Okay, you cannot use this s into E of s limit as s tends to 0. This formula will not be valid. Similarly, I have done it here as well. So you cannot do it. This is wrong. Okay, so yeah, input you can convert obviously. How, what will be the conversion of this? So what is t into ut? T into ut, right, was equals to 1 by s square. Now if I am multiplying by t on the right hand side, right, multiplying by t on the right hand side, what will happen on the sorry, multiplying by t on the left hand side, what will happen on the right hand side? I will differentiate negative minus d of ds, correct? So this will be actually equals to 2 by s cube. Okay, 2 by s cube. That's all. Now what will be your because I have 8 here, right? Don't forget I have 8. So if I have 8 here, so I will multiply 8, that will be 16 by s cube. So you can see the conversion is 16. So this is actually 16 by x cube. A is 16, so this is 16 by, so the conversion for this will be 16 by s cube. Okay, I have not written it, but it will be 16 by s cube. That's all. Okay, so yeah, that's pretty much it basically. That's pretty much it. So the system will not be stable anyways. You cannot apply all this, right? Now let's come to non-unity feedback. What will be the answer for non-unity feedback? There is huge controversy in steady state error for non-unity feedback. First of all, I want to clear the controversy. in today's examination, whatever will come later on, right? Previously, whatever came, ignore that. If it is a non-unitive feedback system, out of 100 cases, I'm 100% sure 99% of the times, right? 99 of the cases, they will tell you the definition of error. In the question, they will give you a non-unity feedback and they will themselves tell you what do they mean by error. So in the question it will be given that I have a non-unity feedback, block diagram will be given, and they will tell you please find the steady state error if the error definition is this. They will give you some definition, right? It might be this R of s into R of s minus C of s, or it may not be R of s minus C of s, right? It might be something else, but that definition will be given to you. So out of 100, 99% of the cases it will be given to you. That is point 1. So that confusion is clear. So what about for 1% of the cases? What will happen for 1%? So what if they don't give you? I am telling you they will give you. Okay, because there is huge controversy. Different books discuss the steady state error for non-unity feedback differently. So there is no standard. So that's why I am sure they will provide you what do they mean by error for a non-unity feedback system. Like unity feedback system, there was a standard. This was the definition. But for non-unity feedback system, there is no standard per se. But just in case, if they don't give you the information, how will you calculate the steady state error? So you will break it down into 2 cases. Okay, I will explain this using an example. Here I don't have an example. So yeah, what we will do is we will break it down into 2 cases. Okay, so case 1, where my when my input is 0, controller input is 0, what is my reference value of the output? Okay, so ideal case is when my like I'm providing some, so not control input is 0. So basically this part is the input of the controller, right? This part is the input of the controller, correct? So this is the controller, this is the feedback system mechanism. So what we assume in the ideal case, so we will solve it for 2 cases. Case 1, first of all, that confusion I hope is clear. How to solve questions, they will give you the definition. I am just talking about for the 1% chance. Okay, so don't worry about this. For the 1% people I am talking about. For 1% case, what will happen is you will first of all break it down into cases. First case will be for the case. So this is my controller actually. This is my error signal, right? So error signal is given to the controller, and controller gives what do you call instructions to change. So basically, if I have AC here, and AC will receive some input error signal, if there is huge difference between the atmosphere temperature and the temperature required, so AC will release more cool air. Otherwise, it will release if the error or the difference between the atmosphere temperature around it and the required temperature is very low. So AC will not release more air, it will release less amount of cool air, right? Because it is already very near to its reference value. So the input to the controller is the error signal. So for the case 1, I assume that the input to the controller is 0, right? When will it happen? When my output will reach reference value for reference input. So basically, what is the input to the controller? Input to the controller is R of t minus. So first of all, I will convert this into Laplace domain. That is the first task. Input to the controller will be R of s minus h of s into C of s. Okay, and this is the input, and this has to be 0 for what? For input to be at the reference value. Just give me 1 second. And output also will reach reference value. So what is the reference value of my output? What is the reference value of my output? So my reference value of my output is equals to R reference upon H of S, correct? So basically R reference is nothing but the input basically. So it will be R of S upon H of S. So basically I want my output to reach to this desired value. I want my output to reach to this desired value. Okay, but my output currently is C of t. It has not reached to this desired value. So case 1 was assumption for the ideal case. Case 2 is the actual case where the current value of my output is not C reference of S, it is C of S. Now we will just compare my error signal E of S would be the difference of the reference signal C reference of S minus C of S. That's all. This is my error signal, because they have not given you the definition, so you have to take a definition. This is the most standard definition that I got from the book. I think it was from Ogata. The book was Ogata. Okay, that is what is written over here. C reference of S minus C actual. ACT means actual. This is my error signal. So C reference of S we have already computed, that is R of S upon H of S. What is C actual? C actual is basically my input into the transfer function, right? That is my actual output C, right? So that is what I will write here. So then you can further solve. So your steady state error will be limit as S tends to 0, S into this, I can take R of S common into this. So this is the proper definition of steady state error for a non-unity feedback. You can remember it, very good. If you don't want to remember, then just understand, solve it for the case 1, find out the reference C of S, right? And then you compare the reference C of S with C of S, that's it. Just remember the formula, that also should be more than enough. Okay, so yeah, that is what you have to remember here. Okay, these are the things, but 99% of the cases they will define what is steady state error. Okay, and obviously this formula will be valid only if all the poles of E of S are lying on the left hand side. So let's solve a very basic question like this one. Okay, so yeah, let's solve for this case. We have to find out the steady state error for this particular case. Nothing is mentioned. So what I will do is, first of all, I will find out the reference of S. So what will be the reference? Reference would be the input to the controller must be 0, right? So if the input to the controller is 0, that means R of S minus Y of S into this H of S, right? I will write the H of S later. I will not worry about it. It has to be 0. Input to the controller must be 0. That is the case 1, right? So from here I can actually calculate what is the Y reference of S. Y reference of S would be R of S by H of S. Okay, and what is my Y actual? Y actual would be simply input into the whole transfer function of this whole system into T of S. Okay, so my error signal E of S would be Y reference minus Y actual in the Laplace domain. So this will be R of S, I can take common, 1 by H of S minus T of S. Okay, so what is T of S? Let me first solve for T of S. So T of S, right, will be G upon 1 plus GH. So 1 by S plus 3 upon 1 plus GH, that is 6 into S plus 1 upon S plus 2 into 1 by S plus 3. Okay, so this will be, if I solve this, right, I have to multiply S plus 2 into S plus 3. So this will be S plus 2 upon S plus 2 into S plus 3 S square plus 5S plus 6 plus 6S plus 6 plus 1. Sorry, this is already multiplied with 6S plus 6, that's all. Okay, so yeah, so yeah, I was here. Okay, this is my transfer function, so we can solve for the transfer function. Let me just get a bit of case here. So okay, we are running out of space. Let me add a page. So yeah, okay, this is my transfer function, and H of S is very simple, 1 by, so what is my input? Find out the steady state error expression, that's all. That is what they have asked me, just the expression for steady state error. Input they have not told me. Okay, so input, this is R of s into 1 by h of s. H of s would be 1 by h of s would be s plus 2 upon 6 into s plus 1 minus s plus 2 upon s square plus 5s plus 6s plus 6. So I can take s plus 2 common. So expression for steady state error, right, will be R of s into s plus 2 1 by this will be 6s, right? So limit, don't forget, like you have to write the steady, this is my E of s, right? Steady state error would be limit, assuming that all my poles are lying on the uh, left hand side, and this time it will lie. Okay, this time system is stable, it will lie. Okay, so if I assume, like we can take a thing, we can assume for a unit step input. So if I assume unit step, so 1 by s and s will be cancelled, this will be s plus 2. Okay, and of course don't forget to write limit as s tends to 0. This will be s square plus 11s plus 6 minus 6s minus 6 upon s square. This is stable system. Okay, don't worry, the system is stable, don't you worry. So if I take common 6, right, this will be s plus 1, that's all. So now you can put s equal to 0. If I put s equal to 0, this will be 2 into 6 is, okay, this is anyway 0, right? Yeah, 6 minus 0. So ultimately it will come out to be 0 only. So your steady state error comes out to be 0. No problems. Okay, I hope you have understood. Okay, hold on. 6s, hold on a second. Oh, sorry, this will be 12, right? So sorry, whatever. This is 6 plus 6, 12. Sorry, here I will have 12. 12, okay, I will have 12. If I have 12 here, yeah, this will be, actually this will not be 0. Sorry. This will be 12, right? Yeah, 12. Okay. So this will be 6, 5. So this will be anyways gone 0, 0. This will be 6 upon 12 into 6. So this will be actually 1 by 6. So your steady state error comes out to be 1 by 6. For a unit step input, they have not mentioned unit step, but for this it will be 1 by 6. So similarly, like, that is what I have solved here. Ultimately the answer comes out to be 1 by 6. Okay. Similarly, you can solve it for this case as well. But here just check whether my poles are stable or not, right? You must check. Okay, so that's all, that's how you can approach it. So there are few guys who approach it in the wrong manner. What do? They convert this into non-unity feedback. They convert non-unity feedback to unity. How? So they find out the transfer function and they draw a similar block diagram with a unity feedback, and they make the both the transfer functions same. So OLT will be different here, and they will say they will compute the steady state error here and they will do it wrong. But don't do it, don't convert, please don't do it. Okay, don't convert non-unity feedback to unity feedback, it will be wrong. They will give you the definition of steady state error. So all these are wrong things. Okay, don't do all these things. Okay, so yeah, so basically type of a system is also very important if you want to compute the steady state error. So let's start with the PYQs basically. So yeah, we consider a closed loop system. Okay, G of s is this, C of s is this. This time your output is not C, it is Y. So just be careful. They will play around with this, right? It will be I, C, Y like this, right? Just be careful. Okay. So G of s and C of s are there. If the steady state error for a unit ramp input is 0.1, then the value of K would be. So solve with basics. No need to remember any formula. So what is the definition of steady state error? ESSS equals to limit as s tends to 0. If one more thing is there, if your question is NAT type and they're asking the steady state error, so by default your system will be stable. It is not possible that they're asking for steady state error and your system is unstable and it is a NAT type. because if it is unstable, your steady state error will be infinite. How can you enter infinity? You cannot. So by default, another trick to understand, you don't need to check for stability if it is a NAT type question. If it was MSQ or MCQ, then you would have had to check for stability as well of E of S. But here we don't need to be careful, so we can relax. So it will be S into E of S. So what is my E of S? E of S is R of S minus C of S, which is, so of course don't forget, I may sometimes forget to write this, right? Limit S tend to 0. It is understood by you, right? I hope. So S into R of S I can take common into 1 minus C by R, that is T of S, correct? So what is my transfer function? It will be G of S into C of S upon 1 plus G of S into C of S. Okay. Now G of S is 1 by S plus 1. So G of S into C of S would be 1 by S into K by S plus 3, because S plus 1 will be cancelled, upon 1 plus same thing, right? S into S plus 3. So this will be K S square plus 3S plus K. Okay. So yeah, that's all. So I can put this over here, right? For a unit ramp input, they're talking for a unit ramp input. So for a ramp input, what is my TUT? What is my R of S? It will be 1 by S square, right? So expression ESS will be limit as S tends to 0, S into R of S, that is 1 by S square, into 1 minus T of S. T of S is this, S square plus 3S plus K. Okay, just give me 1 second. So here, right, what will happen? K and K will be cancelled. This will be 1 by S into limit as S tends to 0. This is like, I hope you understand this. This will be S square plus 3S. K will be cancelled, right? K plus K minus K will be gone. S square plus 3S plus K. So I can take the S common here. So all the S's will be cancelled. This will be S plus 3 upon S square plus 3S plus K, and of course I have this thing limit as S tends to 0. So if I put here 0, this will be 3 by K. So 3 by K, because they have given me the steady state error is 0.1, right? So 3 by K is 0.1 steady state error. So K would be 30. So 30 would be your answer for the question. Okay, let's solve the next question. Consider a permanent magnet DC motor, okay, which is initially at rest at t equal to 0. A DC voltage of 5 volt is there. We are applying a DC voltage of 5 volt as input to the motor. Okay. Its speed monotonically increases from 0 to 6.32 radian per second. Speed may be the output, right? In 0.5 seconds. In 0.5 seconds, it increases to this value and finally settles to 10 radian per second. Assuming that the armature inductance of the motor is negligible, the transfer function of the motor would be. So I have an input here, that is my motor. I have output. Output is my speed and input is my voltage, right? So speed upon voltage is the transfer function in Laplace domain, correct? So one thing I know, right, I see all of these are first order. So assumption is they are assuming that the motor to be a first order system. So a first order system can have only two things, either the DC gain and the time constant, that's all, right? So I will also assume that thing only. So I will assume that this ratio is k upon s tau plus 1, that's all. Okay. Now what is the time domain response? What is the time domain response, right? So the time domain response would be speed omega, if I, okay, and input is a 5 volt applied at the input at t equal to 0. So at t equal to 0 I am applying 5 volt. So it is just like a step signal, right? Voltage, input voltage is just like a step signal. So V of S is simply 1 by S, correct? So speed, I can write speed to be omega of S. So omega of S upon V of S equals to k upon S tau plus 1. So yeah, okay, so my omega of S would be equals to k, if it's a simply step of 5 volt, right? So it will be it will not be 1 by S, it will be 5 by S, okay, sorry for that, S tau plus 1 into 5 by S. Now I can simply use the partial fractions. So if I do the partial fraction, S equal to 0, this will be 5k by S, 5k is just a constant, and S equal to minus 1 by tau, right? So 5k is just a constant. Okay, so this will be 1 by S. If I put S equal to minus 1 by tau, minus 1 by tau, this would be tau by S tau plus 1. Okay. So yeah, this will be S tau plus 1 minus, yeah, that is correct. Okay. So now if I take the Laplace inverse of this, right? So this would be 5k 1 minus tau. Okay, this is not in proper format actually. Let me keep it as S plus alpha only, right? That will be easier for us, right? Okay. If I keep it S plus alpha, that will be easier for us to solve. That's why I'm doing it. So, okay. If I write here S equal to 0, this will be alpha S. Okay, 1 by alpha minus. If I put S equal to minus of alpha, this will be S plus alpha. S equal to 0 if I put, yeah, that's all. So I can take the alpha outside as well. Alpha I can take the common outside. Okay, yeah, that's all. Now it will be easier for us to, so this will be 5k upon alpha 1 minus e raised to power minus alpha t. That's why I did it, because to solve for exponential easily. Okay, you can do it anyways. Partial fractions, I hope you know, right? And Laplace inverse we have already discussed. So they've already told me that at t equals to 0.5 seconds, it is reaching to 6.32. So my omega t at t equals to 0.5 second, it is reaching to 6.32, right? And at steady state, right, I'm reaching to 10 radian per second. Finally settles to 10 radian. So what is the steady state value here? Steady state value here is 5k upon alpha. That is my steady state at t equals to infinity. So this will be equals to 10. That is what my steady state value is, 10, correct? So if it is 10, so 5k upon alpha is 10, so k upon alpha is 10. Okay, so here this is my k and this is not my alpha actually. So let me convert it into my format. So my format is this. So if I, this is my k, this is my alpha. So what is k upon alpha? It is 4, which is wrong. K upon alpha must be 10. Sorry, K upon alpha must be 2. Sorry, K upon alpha must be 2. Here, what is my K upon alpha? This is my K, this is alpha, which is coming out to be 20, which is again incorrect, right? So, yeah. So these are incorrect. So here I can convert this transfer function like this. I can divide by 0.5 on both sides, numerator and denominator. So this will be 20 upon, I can multiply by 2 on both sides, right? Yeah. So what is K upon alpha here? It is 10. Again, this is incorrect, right? K is this, alpha is this. Again, this is incorrect. Again, if I multiply by 2 on both sides, this will be 4 s plus 2. What is K upon alpha? It is 2, which is correct actually. K upon alpha is 2, which is correct. So only option B is correct. That will be my answer. I can of course solve it properly. So if you further solve it, right? If you solve it further, what you will get is one more relation, that if I put t equals to 0.5, if I put t equals to 0.5, my speed is 6.32, right? 6.32 equals to 5 k upon alpha. I already know that is 2, right? So I can replace here this with 2, that is 10. 1 minus e raised to power minus 0.5 alpha, because t is 0.5 seconds. So if I solve this equation, let me solve this equation. So this will be 6.32, this 1 ln inverse into 2. So roughly your alpha approximately comes out to be 1.99, that is 2. If alpha is 2, k is supposed to be 4. So my transfer function would be, this is my transfer function, right? So, or not this, sorry, it is s plus alpha actually. So it will be k is 4, it is s plus 2, but I am saying that I am not getting anything, right? That like that. But what I can do is I can multiply and divide by 2. Sorry, I can divide by 2 on both numerator and denominator. So this will come out to be 2 upon 0.5 s plus 1. That's all. So yeah, so option B is obviously it will match. Obviously it will match because we are pro, but yes, of course it will match. Let's solve the next question. Correct. So let's solve the next question. The closed loop transfer function of a control system is given by this. The input is this, the steady state response C of t. So whenever we have a input as sinusoidal, it's very simple, right? Output also will be a sinusoidal only. Okay, just what we have to do, we have to multiply by the magnitude. Amplitude will be multiplied by the magnitude. So what is the amplitude of the input? 1. It will be multiplied by the magnitude of my transfer function, okay, at omega equals to 1. And of course the phase will change, sine t plus angle of h of j omega. That's all. At omega equals to 1, obviously. Don't forget to put omega equals to 1. Okay. Okay. So yeah, what is the magnitude at omega equals to 1? It is 1 by j omega. Magnitude, if I do, it will be 1 by omega is 1, right? J plus 1, that is 1 by root 2. Okay. Magnitude is 1 by root 2. So this all these are possible. What about the angle? So angle, if I see, right, this will be minus of tan inverse 1 by 1, that is minus of 45 degrees. So I will have minus 45. So with sine I will have minus 45 or pi by 4. Pi by 4. So option D will be correct answer. Pretty simple, straightforward answer. Let's solve the next question. This one. A second order control system has closed loop poles located at this particular location. Now what am I observing? At time t equals to 0, which is the maximum value at the time t at which the maximum value of step response occurs. First of all, how are my poles? They are negative, real part is negative, unequal, imaginary, complex conjugate roots. So it is a underdamped system. And when do I get a maximum value of an underdamped system? At the first peak, basically at the first overshoot. And what's the formula for the first overshoot? It is very easy to remember. This one I think you will not forget. You might forget the rise time. Rise time is almost similar to this only, right? It is pi minus theta upon omega t. And what is your decay time? So all, because d is here, omega d cannot be there, this will be 0.1, 1 plus 0.7 zeta. Okay, that's how you remember, right? These three, always write this down together so that you can remember these things. Okay, so yeah, that's all I guess. So here now, yeah, let's solve it further. Yeah, so the peak time I know. What is omega d? I have to calculate omega d. Omega d is what? So your pole, right? So I have this pole location. So I know this pole location is basically omega d, omega d, and here I have the real part, zeta into omega n. So this is nothing but the imaginary part is nothing but the omega d only, right? So imaginary part is omega d. So omega d is 4 only. So omega d is 4. So I know omega d. I need to find out the peak time. It is very simple. No need to think. So Tp will be pi by 4. That's all. So what is pi by 4? Pi by 4 would be 0.785. So yeah, they are asking you to round off to 2 decimal places. So we'll round this off to 0.79, almost 0.79. Both are same. Both are okay. Okay. So yeah, 0.79 will be your answer for the question. Pretty simple, right? That's why I have told you, right? All understanding each things. It's very, solving question will not be difficult, but understanding the things is the important part. Let's solve the next question. So I have this question. Now here system shown in the figure has a time response like this, right? It is just a first order system, pretty simple, not that difficult. Input is 10 ut, step signal, ut being step, both k and tau are positive. The gain k of the system is okay, gain k. So input is a 10 ut, right? Input is 10 ut. So output, the steady state value of output is 8. Okay, and it's a first order system. So if I write down this, will you be happy with me? Okay. So what is the y of s? Y of s would be g of s upon 1 plus g of s into, this is the transfer function, into my input r of s, right? And what is the steady state value of y? Okay, limit as s tends to 0, s into this particular value, right? K upon s tau plus 1 plus k into r of s, that is unit step, that is 10 by s. S will be cancelled. If I put s equal to 0, again you don't have to check for stability. Anyways, it is a first order system. Okay, very easy. So this will be cancelled. This will be 10 into k. S is 0. So 10 into k upon, hold on a second, 1 plus k. Okay, that this value is equals to 8. That is given to me in the question. So from here you can easily solve for k. So 1.25 k will be equals to 1 plus k. So your k would be equals to 4. Okay, k would be equals to 4, right? That is the answer. Am I using any formula? No. In other place they will teach you this formula, right? But I will not teach you this formula. Like they will teach you the formula for steady state error as well, but I will not do that. I will solve by basics. Okay, because basics will never fail. Formula may fail. Let's solve the next question. So this is the next question. Now we have to solve for this. The step response of a circuit is seen to have oscillatory behavior. So it can be either underdamped or it can be undamped with oscillations dying down. So it has to be underdamped. There is no other options. The correct inference regarding the transfer function from the input output is that it is at least of second order. Yes, this statement is correct. For first order system, have we seen oscillations in the response? Never. In any step response, For first order system, we have never encountered oscillations. So it has to be at least second order. It can be higher order, but at least it has to be second order. That is the point one. That it has at least one pole pair that is underdamped. Again, this statement is also correct. At least one pole pair will be underdamped. Other poles can be lying far away. We can use the dominant pole approximation. We can neglect these poles, but at least one combination has to be complex conjugate. Because the system is underdamped, they have to be complex conjugate lying on the left hand side. That it does not have a real pole, that is not possible. It can have real pole, but those poles are insignificant. They are lying very far away from the origin, from the j omega axis. So I can take the dominant pole approximation. That it is a first order system. Wrong. It is not a first order system. Option A and B are correct. Let's solve the next question. A sinusoidal, this where this is my step input basically. So this is basically u of t. Okay. Indirectly they are telling this is u of t. Is applied to a transfer function with g of s this. The amplitude of the steady state output would be. Okay. So it is a sinusoid. Very simple, right? What will be the amplitude? So it will be amplitude of the output, right? Will be multiplied by the input amplitude into the magnitude of the transfer function at the frequency. Omega equals to 1. Here my omega is 1. So what is the magnitude of frequency? G of j omega, that is 1 by j omega. I think we have already done this kind of thing, right? So if I put omega equals to 1, this will be 1 plus j, magnitude would be 1 by root 2. So your finally amplitude will be 1. So 1 will be your answer for the question. Let's solve the next one. Consider a system with transfer function this. A unit step mu t is applied to the system, result in output y of t. If the, see here they have given you the definition. What is the steady state error? Okay. So this is the transfer function actually. Pretty interesting. This is the transfer function. This is not the OLTF. This is the transfer function. So g of s is not always the OLTF. G of s can be anything. So please keep this thing out of your mind that g of s can only be OLTF. No. G of s can be anything. It is their wish. It's the examiner's wish what they want to keep g of s. G of s can be output as well. G of s can be anything. So please don't consider g of s to be just the OLTF. It can be anything. Please keep this out of your mind. So consider a system with transfer function g of s equals to 2 by s plus 1. So it is a transfer function basically, t of s. Okay. I like my transfer function t of s, but that's fine. So they are asking you the steady state error, right? So what is your output? Output would be the input. Input is mu t. Mu t is applied to the system, right? So in Laplace domain, E of s would be y of s minus 1 by s. That's all. Or it's, I can for now write mu of s, right? For now, because I know mu of s is simply 1 by s. Okay, Laplace transform of unit step. So y of s is what? Y of s would be input into the transfer function t of s into mu of s. T of s is 2 by s plus 1. So I can take my mu of s common into, see here they have changed the definition actually. Our error definition was input minus output. Here they are asking output minus input. So they will give you the definition. If they want to ask some weird definition, they will give you that definition. So this will be t of s minus 1. Steady, again, as it is a NAT type question, there is no possibility that my system will be unstable. No possible. Okay, it has to be stable system. So this will be limit as s tends to 0, s into 1 by mu of s is 1 by s into t of s that is 2 by s plus 1 minus 1. Okay, so s will be cancelled. This will be 2 minus s minus 1 upon s plus 1, and of course limit as s tends to 0. If I put s equal to 0, this will be 1 by 1, that is 1. So your steady state error would be simply 1. This will be answer for the question. That's how simple the questions are. Okay, not that difficult. It will hardly take you 1.5 minutes. For a linear stable system, second order system, if unit step response is such that the peak time is twice its rise time, then the system is. Okay, that is very interesting. Okay, so first of all, my system cannot be overdamped, it cannot be critical damp. That thing is gone. Why? Because in overdamp the response is somewhat like this, in critical damp the response is somewhat like this. There is no concept of peak time or rise time. Okay, in underdamp the step response is somewhat like this. So there is a bit of concept of peak time because I attain the peak once, right? So there is a concept of peak time. So what is the rise time for a overdamp system? It is 0.7 zeta, right, by omega d. And what is the peak time? Peak time is pi upon omega d. So is there any relation? So they are telling me that the rise time, sorry, this will not be omega d. This will be omega d only because decay time is omega n. Sorry, rise time. Okay, sorry. Rise time is this, right? Sorry, rise time is pi minus theta. Yeah, rise time is this. Sorry. Rise time is pi minus theta. Yeah, because your decay time is supposed to be, yeah, your decay time is supposed to be 1 plus 0.7 zeta by omega n, because with omega n this term will always be there, zeta will always be there because zeta loves omega n. Okay, that's why zeta will always be there with omega n. So now how do I solve it? So they are telling me that the peak time is twice the rise time. So if I say this is twice, right, peak time is twice, so if I multiply 2 times to rise, I will get peak time. So from this I can get a relation, omega d will be cancelled, so 2 pi pi minus theta is equals to pi by 2. So my theta comes out to be pi by 2. That is interesting. When is my theta pi by 2? My angle of inclination is pi by 2. Basically, with respect to this axis, the angle is pi by 2, right? So basically my poles are lying on the imaginary axis. And when does my pole lie on the imaginary axis? When does it happen? When it is undamped. So this is the corner case. Okay, corner case. Very interesting question. This was the corner case of underdamped and undamped. Okay, so my system will be undamped. Okay, so these things you have to keep in mind. Now let's solve the next question. Here they have given you this circuit, and they are asking you whether your system will be overdamped or underdamped. First of all, they are asking you whether it will be high pass filter or low pass filter. How do you check what kind of filter is this? So you can check by putting s equal to 0 or s equal to infinity. So if I put s equal to 0, that means your inductance will be shorted because the impedance provided by inductance is s into L, and your capacitance will be infinite, it will be open circuit. So your inductance, I have only inductors, so I can short all the inductors. Okay, and this is my input and this is my output. So directly I can see my output is directly connected across the input. So VO is equals to VI. So definitely it is passing all the DC signal. So it has to be a low pass filter. How? So let's check. If I put s equal to infinity, I have to replace my inductors with open circuit because impedance will be very high. So if I replace this, this will be input, this will be open circuit, again this will be open circuit, and here I am measuring the output. So here I don't have any current, right? So VO will be 0 because this is a resistor. So VO will be IO into this 0 ampere of current into resistor, which is 0. So VO is 0. So it is not passing any high frequency signal. That's why it will behave as a low pass filter. Low pass filter behavior is like this. Okay, that is one thing. What about the this option C or D? So for this you have to solve actually. Okay, I will give you this as homework. So you find out the transfer function. Again, you can assume, you can take nodal here. So what you will do, you'll draw the circuit SL1 S. Oh, let me solve it anyways. So this will be what? L1 is 2, right? So this will be 2s. This will be 0.5s. Here I have R1, that is 2. No, you solve it. Okay, you solve it. This will be a bit lengthy. So this will be 1 ohm. Okay. So like, I hope we can take the nodal, right? That is my expectation. So I hope we can take the nodals and you find out the ratio of VO over S over VI over S, and then you will calculate the pole locations, right? You don't care about the numerator, you will calculate the locations of the pole you will observe that the pole locations are coming out to be negative, real and distinct. That means it is a overdamped system. That is the homework. Please do it. Okay, pause the video now and solve it. That will be a good practice. Let's solve the next question. So here we have to consider a negative unity feedback closed loop transfer function. So it is already told us that the transfer function of a negative unity feedback system is given. The steady state error with respect to unit ramp input would be. It is again unity feedback system. So definition is not mentioned. Again it is a NLT type. So definitely system would be stable. So because I have derived this so many times, I will write this directly now. Steady state error will be limit s tends to 0 s into your this value, right? Ramp input. For ramp input, R of s is 1 by s square into 1 minus transfer function, that is this, right? S, I'm doing this directly because we have already solved so much of this, right? So that's why I'm doing this direct. So this would be s square s plus 9, okay, ss will be there. This will be 1 by s, limit as s tend to 0, 90 will be cancelled. This will be s, I can take common, s plus 9. So ss will be cancelled. This will be if I put s equal to 0, that is 0.1. So 0.1 will be your answer for the question. Okay, I'm just doing it because we have already done these kind of questions. Okay, two linearly time invariant system, LTI system, basically the transfer functions are shown, have unit step response y1 and y2. Which of the following options is correct? Okay, we don't have the options here. Okay, that is unfortunately that is unfortunate. Okay, so yeah, maybe I will get the options now. Yeah, so I got the options. I forgot to copy the options. So y2 and y1 has same peak overshoot, same steady state value, same damp frequency. So okay, what is peak overshoot? So percentage peak overshoot is e raised to power minus pi cot theta. So basically, if their theta is same, that is basically if their zetas are same, right? Then they will have same peak overshoot. What is the zeta in the first case? Oh, both of them are in their proper standard format. Zeta in the first case, what is omega n in the first case? 1. Zeta is basically 0.5. 2 zeta to omega is, yeah, zeta is simply 0.5. Okay, what is the zeta in the second case? So it is basically what is omega n here? Under root 10. Okay, and your 2 zeta into omega is 10 equals to 2 zeta omega is equals to under root 10, right? That is what your coefficient. I'm just comparing with the standard second order system. So s square plus zeta omega n is plus omega n square. Okay, so I'll just comparing with the standard second order system. So yeah, this would be under root 10. Okay, so yeah, 2 zeta omega is equal to under root 10. So your zeta is simply 0.5. Yes, the first statement is actually correct, that their peak overshoot will be same because their zetas are same. So yes, their peak overshoot will be same. They will have same steady state value. Steady state value basically means that their DC gains are same, right? If their DC gains are same, if I'm providing same input, right, then their steady state value also will be same, because what is the steady state value? It is A into K, right? For unit step input, the steady state value, it is unit step response, so it will be simply K. K1 minus some, there was some sign omega d and this was there, right? Something was there. Steady state value, this will go away, only this will be there. So their steady state value is K. What is the DC gain here? 10. What is the DC gain here? 1. So their DC gains are different. So they will not have the same steady state values. They will have different steady state values. Okay. So this option is incorrect. They will have same damped frequency of oscillation. So I see they cannot have the same damped frequency of oscillation because they have same zeta, but they have different omega n, right? Omega n here is 1, omega n here is under root 10. So omega d is a function of zeta and omega n. So if they have same zeta but different omega n, so omega d damped frequency also will be different. You can calculate, it will come out to be different. Omega d is omega n into 1 minus under root 1 minus zeta square. It will come out to be different. They have same settling time. So settling time is 4 upon zeta omega n, both are under damped system, 4 upon zeta omega n, right? So they have same zeta, but they have different omega n. So they will have different settling time. So only option A will be correct. Let's solve the next question. This is the next question. So here, yeah, what is the, if I solve for this, right? Again, we have been given a block diagram. These are all Laplace transform, time domain signals. They have defined the error signal. Very weird kind of block diagram, but they have defined the error signal specifically. Assuming reference input to be 0 for all time t, what will be the steady state error E of infinity due to unit step disturbance? So they are asking what is the value of this due to a unit step disturbance. This is 0. Okay, very interesting. So they can, like, this is a real life problem, right? If there is some disturbance, what will happen to the error signal? Real life example. So let's solve it basically. Yeah, if I solve it, here I will have okay, let me solve, interesting. So what will be my error function? It will be simply minus of yt, right? Simply because r of t is 0, very simple. So what is yt? So this is 0, right? So if I solve, this part is 0, this Laplace is y of s, I will adjust y. So here I have minus of y. So this will be minus 10y. Okay. So d minus 10y. So here I will have d minus 10y. And I am multiplying this by this, right? So at the output I will have d minus 10y upon s into s plus 10. So yeah, this is equals to my y. So I can solve for y. So d minus 10y is equals to s square plus 10s into y. So basically your y will be equals to d upon s square plus 10s plus 10. Okay, that is what my d is equals to. So I'll replace it, right? So what will be my E of s? It will be minus of, again I don't need to check for stability, NAT type question. So d is what? D is a step input for a step disturbance. So this will be 1 by s upon s square plus 10s plus 10. Okay. Now what will be E of infinity, right? S into limit as s tends to 0, s into this value, right? Minus 1 by s square plus 10s plus 10. So this will be minus 0.1. So the steady state error will be minus 0.1. And trust me, right? Many students will not be able to solve these kind of questions because they don't understand the basics of error. So even though you are doing only the crash course, right? Not the crash course, this is the almost the full course only, R-PYQ series, but they have studied comprehensively from somewhere else. But they will not be able to solve it because all they know is just formula. They don't understand what is steady state error and how to solve it basics without any formula. They know is formula. What they know is formula. Okay, but trust me, like, this is simple for you, but for others it is not that simple. Trust me. Okay, so let's solve the next question. So the damping ratio and they are asking the undamped natural frequency for this particular configuration. Simply, I will just calculate the transfer function, right? So I can reduce this whole block diagram into a simple block. Okay, this is nothing but a negative feedback system, right? So this whole thing can be replaced by a single block. What will be the value? I know for a negative unity feedback system, it is 10 by s, g upon 1 plus gs. So upon 10 by s, which is 10 s plus 10, right? So this block will be replaced with this value 10 upon s plus 10. Or if you don't like this, again you can use that basic x here, you can assume x and you can solve it, but we will solve it using this. So this will be 10 by s, and here I have y, and here I have simple r, and don't forget again I have a feedback, right? Negative feedback. So again you will solve it further. So again this answer will be again g upon 1 plus gs. This time g is this OLTF, okay? Don't get confused. G will change. G will change. So s plus 10 into 10 by s upon 1 plus gs. So this will be 100 upon s plus 10. So if I solve this, this will be 100 upon s square plus 10s plus 100. Okay. So what is omega n? Omega n is 10. What is zeta? 2 zeta omega n is equals to 10. So your zeta would be equals to 0.5. So zeta is 0.5, omega n is 10. That is option A. So option A would be your correct answer for this question. Let's solve the next one. So LTI system is given, transfer function is given. The steady state output of the system, if the input is this, right? So for a DC input, so what will be the value of A and B if the input, let's say I'm giving 1 as input and sinusoid. So I can use the superposition. So due to 1, what will be the output? Due to a unit step, right? It is a simple steady state second order system, right? And I see that my omega n is under root 10. What is my zeta? Zeta is, so 2 zeta into omega n, that is under root 10 equals to 0.1, right? So your zeta would be 1 by 20 under root 10, which is less than 1, positive, which is less than 1. So it is an underdamped system, and for an underdamped system, I know if I have a unit step input, the steady state value is 1. This is a steady state value, right? This is a steady state output. Okay, it is A into K. A is 1 and K is K. What is K? K is the DC gain of my transfer function. So if I put s equal to 0, this will be 10. So K is actually 10. So this will be 10. So if I give 1 as input, the steady state output will be 10. So A has to be 10. So option B and D can be correct. Now, sorry, option D is also not correct. So option B is only correct. Okay. So option B will be your answer. Now, of course, if you want to solve for the other part as well, right? Just hold on a second. Yeah. Yeah. Now, if I want to solve for B, what would be my B? So for B, again, your amplitude will be, output amplitude will be 0.1, the input amplitude multiplied by the magnitude of the transfer function h of j omega at omega equals to 10. So omega equals to 10, right? So this will be 100 upon j omega whole square plus 0.1 omega plus 10, which is equals to yeah, 100 by minus omega square plus 0.1 j omega plus 10. So if I find out the magnitude, this will be 100 upon, so if I put omega equals to, omega is 10, right? So if omega is 10, okay, this will be j minus 90. Okay, that is what omega equals to 10 is equals to. Interesting. Okay, let me just check one thing. Omega square. Okay. Something is wrong actually. I am guessing there is a bit of typo here. Okay. Yeah, that is what I am guessing actually. This should be 0. I think there is a bit of printing mistake. This has to be 0. Okay, I'm sorry, I think there is a bit of typo here. That is what I'm guessing. This has to be 100 actually. So then your omega n is 10, your zeta would be 1 by 200, okay, which is still underdamped, but your k will be 1 actually. So your a is 1. So this and this is possible answer. Okay, I think there is a bit of typo here. That is what I'm guessing. Is it though? If it is 10 as well, this will cancel. This will be, yeah, this is fine. Yeah. Okay, there is a typo. This has to be 100. I'm sorry, this has to be 100. Like some printing mistake. So now if this is 100, right? So this will be plus 100. So basically, if I put omega equals to 10, this will be 0. Okay, the magnitude of this would be 100 simply, right? So this is 100, this is 0.1. So output amplitude will be 10. So B has to be 10, A has to be 1. Okay, A is 1 from this particular equation, A is 1. So option A will be correct. There was a bit of typo. So A has to be 1, B has to be 10. Let's solve the next question. Okay, so yeah, just give me 1 second. Yeah, a closed loop transfer function is given. Okay, shown in the figure. Steady state error due to ramp input would be. Again, you can simply solve it, right? If I were like they have already given you the Laplace transform of the ramp input as well. Like they're doing everything, right? There are options, but all the options are stable, finite value, so no problems. So you can solve it, right? I will give you this as homework, right? This you can solve. Okay, I can tell you the answer, but okay, let's solve it. Let's solve it, right? So pretty simple. The steady state error will be for unit ramp input. This will be limit as s tends to 0, s into alpha by s square into 1 minus transfer function. Transfer function is g upon 1 plus gs, that is k upon s square plus 2s plus k. Okay, I'm just doing this in a fast manner. So kk will be cancelled, s I can take common. So this will be alpha limit as s tends to 0, s plus 2, ss has been cancelled, right? S square plus 2s plus k. If I put s equal to 0, this will be 2 alpha by k. So 2 alpha by k is present in option A. So option A will be your answer for the question. Okay, again let's solve the next one. So again this one, the feedback control system is given. They are asking you to find out the steady state error. Now this right here, the option D is there present, right? Limit as the error does not exist. Okay, so this question was very interesting because many people, many educators as well, when they solve, they simply apply the final value theorem and they thought the answer was something else. Okay, so if I apply the final value theorem here, right, this will be limit as s tends to 0, s, and the input is what? It is a unit step. So 1 by s, 1 minus the transfer function, that is simply s plus 1, s plus 2 plus this 6. This is a transfer function, right? Directly you can solve it. So this will come out to be s into s plus 1 into s plus 2. 6 will be gone. This will be s into s plus 1 into s plus 2 plus 6. Okay. So if I put here s equal to 0, right? So you will see it is 0 upon 6, so it is 0. So many people answered 0, but it is wrong because the system itself is not stable. If you look at the poles of E of s, right? The poles of E of s, this is a problem to us. If I see the poles here, okay, you will see if I expand this, this will be s into s square plus 3s plus 2 plus 6. This will be s cube plus 3s square plus 2s plus 6. So this will be 6. So internal product is equal to external product. I do understand that. So what is this? What are you doing? Okay. In the next part, I will explain what am I doing. So just trust me that the system is marginally stable here, right? It is an oscillated system. So error signal will always oscillate. Just trust me. Trust on me, okay? Just put the trust on me. So that is the problem here. Correct? System is oscillatory. E of t is oscillatory. So option D will be correct. System is not stable. So be careful That's why I'm telling you just to be careful here. Let's solve the next question. So in the next part, I will explain how to find out the stability, basically how whether my system is stable or not. I will explain that in the next chapter. Consider the cascaded systems as shown in the figure, neglecting the faster component of the transient response. Which one of the options is a first pole only approximation such that the steady state value of the unit step remain same. What do I mean by steady state value of the unit step? Basically it means the DC gain, right? DC gain must be same. Okay, so what can I do? Approximation. So I see that I have two poles, right? If I multiply these two objects, these two block diagrams, I have one pole at s equal to -1, one pole at s equal to -20. So I have two poles. Now of course I can neglect the higher order, like the pole that is very far away from the j omega axis, correct? So this I can neglect. So approximately my system will be converted into s plus 1. Okay, of course I can neglect the 0 as well. So they have neglected the 0 as well. So it will be something k upon s plus 1. Now what is the DC gain here? It is 40 upon 20, right? That is 2. So here also if I put s equal to 0, I should get the same DC gain. So if I put s equal to 0, this is k. So this will be equals to 2. So my transfer function will be s plus 1. So first order approximation of my transfer function would be 2 upon s plus 1. That is option B. Option B is correct. Let's solve the next question. So okay, they've given you this. Consider the standard second order system. Okay, and the values are given. This theta and omega n are given. Which of the following things are correct? Settling time. They're just comparing the settling time, right? So settling time, if they are comparing, that means what is my settling time? It is 4 upon zeta omega n, correct? So zeta is nothing but cos of theta, right? That is theta from the negative real axis. Okay. So what is the zeta in the first case? It is cos 60. Cos 60 is half. What will be the zeta in the second case? I think it will be something smaller than half. I will just quickly verify. Something lower than half. Okay. So 70 would be 0.34. Okay. Now, so zeta omega n, right? For the first one will always be greater because in both case omega n is also lower, zeta is also lower. So zeta omega n in the case 1 will be greater than zeta omega n in the case 2. Okay, because both the values will be higher than these values. So inverse I can say, because it is inversely related, the settling time is inversely related. So I can say settling time of the first system will be less than settling time of the second system because they are inverse of each other. So settling time of system 2 will be more than system 1. Settling time of system 2 is more than system 1. So option B will be your correct answer for the question. Pretty simple and straightforward. Let's solve the next one. So we have been given the transfer function. Choose the range of zeta and omega n for the following options. So here, if the poles lie on the shaded region, if the pole is lying in this region, then what can be the possible value of zeta and omega n? So one thing is for sure, this is a circle of radius 2. So if my poles are lying beyond this distance, that means the distance is increasing. That means the radius of this circle is increasing. That means this distance is also represented by the omega n. I have taught to you, right? I have taught to you that this distance from the origin to this point is omega n, because this point is omega d, right? This height and this length is zeta omega n. Okay, and if you square and add them, it is a right angle triangle. So this forms omega n. So basically my omega n must be greater than 2. Omega n must be greater than 2. So these two options are correct. These two options are incorrect. Here they are saying omega n has to be greater than root 3, that is 1.732. Not entirely correct. It has to be greater than 2. So option A and B can be my possible answers. What about zeta? Okay. So I see that zeta, right? What is this angle? That is 60. This is 180, right? And this much angle is 120. So this will be 60. theta will be 60 degrees. Okay. So, yep, theta is 60 degrees. So, what is the range of my theta? Theta, the range of theta I see, it is going from 0 degree to 60. So, range of theta is 60 to 0. So, what is the range of zeta then? So, zeta is basically cos of theta. So, cos of 0 is 1. So, maximum value of zeta can be 1 and minimum value of zeta cos 60 is half. So, zeta has to be greater than half and also, okay, zeta can be greater than 1 as well, right? Yeah, zeta can be greater. So, for underdamped system I am talking, but for overdamped system zeta can be greater than 1 as well, no problem. Pole can lie, like the poles can lie here as well. For these kind of cases, zeta will be more than 1. So, zeta has to be greater than 1 by 2. Okay. So, zeta has to be greater than 1 by 2, that is present in option A. So, option A will be a correct answer for the question. So, even though I have not taught you the variation of poles and those things, but I hope you can solve this, right, with basic things. So, yeah, let's solve the next question. So, we have this question left. Consider the feedback. Okay, now this is very interesting. So, they have given you a feedback system where it is not unity feedback, but they have told you the definition of error. That is very interesting, right? They have given you the definition of error, and in everywhere it is finite. So, system will be stable. That is understood by us, correct? So, yeah, that's all. So, we can simply solve it. The definition is given, right? So, what will be the error? It will be R of s minus y of s. Okay, R of s minus y of s. So, this will be equals to yeah, R of s is what for a unit step reference. So, this will be, I can take R of s again common, 1 minus t of s, right? So, what is the transfer function? It is g upon 1 plus gh. So, s into s plus 1 upon 1 plus gh, that is k by s into s plus 1. So, this would be equals to s square plus s plus k. That's all. So, this is my transfer function. So, R of s is 1 by s. And what will be a steady state error? It will be limit s tends to 0, s into u of s, ess, right? So, I will multiply s. So, s will be multiplied. Don't, like, I'm just doing bit of shortcut here. So, this is my steady state error. 1 minus transfer function s square plus s plus k. So, this will be s square plus sk minus 1 divided by s square plus s plus k. I will put s equal to 0, right? And they have given you the definition, so you don't have to worry, right? So, this will be k minus 1 by k. So, your steady state error will be k minus 1 by k, that is option A. So, option A will be your correct answer for the question. Okay. So, yeah, that's all. Basically, these are all the questions. With this, we end our time response. So, I hope you have enjoyed this whole marathon. If you have enjoyed this marathon, please put a comment below. Please hit the like button. Please hype the video. That will help us out immensely. And of course, in the next part, we will be discussing about stability, Raoult-Hurwitz criterion, root locus. So that will be not that long. That will be also short video. So and after that, we can start with frequency response. Okay. So yeah, I hope you have enjoyed. So that's all. I will see you in the next lecture. Until then, happy learning.